This conference will now be recorded.
Sir, can you hear me, sir?
Good morning, Ranjan. Hello, Ranjan.
Yes, sir.
Are you able to listen to me?
Yeah.
Okay. Ranjan, actually, I am not used to this go to where to put my PowerPoint.
So there is a, there's a screen. You see the screen logo,
Uh-huh.
the
Yes.
computer screen? Yeah. So you click there.
Uh,
And besides that, mic, camera, there's a screen.
uh-huh.
So
Oh,
you click.
okay. The screen.
Yeah.
This screen part is not opening.
Screen part is not there, sir.
It is not opening.
Share screen. Please click on that.
Uh, what happened? Uh, it is suggesting this go-to meeting needs to use accessibility features, etc. And when I'm putting open system preferences, it is remaining in a cancelled mode. I don't know.
So when you click the screen, the
Uh,
screen share, applications will come. A number of applications. You select the application. Your PPT.
it is asking for open system preferences, but when I am actually putting that open system preferences,
Yes, sir.
it is vanishing. I don't know.
So after clicking the screen, what did you get?
Should I restart?
You can restart, sir.
Okay. Okay. Ranjan, that
Yes, sir.
screen part is again showing it.
I'm making you the presenter. Now you please click on
Okay.
the screen.
Okay. Uh,
Please click on the screen. When you click on the screen, the share
uh-huh.
my screen pop-up will appear. Then you have to select application.
Okay. Uh,
So please
I have
select
to
that
application. Okay. Okay. Applications. Oh. So when I put application, then what to do?
application. You select the PPT that you are going to do.
Okay. Okay.
After selecting the PPT, you click share. Yes, sir. It's coming. It's
Uh,
just coming. It's just coming. It's not
this
coming now. Just coming.
this PowerPoint, has it come?
It came, but it went off again.
Oh, I see.
Yes, sir. It's coming.
It is coming? Okay. Fine.
You can select the slide view.
Okay. Okay.
So a very good morning to one and all present. Welcome to the first session of Day 2 of the ATAL Academy sponsored faculty development program entitled Recent Trends in Upstream Petroleum Technology, organized by the Department of Petroleum Technology, Dibrugarh. It gives me immense pleasure to welcome our first resource person this morning, Dr. Kumar Lahiri sir, who will be speaking on the topic basin scale morphotectonic studies by using geophysical data archive, a heuristic approach. Dr. Kumar Lahiri sir is currently working as an associate professor in the Department of Applied Geology, Dibrugarh. He got his MS and Tech in Applied Geophysics from IIT ISM Dhaka in 1985 and subsequently joined ONGC as a subsurface geophysicist in 1986 to explore basin scale oil prospects in the Brahmaputra and the Barak valleys of Assam. In 1993, he joined Dibrugarh University as a faculty member. He was instrumental in developing the Applied Geophysics program at Dibrugarh University. He received his PhD from IIT Kanpur on basin evolution, morphotectonics, and fluvial processes in the Brahmaputra River system. Currently, he is engaged with connecting surface processes with different fields of subsurface geophysics. Please join me in welcoming Siddharth Kumar Lahiri. Over to you, sir.
So good morning, everybody. There is a great opportunity for me to address this session And I will just try to put forward uh, my experiences in the early days when I first got myself associated with this oil exploration business. Now I remember that our party chief at that particular point of time, uh, his name Mr. Kane Singh. So in the very first interaction, he just while taking the initial classes, he told us that oil is first found in the mind. Now, at that point of time, I didn't know that this is actually a very famous quotation from Wallace E. Pratt. And I also didn't understand properly that is what exactly it means. But now almost more than 3 decades have passed from direct association with oil exploration. I got opportunity to switch over to academics and subsequently uh, take up my own fields of research. And not only that, when we introduced in our course curriculum a subject which is of fundamental importance, that is philosophy of science. So then I could realize actually the depth of the statement. So I thought that let me start this whole session by paying tribute to Mr. Pratt, who coined this sentence, that is, oil is first found in the mind. Now, why we need to actually go through the philosophical issues related to oil exploration. Now, this was the actually paper in which uh, Pratt uh, suggested that what's called his views on oil exploration. Now, he was actually giving example his lifetime experience of 2 specific instances. One of the important administrators in USA, he suggested to him that the resource base of oil in USA is very limited. So it is going to be exhausted very soon. So USA needs to have control over other places so that their oil security is maintained. Pratt actually didn't subscribe that view. He was of the view that USA is not exhausted of its oil resources, but there is every possibility that it has exhausted its thinking capacity. So there is an immense scope for oil provided we think in different ways. Second example that actually he has given in that particular paper, some of the major oil companies believed at that point of time that Arabia does not have oil. And why they believed so, it is difficult from today's understanding of this oil systems. But because of that, many of those big oil companies backtracked, and one lesser known company actually it took up that operation, and a very one of the biggest oil fields was discovered. Pratt says that that particular company which discovered that oil field, it did not know the mindset of the big companies. They didn't, that particular company didn't know that those big companies thought oil was not to be found in Arabia. So perhaps that was the main reason that it did not become victim of that particular mindset, and that caused the discovery of that particular oil field. So what is suggesting that my experience has forced me to the conclusion that even the most finished art of prospecting by itself is not adequate to the task of finding the Earth's oil. There are other factors. And what are the other factors, and why those factors need to be considered? In this particular presentation, my emphasis will be some of the philosophical concerns regarding the mind searching for oil, then the object-subject relation in oil exploration, and I'm going to talk about a particular approach, that is the heuristic approach in oil exploration, what exactly it is, and then the continuation of basin scale geophysical studies in the fund-starved academic institutions, then major knowledge gaps in the Assam-Arakan basin, and morphotectonic studies for basin analysis, and certain different uses of available geophysical data archive, which helped us to see the things in new lights. Now, I will also try to put in this context some of the common misperceptions about oil exploration. So here, it is a very common way of thinking that all subsurface problems can be solved by technology and specifically by seismic. And there are beliefs that finding oil is a matter of luck. So the skill component is the ability to think. It plays a minor role. However, it is a very this is also a very common coinage that we usually find oil in new places with old ideas. Sometimes also we find oil in an old place with a new idea, but we seldom find much of oil in an old place with an old idea. So several times in the past we have thought we were running out of oil, whereas actually we were only running out of ideas. Now the question comes that what is the new idea? So John Masters, he was actually one of the pioneer investors in the oil and gas fleet. People paid values to what he uttered or whatever he said. So he was saying in one of his lectures that part of the definition of a new idea is that it will be rejected at first. So those who are actually going to put forward certain new ideas, they are supposed to go through a long period of frustration probably, but they should not be frustrated because evolution teaches us that most new ideas don't work. So we learn to be against them. Big ideas do not come from groups or committees. Throughout history, they have come from individuals, and normal people almost never recognize the importance of the idea until much later on. He also says that uh, the remaining potential is primarily unconventional. So long gone are the days that a geologist can find 100 millidarcy rocks on top of large anticlines. To achieve outstanding results, new exploration concepts must be applied. And few investors are willing to accept that degree of risk. So it is this backdrop which demands that we need to think in unconventional terrains so that we can have a proper match between the long-term objectives and the short-term goals. Now, here I am just trying to put forward a very common issue, that is what exactly is meant by the understanding or the process of cognition itself. Now, when we talk about the objective world, uh, in the modern times, mostly the things are related to stock exchange. That is how the things move in the stock exchange. So, if the stocks are running high or the stocks are running low, it has almost nowadays have become a part of the mental ecosystem where we live. So stock exchange is almost equated with the environmental changes. So you can call that our objective world, the objective world of a modern human being is highly regulated by stock exchange. Now it has become the second nature. Now the question is, that is, how to know that where at present my stock lies. We have different scenarios. So which one is true? It is a very difficult question, because it is a very abstract kind of understanding. It is a kind of value judgment. It is the differences in the anticipation of the participants, which also come in the form of books and bookies and so many other linkages. So the objective world is not mere your production and selling of oil. Rather, it is lots of speculations which also gets added to that world. And as a result, it becomes very difficult to know that at a given moment of time, where we are right now. Are we uh, on a curve which is presently a bit stable, but very soon it is going to rise? Or perhaps we are at a position where a simple future rise will subsequently give rise to a greater fall. So let us say that this is a kind of object-subject relationship which surrounds us. Now the question comes, now what is the objective world of a geophysicist? It is a very crucial issue. Now, geophysical problems by their inherent characteristics are inverse in nature. So when we talk about inverse in nature, so essentially what we want to mean that a similar kind of anomaly, maybe it is originating due to so many possibilities. Here in the first diagram, that is, you will see that it is shown that if certain ore bodies are falling within a cone, so if the shape of the ore body is fair, or it is a lens-like, or it is perhaps a lamina, for all those situations we will be getting the identical kind of gravity anomaly. In the second instance, it is shown that suppose there is a kind of structural change which is flexural, or perhaps it is a very sharp fault. The gravity method cannot distinguish that which one is actually uh, due to this anomaly. Third situation offers much more critical issues. Here, from 1, 2, 3, 4, 5, 6, 7, the way it is numbered, all these situations are supposed to give rise to same kind of gravity anomaly. So there are certain inherent ambiguities in geophysical exploration, in geophysical problems, which keeps the mind of the geophysicist busy, and they need to uh, bring into consideration so many other factors, so many other tools to have clarity that which suits best. Now, it is at this point we will definitely say that the quest for finding oil by the geophysicists and seeking truth by the philosophers are having a close parallelism. Now, the most successful of all geophysical methods, the seismic, it developed rapidly after the Second World War, when echo sounding of high frequency acoustic pulses could help to locate the seabed as well as submarines very accurately. Now, the only issue was to replace water with the earth materials. Now, just let us take a very simple problem. Suppose a signal takes 0.20 seconds vertically down to come back, and after hitting a target, then we know on an average the velocity of sound waves through water is 1500 meter per second. So if it travels two ways in 0.2 second, that means total length traveled is 300 meter. So the depth is 150 meter. It is a very reasonably simplistic your way of locating certain targets. But when we replace water by earth materials, it is apparently a very simple act, but the answer is not that easy, because earth is not a kind of this homogeneous continuum. Rather, even when we call it nicely layered, then also there are so many complex issues are there. So it is very difficult to find out that what is that particular average velocity that we can replace the way we took the velocity of sound waves through water as 1500 meters second. So what will be that particular average velocity? So here so many issues come up and things don't remain as simple as we wished. So definitely there is no doubt about it that geophysical methods work satisfactorily for different situations. Say, for example, here the situation that is being shown. Here, if you see this gravity, what's called the gravity method that is being shown here, this is the subcrop of a salt dome approximately. This is the subcrop part of from the magnetic methods that we get. Obviously, the seismic section, the seismic reflection section that we are getting for the situation, it is much more what's called representative, from which we can definitely draw a salt dome of this kind, which is not possible for either this gravity or magnetic method. However, once and say, for example, this kind of situation. Here we have actually a very nice subsurface view of geology across this Naga Patkai thrust belt. And apparently the things are known to us. That is this advancing frontiers of thrust is these are actually playing very significant role. But if we question that where from this nice sectional view came up, it came up from seismic sections. But if we consider the limitations of seismic sections, that is, when seismic sections say, when seismic sections, what's called your, when we uh, take up seismic work in those areas where the beds which we want to map are dipping, and if, as you see in the for this thrust belt zones, this dipping is highly variable, so there the data quality of seismic sections become very poor. Now, generally geophysicists, while mapping different horizons, they try to phantomize. That means they try to pick up smaller informations and try to fit the conceptual background and then draw those lines demarcating different boundaries. So drawing these phantom horizons is not merely joining similar looking points. Rather, you need to have certain probable models in your mind which will prompt you to interpret properly. So there lies the challenges. That is the type of what's called your sectional views which are being generated by geophysicists, how reliable it is. Say, for example, for this Naga Patkai thrust belt, uh, do we know that it is a thin skin problem or a thick skin problem? So, and again, the question comes: what do you call as thin skin problem and what do you call as thick skin problem? There is one view which suggests that in any kind of your stratigraphic succession, if you find that basement geometry is corresponding with that of the stratal geometry, so we say that it is a basement involved uh, subsurface. So that is a thick skin, because here what happens, the basement got involved, directly involved in shaping different strata. But if you find that the basement geometry is of one kind and the stratal geometry, that means different units of sedimentary rock deposits, their boundaries are independent of the geometry of the basement, then we call that as a thin skin problem, as if basement is behaving in one way and all the thrusting processes are as if sliding past the basement. Now, there are other views. That is, uh, instead of basement, they call that if the crust as a whole is involved in forming different stratal geometry, then that is a thick skin problem. And if the sedimentary strata that we are talking about, these are independent of the crustal geometry, then that is a thin skin problem. So we need to first of all settle those things. But have we settled it? The question is yet to be answered. So though apparently we know some of the things which are important directly from the point of view of immediate oil exploration, we are sometimes not ready to attend some of the broader geological issues. However, the urge for having unconventional ways of exploration, unconventional ways of your understanding, these demand that we need to address some of the issues which are regional in scope, which are much more larger than immediate drilling uh, of wells. It is in this context we need to think more in the coming days. Now, generally, if we go by the usual, the what's called the professional way of proceeding in the oil industries, generally we go by these kinds of situation. Suppose if the goal is to map the extent of certain gas field reservoir, let us say, we will try to analyze the amplitudes uh, in the seismics. If we expect that okay, certain gas bearing zones are there, so there will be certain differences in acoustic impedances. That means if normally the reflection coefficient is positive for gas bearing zone, we will be expecting certain negative reflection coefficient, so there will be a kind of phase reversal. So as a result, perhaps we will be able to directly identify those gas bearing zones. Now, if certain extent of gas is identified, we will perhaps just try to uh, uh, conceive of a system which perhaps looks like the way it is shown here. And gradually what happens, we try to uh, understand more and more what's called nuances. That means the way we understand it, is it exactly the similar way it exists in the subsurface? Say, for example, uh, is it possible that the things are actually moving the way we are finding it here? And if it is so, can we say that that means the type of expectation that we are going to have, it is going to produce in a similar way? Now, it is in this context that certain detailed analysis is being done, and geophysicists try to suggest different possible scenarios. That means from the seismic studies, perhaps we may not be able to know some of these complicated issues related to fractures and other things. And there certain speculative issues will be coming up. And depending upon the structural changes that particular place is witnessing, there's every possibility that the migration of oil will be guided by that factor. As a result, in some of the blocks which we think that it is going to have the amount of oil trapped, there is every possibility that if certain temporal sequence changes, that means which fault came after which, this kind of things change the way we are thinking, the site of oil trapment will change. So here, uh, these are some of the situations which is shown here, and as a result, it is possible that the understanding of oil generation, the provenance of oil might keep on changing, and we will be and we will be observing different types of scenario. So the same kind of have you any question?
बहुत दूर 10 किलोमीटर हो गया
Okay, I think somebody is
जी बीते जाते हैं पिछले मुझे पिछले हैं हम लोग डॉनबस का खाइए स्टेडियम और पिछले स्टेडियम का काकत स्ट्रीम है
so can you please identify talking
इसी हॉस्पिटल की सर्च जो रास्ता
hello
अपने
I'm getting some background noise.
इलेक्ट्रिसिटी ऑफिस टू पाए कि असम गैस कंपनी ऑफिस टू पाए इट इज अदर ना ও এটু একাডেমি নাকি তো এটু সব এমনি গিয়া
Okay, so
মোটা অনলাইন আছে
what
কম্পার্টমেন্টাল প্রতি আনিছে সেইবিলাক তো আছে কম্পার্টমেন্টাল কি আছে
hello Ranjan, hello Ranjan,
না মোর পেট্রোলিয়াম ওনারে এক্সপেল হতে
hello Ranjan, can you please take care of background noise is coming. Hello Ranjan,
yes sir
somebody is talking, actually I am getting disturbed.
yeah I'm trying to find out
Can you please mute his
4 ঘন্টা মান দিবনে আনসারটো দিওতে
okay, so let me continue. So one of
One
the
minute.
ways
1 minute sir
okay sir,
yes sir you can continue now
okay, fine. So what exactly we want to emphasize that the usual time that we give is to refine the data set. So for example, here we can find that these two seismic data sets, it was improved a lot by finer processing and other things. So in general, what happens, the industry is interested in the line that I'm showing here. That is, they will try to keep on improving the situations. Some of the reservoir simulations that they will be conducting, and subsequently they will be generating a geological model as realistic as possible. The question is that by doing so, can we say that okay, we have achieved a goal, or we have reached a position where the actual geology is known to us? Now here certain issues are there. Now for any situation where a reflector is not horizontal or near horizontal to the surface topography, complexity builds up. For dipping beds, and more specifically when the amount of dip varies frequently, the problem of migration and locating the target becomes increasingly less conspicuous. So the way, the clarity we are thinking that we are having, in actuality it may not have. Now, particularly mapping the thrusting affected subsurface of the foreland areas and elements within the thrust belt by interpreting seismic records are real challenges for even highly expert geophysicists. So at this point, unless the data from different disciplines are synthesized, it is very difficult to generate realistic models. And a more fundamental question keeps on lingering, that is, what exactly is the difference between a realistic model and a true model? Or where lies the truth? And to have a much more generalized question, can we say that truth is in geoscience is stochastic or deterministic? Or uh, is it a probabilistic, or it is a very certain kind of thing? What is the meaning of truth in geoscience? So here, this simple question calls forth attention, a philosophical attention, and for which perhaps we try to have certain enlightenment from some of the philosophers who are pioneers in the field of philosophy of science. So particularly, I feel fascinated by Karl Popper, uh, who coined that famous statement at certain points of time, that is, any theory which is not falsifiable is not scientific. Now, you see how critical that particular statement was. He was suggesting that the essential task of a scientist is to throw certain hypotheses, then go through systematically testing it, and then finally they will build up certain theories. But there is no certainty that that theory will remain as it is uh, forever. So he had before him the experience, and that means there was a long time for which the Newtonian world was the ultimate. So when the Einstein's suggestions came, it didn't came all of a sudden. Rather, some of the unsolved questions in physics uh, was actually acting as a force behind, and we could find that Newtonian world is limited compared to the world of Einstein. So there are certain micro as well as mega problems. That means the problems related to black holes or the problems in the atomic world. Those problems, those laws of motion could not be explained the way Newton gave us his laws. Now, what does it mean? Does it mean that Newton's law was ultimately proved wrong by relativity? No. What Popper says that because Newton's laws were falsified, that's why those laws were scientific. So any kind of belief which cannot be falsified or which is assumed to be uh, true forever, that is not scientific, that is a dogma, and that is very closer to the points of views propounded by theology. So those who are the practitioners of theology, from them the scientific understanding differs in this particular criteria. That means whatever you are proposing as a theory, whatever you are proposing as an hypothesis, at certain points of time, new situations will be coming up, and you will find that it is unable to uh, justify the new observations. So if that capability is there in that particular hypothesis and that statement, then only it will be called as scientific. Now, he was actually the Popperian position is like this. That means, suppose you are having a problem situation. So the task of a scientist or any person who thinks in a critical manner, they will try to have propose certain tentative theories which can address that problem situation. Your third part is error elimination. Now, when this error elimination comes, the sense he used was not in the sense of truth, rather it was uh, closer to the fitness of the problem with the situation in hand. And he was actually trying to explain this uh, biological evolution by making use of these theoretical issues. So he was suggesting that if you are having certain new ideas or if you are having certain more interesting issues, so he will be then jumping from the first problem situation to second problem situation. So that is the way the knowledge will keep on advancing by falsifying the previous issue. So in, it has got a tremendous implication not only in different branches of science but also in the geophysical investigations. Now it actually gives us a kind of progress spiral, that means how actually the knowledge advances. So the way we understand the external world by certain perceptual knowledge or by contacts with the objects, you may say, that we get certain knowledge. And this is called the first stage of cognition. That is objective matter to subjective consciousness, or we may say that it is a transition from existence to ideas, which includes theories, policies, plans, measures, etc. Now, individuals then go for certain scientific practices by synthesizing the data of perception, by arranging and by reconstructing. And it helps us to have another type of knowledge that is called rational knowledge. Now, with that rational knowledge, there is every possibility that certain individuals will be having first that kind of rational knowledge, and that rational knowledge subsequently is being practiced by a whole of community, and as a result, we go from one stage of perceptual knowledge, that is a community based perceptual knowledge, and then again a different level of rational knowledge as a whole develops, and this process keeps on changing the world. So the world of geophysics, the world of oil exploration has also changed by this way. We can have that kind of philosophical background from Popperian mode of thinking. Now, let us come to this heuristic technique. That means, what exactly is the heuristic approach? Now, heuristic approach is a very simplified approach. What it says that suppose if somebody is thinking that whatever I am interested in or whatever laws I have discovered, as because ultimately it is going to be falsified. So, so what should I do? So what should I do? That means if everything is ultimately falsified, then where from I will get my motivation to find out the truth? So what heuristic approach suggests that you have to keep on doing research with whatever means you have. If you are having a very complex problem, just try to break it into a number of parts. If you are unable to conceive the abstractness of the problem, just take a paper and draw certain simplistic sketches or diagrams. From that, you start thinking, but don't stop. You keep on doing research, you keep on thinking with whatever means you are having. So essentially, this heuristic approach suggests that you can take entry into the domain of research with whatever you have with you. Particularly for we, the researchers of third world country, this approach gives us lots of confidence due to so many reasons. So this particular theory was actually propounded by Imre Lakatos. He was actually a disciple of Karl Popper, and he was only trying to uh, put forward certain methodology. Uh, he definitely took that refutation and falsification ideas from Popper, and but he emphasized that research should be an integral part of any higher education in any form of intellectual activities, and that can be done even with very trivial resources at hand. So that kind of your understanding, that kind of what's called your approach to philosophy of science, it it actually brought a different kind of enthusiasm in so many countries, among so many scientific communities, because those areas which run short of uh, funds, those areas which run short of advanced, what's called your uh, technologies, they always keep on thinking that is uh, uh, that is whether science is for us or not. And particularly these high technology areas like this geophysical exploration and other things, where the cost of instrument is very high, sometimes it becomes very difficult to convince ourselves that can we do some good work in these areas, because we have got so many limitations. So it is at this point this heuristic approach helps a lot. So why are we interested in the heuristic approach? This is a very summarized overview. That is, unless quality research works are done, it is difficult to publish in the reputed journals. It is known to all. Now, in the post-COVID situation, higher education is in greater crisis, particularly in advancing quality research. Now, for conducting geophysical studies in the regional scale, generation of primary data is highly cost prohibitive. So, how to maintain the quality of research? The answer is by adopting this heuristic approach. So there are certain things available to geophysicists at the present point of time. So for example, we have got satellite-borne gravity data, we have got satellite-borne magnetic data. We can have very precise information about the topography. We can have seismological data, all free of cost. Along with that, if we can have or manage some data from some oil companies, then there is possible to generate good research work. So it is at this point we got interested in morphotectonic studies. That is how to make use of these geophysical methods to go for certain regional scale studies, which is having its long-term goals, as well as it can also address some of the short-term happenings all around us. So to summarize, when we talk about that, what goes on inside the mind of a geophysicist while interacting with complex geological situations, the immediate answer is a fine synthesis of four factors. That means the temporal thinking, it is how the things change with time, appreciating the earth as a complex system, learning in the field, and a spatial thinking. That means something which is changing in the space domain, how to conceptualize or visualize it in different planes. So if a particular person in the field of geoscientist can synthesize these four issues together, it becomes much more easier to take entry into certain problems. Now, to adopt this Earth system science approach for the area where right now we are located, that is in the upper reach of the Brahmaputra Valley, we just took the initial stand like this. That is, here the surface problems can be understood based on certain shallow subsurface changes as well as deep subsurface changes. Here by shallow subsurface changes, we want to mean changes within 100-meter depths from the surface. And when we are talking about deep subsurface, we are talking about only the basin scale changes, which is for this particular valley is always less than 10 kilometers. But if we go to this Bay of Bengal part, definitely this becomes much more than 10 kilometers. So as because right now we are in a position approximately to drill up to that on an average 10 kilometers of depth. So that is the limit of deep subsurface studies in practical sense. So we first of all took our study area this way. That is, there are three layers of natural resources in the surface, shallow subsurface, as well as deep subsurface. There are three layers of natural hazards, and there are three layers of knowledge gap. And unless we can connect these three issues together, it is very difficult to go to appreciate different problems and find out the internal connections. These are the data sets mostly we used, that is for monitoring the surface changes. We cannot have more what's called your reliable data beyond 100 years. So the 1915 topographic map and the subsequent topographic maps and the recent Landsat and other satellite imageries, we can have very representative elevation data from this SRTM model. And as I have already introduced, the gravity data. If we promise these oil industries that, okay, our research will be fruitful to them also, then on a number of occasions, they share some of their data. So Oil India shared some of their data with us. That is some seismic data and some data sets which they could not manage proper time to make some other kinds of uses like shallow subsurface, upfall and refraction data. So making use of these kinds of data archive, we did some research work which we feel that it has added certain values not only in the knowledge field but also in the practical field. There are certain other scope for those knowledge. So I will just try to briefly introduce those areas where we could develop some knowledge. So the data integration plan, generally we were mainly interested in this landscape dynamics with the basin evolution. So that was our central issue. So we tried to integrate the field observations with remote sensing data, then topographic maps, seismotectonic maps, etc., etc. So this was the plan of integrating the scheme of our work. And we started with certain premises that Brahmaputra Valley relief is structurally controlled. So when taking the cue from Karl Popper's what's called way of attacking the issues, if we say that Brahmaputra Valley relief is structurally controlled, so we need to prove it. We need to have some data for it. Definitely the geological elements, the geologists have already identified those things. We can go for certain simplistic studies. Say, for example, if we go by the take this river as a valley divider, then taking cue from this what's called your basin asymmetry factor, if we divide this valley into different reaches and just calculate the ratio of a particular side of the valley, here what is being shown is, suppose this is the median path through which a river is passing. If this valley is uplifted, then what happens? The general tendency is that the river will shift its position towards the uh, what's called your the downthrown side. Now here it so happens that if we just have the ratio of this particular area versus the total area of a particular reach, so we will be generating a number. In case the median path of the river is dividing the valley into two equal parts, this value will be 50. Otherwise, it will be either more than 50 or less than 50. Based on that, we could find that this upper reach of the Brahmaputra Valley is being controlled by two types of thrusts in two different ways. Mostly, this valley is controlled by the Himalayan frontal thrust, and partly this Naga Patkai thrust is also uh, controlling the valley. That means here by controlling, what we want to mean is that which control is more, that is which control is stronger. So depending upon different reaches, we find that this is a kind of competing tectonics between the Himalayan thrust and the Naga Patkai belt. In some of the areas, this Naga Patkai thrust belt also becomes dominant. Now, evidence of this structural control we can have from seismic data. So here I will be just showing you two seismic sections across the valley, that is AA dash and BB dash. So if you see it, this is the type of profile that we can get. This the first one is the uninterpreted and the second one is interpreted. So here what we observe, that if we see that there is a formation that is written as this Namsang formation, then there is the Dhekia Juli formation, etc., etc. But main thing is that there are certain sediment stacks which are of river origin or fluvial origin, and there are certain sediment stacks which are of marine origin. So here, if we just divide the entire sediment stack based on these two types of, here another profile, this is BB dash, then a very interesting thing happens. Suppose if we put these two seismic sections side by side and just try to identify the sediments which are of marine origin, then we will be getting a kind of what's called thing like this. Suppose if this part is the fluvial sediments, then we will be getting a kind of wedge like this. So here the point is, we are getting a kind of one wedge which is of alluvial origin or fluvial origin rather, I should say. That is the sediment sequestration that was being guided by the river processes. So it is shown by this yellow wedge, and that green wedge is of marine origin. Now, just this simplistic your separation of sediment stacks based on their origin gives us immense scope to understand this what's called basin better. Say, for example, if you just try to understand this particular diagram, here this green part is the marine facies. Let us, this is a cartoon. So this is the fluvial facies. Now, this fluvial facies was being constructed by a very big river, and that particular big river should be Brahmaputra-like, because when we try to define Brahmaputra, that function this Brahmaputra river actually it performs. So it is essentially a conduit, or it is essentially a channel through which the source and sink gets connected. So the source is the Himalayas, and the sink is the Bay of Bengal. So the sediment transport is being done by the Brahmaputra river and the other tributary rivers as well. So the basin, what we call as the Brahmaputra basin, is continuously being constructed by this river. However, when it was long back, no rivers were there, no Himalaya was there, it was part of an ocean. So at that particular point of time, the thickness of the marine facies that we see, if it is becoming thicker in the Naga Patkai end, then it is a general understanding that if you stand before a coast, the direction along which this marine sediment thickens, that is the deeper part of the sea. Now, in the seismic section, we find that the top boundary of this marine facies, it is going up. Now, it is not possible if after deposition, this basin is modified, or the basin is subjected to certain structural forces by which this boundary must have gone up. So this evidence, or you can assume that perhaps this side, it has subsided a lot. So if this is to happen, a very large scale structural activities must be influencing the whole valley for a very long time. So you see here, just by observing the seismic section and separating two types of sediments, we can rationalize the sentence that this basin is structurally controlled. So my point is that how to generalize some of the observations by simplifying certain issues. So here we were actually following this, what's called the approach suggested by Lakatos, or the heuristic approach. The things are available, but we are just trying to see it in a different light. Now, based on that, we can just prepare an overview of controls causing the morphological variability. And here we have just tried to modify a known sectional view proposed by Dasgupta and et al. In 1966, just by separating these different sediment characteristics. And then we suggested that how at different stages the basin might have evolved. So it is from the geometry of the stratal arrangement we can go to conclude in that particular direction. We also did one important thing, that is to suggest also, that is, suppose if across the valley we are finding the what's called the thickness of the fluvial facies is varying, we can go for a simplistic what's called understanding of it, that the places through which the river was flowing or staying for a longer time, there the sediment stack is thicker, and those places where the river stayed for lesser time, there the sediment deposition was also lesser, and that's why there the sediment thickness is thinner. Now, why a particular river should stay for a longer time at a particular place? So it is in this context we can think it further. That is, if a particular place has shown a tendency to subside frequently, so what will happen? New accommodation space will generate at that particular point. So if we assume that the Himalayan side, because of its, if you see it here, we have shown it, I am going back again. The eastern Himalaya side shows here the rate of uplift is higher. So from that end, the sediment supply will also be high. And there the rate of subsidence is also higher, and that's why actually this rate of uplift is higher. Whereas in the Naga Patkai end, there the subsidence rate is lower, upliftment rate is also lower, and the sediment supply is also lower. So that is the reason this what's called the sediment, which is of river origin or the fluvial origin, that is thinner in this particular site. In other words, in the competing tectonics, we can say that the side which is having higher heights of mountains, those are the areas where the rate of upliftment is more, or there the tectonics is also much more vigorously playing its role. And that is the reason that the sediment supply from that end is more. So all this understanding we are trying to develop from the seismic sections by dividing it into two sets of differences. Of course, to do that, we need to take help from the well data drilled at different locations on those profiles. Okay, so we just divided that this valley shows some of the regions a general tendency to subside, and there are other areas where a general tendency of upliftment is there. And there is certain other areas which will be having the middle ground. So broadly speaking, we can go for a zonation scheme that is a first order tectonogeomorphic zonation, whereby we will be identifying some areas as the areas experiencing uplift and other areas where the areas are experiencing a depression or subsidence, and there is a slope area. Now, this simplistic classification helps us to understand what's called here, that is the tectonogeomorphic zonation scheme that we practiced. And this particular zonation scheme helped us to understand the recent river dynamics which is happening in this part of the land. And if we see that from 1950 onward, the rate of change in the geometry of the river, its width, it has changed like anything. So we divided also that period into two what's called categories. That is, those changes which happened with certain jerks that this valley experienced in 1950. There was a very big earthquake. So there are certain co-seismic readjustment, and between two big earthquakes, the interseismic period, in that particular period, the valley try to either get back to its original position or certain new types of your subsidence and upliftment arrangement happens. Accordingly, we just try to uh, analyze the type of river dynamics that is being witnessed in this particular valley. So we measured some of the changes from 1915 onwards to 2005 by comparing the older maps and the recent satellite imageries, very precisely measured the changes in the bankline migration, width variation, in the what's called your sandbar bearing zones and the actually channel bearing zones. All those ratios we tried to measure. So we also tried to understand whether this river is showing certain aggradationary tendency or not, and accordingly we proposed a conceptual model substantiated by subsurface data and tried to explain it. So what is the extra thing that we did? This channel migration was measured by some of the previous workers as well. We of course went for more precise, more updated measurement of that. But earlier workers, they observed what was happening. We just added another component, that why is it happening? And for that purpose, we brought geophysical tools, geophysical data sets to explain the geomorphological changes. So it is a kind of a marriage between geomorphology and geophysics, which helped us to understand the morphotectonics of this valley in a better way. We also try to explain how the what's called the island Majuli evolved. Now, many people believed earlier that Majuli is like other islands of Brahmaputra, because if you visit Brahmaputra, you will see that Brahmaputra is having so many islands, which we sometimes called as the chor area. So should we put Majuli island in the same bracket? Making use of geophysical data, here it is shown that some sectional views, that means here which is running, if you see a small box within this Majuli and a seismic section, we are thankful to Oil India for sharing these seismic sections with us. The interpretation is ours. We could show that some of these basement highs match with the topographic highs of Majuli. And the maximum height of Majuli is much higher than the elevation when the river becomes full. Now the question comes that those islands which were being developed by Brahmaputra river, the average elevation of those islands cannot be more than the elevation when the river is full. So what we proposed, that this particular island comes under another bracket of islands which are called as the relict island. So relict islands are actually those kinds of islands, the age of which is more than the age of the present location of the river. In other words, suppose there used to be a highland and the river was shifting its course. Now, there is a possibility that either the river will cut that part, make it smoother, or the river will bypass it. So it is based on the strength of material, that means how compact that particular land mass is. So our suggestion was that a river actually bypassed that particular place. So the age of Majuli is older than the present location of the Brahmaputra, and we substantiated our data by comparing the highest point of Majuli with the what's called your basement topography, and we got a match. So that helped us to conclude that Majuli is not a merely geomorphic high, but it is a basement controlled geomorphic high. In other words, there is a possibility that in these valleys there might be many highs which are controlled by the basement. But it does not mean that all the highs or geomorphic highs are supposed to be controlled by only basement highs. There is every possibility, particularly in the foreland, immediate foreland part of this your mountain belts like Nagapatkai and the Himalayan hill. Laterally, some of the thrusts are coming up, which are not possible to see on the ground except a hump or a piggyback like feature. So those are not controlled by basement. Those are rather controlled laterally by those advancing frontiers of thrusts. So here all geomorphic highs do not necessarily conform the basement geometry. There is a possibility of influence due to those advancing thrusts. There can be situations where the basement topography is following similar trend to that of the basement. There are other possibilities where topography will show opposite trend to that of the basement. And there are third categories of areas where perhaps this basement related highs are also influenced by thrust related highs, where certain combinational situations will come up. So how this topography looks like, as because that is a very significant issue so far as the river dynamics is concerned, the residence time of a river, that is how long that particular river will stay at a particular place. So we felt that these surface processes, the landscape or the riverscape dynamics, if it is to be appreciated properly, fusion of subsurface data sets can help a lot. This is another work where we actually brought into use some of these geophysical techniques. This is in the your northwest India, where we tried to explain, that is the river Saraswati, if it does not exist anymore. Now, is it possible to locate through which path it used to flow? So here, of course, we didn't go into that question, that if it is no more there, why it is no more? Because that question needs to be addressed based on the tectonics, understanding of tectonics, how this plate was behaving. That is why most of the rivers at present point of time flows in the eastward direction. Say in the Ganga Brahmaputra valley, we see that most of these rivers are flowing in the eastward direction, but Saraswati used to flow in the westward direction. Okay, so why this Indo-Gangetic plain or in the Indian plate, at certain points of time, the rivers which used to flow in the westward direction, they got dried up, and at present moment of time we find most of the rivers are flowing in the eastward direction. So that's a very interesting problem, but we're here in this particular work we just try to identify that really it is a myth that there used to exist a river called Saraswati, or that was not a myth. Really, there was a river. So we just tried to prove here that yes, there was a river, and some of the geophysical tools can be used to prove that understanding or that kind of contention. Now, we also try to make certain other mathematical tools to understand the geomorphological changes better. And we use this first Fourier transform, the concept of first Fourier transform, in understanding river dynamics better. How did we do? Now here it's we just try to apply it in this upper reach of the Brahmaputra Valley area the way it is shown in this particular diagram. Now here, as I have discussed earlier, we just try to identify that is how the left bank and the right bank of the Brahmaputra river is behaving between two times. Now, here it is shown that this is the right bank line shift. This is the basin asymmetry, and this is the left bank line shift. And the time period that we considered here is from 1915 to 1975, and another time zone it is from 2000, that is 1915 to 2005. So here we find by that is what is the magnitude of changes. This here we are just what's called your plotting the shifts, and we find that we are getting a kind of curve now, a kind of wiggle trace like
Hello, sir. Your presentation has come. Maybe network issue. Yeah, it's coming now. Thank you.
okay. I think now I'm audible. Yeah. Okay. 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 Just let me go to this area. Okay. Now here the question comes. Say for example, suppose we are having a curve below. Now we can think that this curve is actually a superposition of different types of what's called your simple harmonic motions of different orders. So making certain overlapping or superposition and maintaining certain phase lags, it is possible to replicate this kind of change. In other words, we can say that this curve is the superposition of these different types of simple harmonic your waves. So if we just call that these different waves having variable frequencies represent different events, then we can go for a further assumption that those events which are regional in extent, those represent this long wavelength, low frequency phenomena, and those events which are very local in scope, those represent this short wavelength and high frequency phenomena. Accordingly, if we just make a smaller changes, that is in a Fourier transform, usually it is a time series data, That is, for that we try to find its the frequency content. Now, if instead of this time series data, we replace the time function with unit distances, then we can say the frequency will be redefined as number of cycles not per unit time, rather number of cycles per unit distance. So that is exactly what we did. That is, if we find that all along the Brahmaputra river, these different what's called its left side as well as the right side, or the left bank and the right bank, the way it changed its position, it amounts to a particular type of curve. So we can just find out its frequency content. So and that frequency content where we have replaced time value with the distance. So as a result, we could get these types of what's called your frequency content, and we found that this north bank and the south bank, it was showing some kind of similarity as well as dissimilarity. So we just try to then suggest that it is because of the competing tectonics. That means the way the Himalaya is controlling this basin and the way this what's called the Naga Patkai thrust belt is controlling the basin. These are actually variable because this width of the river comparing the width of the average width of the basin itself is very high. If we say the average width of Brahmaputra right now is 10 kilometers, and the average width of the valley at this point of time is around 100 plus kilometers. So 1/10 part of the area is being covered by this valley. So if the right bank and left bank we compare, that means the distance by which the right bank is located from the Himalayan frontal thrust, the left bank is 10 kilometers more away from that. So there's every possibility that then from the other end, the Naga Patkai thrust belt, the influence which is coming, it is influencing the left bank more, which is closer to Naga Patkai thrust than the right bank. So here the bank migration is getting affected due to two competing thrusts in two different ways. So here, by application of these concepts of basic concepts of Fourier transform, it is possible to shed new light on the types of forcings which are operational in changing the riverbank geometry in the last 100 years. Okay. Now, we also tried to shed certain new lights on a corridor that is called Disang corridor. If you go to Google Earth, you will find that this Disang is one of the highly meandering south bank tributaries of the Brahmaputra river, and it flows through a prolific oil corridor of Assam, having strong evidences on sin depositional tectonic controls due to the Naga Patkai fold thrust origin. So the type of mountain building process which is going on right now, it influences the whole valley in a very dynamic way. Now, this is the area that we are calling as the Disang corridor. So we will be just discussing some of our findings for these two corridors only. Now, we have picked up these two corridors because these are very complex areas. If we consider the seismotectonic map, we find that there are to prominent, this black one, it shows to prominent blind faults. That means those faults which were proved from the seismic sections, but on the surface you cannot see those faults. So those faults which are not having their surface manifestations are called usually the blind faults. It is these two faults are running along this Naga-Patkai thrust belt, and some of the major oil fields are located in this particular area, which is shown by some this what's called yellow marks. And as you can see that there are very clear your signatures of paleo channels, which shows that the rivers shifted their position all of a sudden at certain points of time. Because if a river shifts its position gradually, it cannot leave behind a very distinct kind of signature. But if it shifts all of a sudden, or if it shows a kind of avulsive character, this sudden shifting usually we call as avulsion. So if it shows certain avulsive character, that means the floor through which it was flowing, perhaps it experienced a sudden change in its tilt or slope, whatever you call it. So it is from that understanding, it is from that backdrop we try to follow, that is why these paleo channels marks cannot be related with the oil provenance or the oil fields existing right now. Is it possible to put forward certain explanations, that is why while oil is found there? So for example, we know that the north bank of Brahmaputra Valley hardly provides any oil. Most of the oil fields are located in the south bank part of it. And we also thought that why not make use of those data sets which usually oil industries don't need for their uh, work once certain types of corrections are being done. Generally, oil industries have very accurate shallow subsurface data to monitor the thickness variation of the loose layer, that is called the low velocity layer or weathered zone, because unless that weathered zone correction is done, some of the prominent subsurface reflectors cannot be mapped properly. Because in the seismic sections, it is the travel time which matters. So looser a formation, if it is very highly unconsolidated, so there the velocity, seismic velocity will be very slow, so there the effective time will be longer. As a result, the total time consumed to travel a deeper reflector, there a considerable portion will be shared by the shallow subsurface zone, and that will create confusion to map that deeper subsurface. So generally a practice is being followed that bring all the surface position to certain standard datum, so that the subsurface mapping is very accurate. So that particular correction is called a static correction. So once that static correction is being done, usually oil companies don't have much requirement for those shallow subsurface data. It is this kind of shallow subsurface data, which is called sometimes as the uphold data and shallow refraction data, we brought into use to advance some of our morphotectonic goals. So here, generally in the uphold data, certain first breaks are being picked up. And if you see that this is the way generally this uphold survey is being done. So as a result, what happens, we generally get what's called the data sets that is similar in scope to that with the refraction data set. However, in uphold data set, we are having only one-way travel time. So there, the reliability is much more compared to the refraction data set. Now, here, we just went for a particular kind of logical zonation scheme. That is, generally in the upfold data set, we can have these three values very accurately monitored. What are these three values? It is the velocity of the, let us call it as the P waves for the first layer, then the velocity of these P waves for the second layer, or this is the seismic waves we are talking about, and the thickness of the weathered zone. So these three parameters, let us say this is V1, V2, and H1, which is shown here. This is the ground surface. So this is the V1, this is V2, and this is V3. These are the different layer thickness values. Now here we just try to develop a logic, that is, if both the layers are having very high velocity, it implies that it is constituted of older floodplain materials which are already highly consolidated. And if the first layer is also thick, so there is every possibility that it is a regional high and older sedimentary rocks which were rather bypassed by the fluvial channels or older floodplain deposits got uplifted. So you see, if we have these three information, by making use of permutation combination of these three situations, we can have certain your explanations which goes like that. So if it is the first velocity is high, second velocity is also high, but the thickness is very lesser compared to the first. So this is a regional high, came into being much before the type 1, where the rate of erosion is higher. Similarly, say the third situation, if we find that the recent sediments are showing lower velocity, however, the earlier sediments or the V2 is showing, that is the higher value, and thickness of the zone is higher. So it is a presence of a channel that inside the older sediments, thicker low velocity material is caused by lack of channel dynamism. So as because at present point of time, a channel is flowing, or in the recent past it used to flow, so there loose materials will be more, and as a result the velocity will be lesser. So what we tried to see, that making use of these three parameters, it is possible to generate 8 different type situations, and accordingly a study area can be divided into different zones. So this is, we just experimented with a kind of multi-parametric micro-zonation scheme, whereby we divided these different classes. So if you consider 2 parameters, it will be a biparametric microzonations where the possible types will be 4. If you consider 3 parameters, then the possible type areas will be 8. Accordingly, the methodology is simple. That is, if for biparametric microzonation, if you think that, okay, the first layer is either can be high or low, second layer is also similarly low or high, then your next task will be just to divide it into these types of classes. Okay, so that is exactly being done to divide the area as per the biparametric microzonation. So we got the velocity values, the very accurate velocity values and the thickness values from either upfold data or refraction data, and then we subjected this particular area to this kind of micro zonation scheme. Similarly, for type parametric microzonation is a similar type of situations you expect. So here, when you are actually overlapping these three parameters, as a result, these 8 type areas are coming into picture. Okay. Now, making use of this, we just try to implement this kind of microjonation scheme for this Disang corridor, and we had a situation like this. So here, of course, a crucial issue is to choose certain threshold values by which you can consider a velocity as low or a velocity as high. This low velocity for the first layer and the low velocity for the second layer will definitely be different. So this kind of what's called threshold identification helped us to separate this low velocity zones from the high velocity zones, and from the pattern itself you can see that we are able to get tentative flow directions of certain channel like process. So these flood plain deposits, if based on this velocity discrimination is seen, it is possible to retrieve the past locations of those rivers, uh, and this is a very important work from the point of view of uh, understanding better the quaternary geology or the quaternary basin evolution process, that is in the last few thousands of years or millions of years, how the basin was evolving, how the landscape and the riverscape was changing. So it is by simple velocity discrimination it is possible to identify. Similarly, we went for a biparametric microjonation that I have suggested earlier here, and this is a what's called a triparametric microjonation. So these kinds of microjonation is helpful not only to locate some of the geomorphic highs, but it can also help to have a proper town planning if you are going to raise new cities in those areas, because definitely the you need to locate those stable zones where in these active areas, even if certain earthquakes are coming, you can minimize the loss. So to take up that kind of exercise also, these kinds of microzonations are very helpful. A similar thing was being practiced in the Amguri window. This is also a very oil-rich area, but it is also a very prospective area where we are supposed to have perhaps new breakthroughs in the coming days. So many companies are interested in these types of areas. And these are the actually data sets. This is the uphold data and refraction data sets, which Oil India was actually kind enough to donate us for research activities. And we believe that we could make certain innovative use of that. So here, this is the Amguri window, and the same thing by, sorry, just by velocity identification, mapping of different velocity values, you can see different patterns which resemble the rivers, or the rivers which are flowing in the immediate vicinity of those areas. So you can find out that the river right now, the path through which it flows, by comparison with the older maps, we can only have changes of say last 100 years or so. But if we can discriminate velocities, we can know in the past say 10,000 years or perhaps 1 lakh years what used to be the course of the river. So if we find that the direction along which the river has shifted from its past position, so perhaps that particular area was rising or subsiding, that means some changes in its slope happened, and as because rivers are very sensitive to the slope changes, so this rivers changed its course. Now you can relate with the available geology of that particular area, that if the slope of the basin in that particular area has changed, why has it changed? By that way, we can uh, predict certain ongoing structural changes which can have a very early breakthrough in oil exploration. You can cost minimize, because these kinds of data, it is not a very costly affair. It is mainly you are using the old data sets but infusing new ideas to understand the basin dynamics, which subsequently be related to costly subsurface data procured by seismic methods or any other kinds of methods. Okay, so in the Amguri window, these kinds of velocity discrimination helped us a lot to identify some of these what's called paleo channels, which in turn helped us to understand that the blind faults which were being marked by the seismic sections, how those actually displacements uh, along those blind thrusts are probably helping a particular area to get uplifted. So that kind of explanation we try to put forward by making use of awful data. So our what was the point that I was trying to build up is that similarly, so this is the biparametric zonation of the Amguri window, and the whole of the area was actually, if you see that this yellow part is about this V1 high and V2 high. So perhaps those areas are the uplifted zones, and you can have a very close correspondence with the uh, understanding that we have right now, that some of the areas in front of those Naga thrust belt mountain areas are very active. New thrust fronts are trying to come up, and as a result, we are getting those kinds of geomorphic highs, which during field visits may not be noticeable very clearly, but when we subject that particular area to certain velocity discrimination based on shallow subsurface data, it is easier to locate those highs from lows. Okay, so this is again the trimetric parametric microzonation for the same area. So in nutshell, we have just tried to show that this in the Disang corridor and the Amguri corridor, there's a possibility to study the changes at depths by finding out new uses of the shallow subsurface data. So here, the point actually what we are trying to make is that we need not feel frustrated about the fact that okay, higher or the fund is not coming to take up certain research work, or we don't have sufficient sophisticated instruments or laboratories. Rather, right now the need of the hour is to generate new ideas, to generate new ways of thinking, and optimize the use of the existing data archive, particularly for those areas. For example, the area that we were discussing right now, here the age of exploration has already crossed 100 years. So here uh, that helped to accumulate lots of data which can be used in so many ways to further quality research work. But what is needed is to grow a critical way of thinking. And I will like to conclude my discussion by making use of, by referring a particular outcrop section that was being drawn by P.B. King in 1942. So if you see the above, what's called your figure, at that particular point of time, they didn't have high resolution your smartphones or cameras. So many of the geologists, they used to draw what they used to see. Here, the beauty of this art is that all these things were being sketched by simple pencil and paper. Subsequently, the geologist's mind was used to discriminate these different types of rocks from those what's called your visible outcrops, and it helped a geologist to predict the progradationary character of that particular area. So whether how this sedimentation process happened in the past, that observation could be picked up by the geologist who was sketching these things and reinterpreting the data based on the training he had. So that is what is called creative thinking. And as long as this kind of thinking is uh, uh, encouraged, we can expect that new findings will be coming up from using old data sets as well as blending with different new concepts. So at this point, I will try to end up my deliberation. If you have got certain questions, I will be glad to address those issues.
Thank you, sir, for your presentation. Any queries from the audience? There is no query. There is one query coming from Sangam Mitra. What is Relic Island? What is Relic Island?
Now, it is not actually relic. Let me answer. It is R-E-L-I-C-T, relict.
Relic.
Yes, R-E-L-I-C-T, relict island.
Relic Island. Any other query? Okay. He's asking about the importance of Relic Island.
Okay, so there is a question about the importance of this relict island. So, for example, in very recent times, uh, another relict island has come on the map of this Brahmaputra Valley. It is called your DibrU Island. Now, there also we found that from seismic sections, of course, that once the tip of that particular island is crossed, suddenly the basement depth increases. Okay, so there the thickness of sediment deposition is much more compared to the central axis part of the valley. Now, if you remember, in the very recent past, there was a fire, is the Bagjan oil field fire. Now, it was reported that in that particular accident, from the gas wells, materials came up, which is called condensate. Now, how that condensate formed there, it is to be understood from the ongoing tectonic process. Is it a possibility that at certain point of time that area got uplifted? So the pressure temperature condition that was existing earlier that changed, and a phase change of hydrocarbon occurred there. So my point is that is, if some of these problems in the oil industry are understood with respect to the uh, processes related to morphotectonics of that area, better appreciation of problem is possible. And it is in that context, it is important to identify some of the geomorphic highs, which can very easily be identified if those geomorphic highs are at present point of time are relict islands, like Majuli or DibrU Island, which is also sometimes called as New Majuli.
Any other queries? You can type in the chat box.
So I believe there is no other query.
Other queries.
So thanks to everybody for your patient listening.
Thank you, sir. Thank you on behalf of everyone present in the program. I want to thank and appreciate Dr. Siddharth Kumar Lahiri, sir, for an interesting and insightful presentation on the various aspects of geophysics, starting from oil generation to seismic exploration, and the different studies you shown us the case studies about the Disang corridor, the Hamguri window. It was really nice listening to you, sir. I believe everyone enjoyed the presentation. Thank you. Thank you, sir. Once again, thank you very much. Thank you.
Thank you. Thank you. Thank you.
Now we will have a break of 30 minutes. So please join me again at 12:30 for the next session. So I'll make an announcement here also. We will have 4 sessions today because one of the resource person he has requested to shift the sessions to today instead of Thursday. So at 2:30 we will have a technical session that will be on water injection by Dr. Manish Kumar of Oil India Limited. So please join me again at 12:30 for session number 4. That will be a lecture on petroleum microbiology. by Dr. Akhil Agrawal of Central University of Odisha. So we meet again at 12:30. Thank you.
This conference will now be recorded.
Good afternoon, sir.
Good afternoon, sir. Good afternoon, sir. Am I audible, sir?
Yeah, yeah. Loud and clear.
So do I have the sharing rights?
Yeah, you have. I made you the presenter. You can say. So we are going to start now. So I welcome once again everyone to this fourth session of the FDP. So it's my pleasure to introduce our resource person for this session, Dr. ATAL Agrawal sir of Central University of Rajasthan, who is going to talk to us on the topic of production-related petroleum microbiology. Dr. Akhil Agrawal sir is an associate professor and group leader of Energy and Environment Research Laboratory at Central University of Rajasthan. He received his PhD from the Energy and Resource Institute, Delhi, New Delhi, and Flemish Institute of Technological Research, DITO, Belgium, in petroleum microbiology. To further extend his perspective in the same field, after his PhD in 2009, he joined the Department of Biology at University of Calgary, Canada, as postdoc scientist. Dr. Agrawal's areas of expertise are molecular biology of the oil field system. He had worked on prestigious hydrocarbon metagenomics projects sponsored by Shell, BP, Enerplus, Chevron, ONGC, Oil India, Assam, Baker Hughes, Nelco, Champion, etc. He has 30 publications in peer-reviewed journals and one US patent to his credit. His current research focuses on development of novel biochemical and hunter recovery technology for oil fields of India. He has won several awards and fellowships under Real Energy Innovation Award, JKLU Water and Environment Award, Best Business Plan Award, SERB Travel Plan, and Belgium Government Fellowship. He is a member of national and international scientific societies like Association of Microbiologists of India and International Society of Chemists and Biologists. He has successfully guided 3 PhD and 21 master's students. Please join me in welcoming Dr. Akhil Agrawal, sir. Over to you, sir.
Thank you very much for a very good introduction. And so we will start with the production-related petroleum microbiology, and I would like to keep this in a interactive mode. So wherever our faculty members want to ask any questions, probably they can just raise hand or put a question on the chat, or just unmute their mic and stop me, and then they can ask the question. Probably if it is in the more of interactive mode, that will be much better. And one more thing which I would like our participants to tell me is about their background, so they can just put in the chat quickly. They can put in the chat that what is their background from. Like I are most of the people from the petroleum background, or they are from the other background. So if they can just quickly put something on the chat that their background, so that this will help me in designing, like talking to you what I should talk. If there are people are from petroleum background, probably I would not uh, uh, go for a lot of details on the about the petroleum field. Otherwise, I'll start from the basics. So if everyone can put in the chat box their background. So chemical engineering, thermal engineering, mechanical engineering, chemical engineering. That's good. And someone else, if few more, I can chemical engineering. Yeah, so most of the people are from engineering background, so that's great. Few more if I can get. Yeah, petroleum refining engineering, very good. Mechanical engineering, fine, that's great. Right, petroleum engineering, good. All right. If I can get few more, one or two more. Organic chemistry, great, 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 great. Geosource engineering. All right, thank you very much. So yeah, so this has given me some idea that a lot of people are from either chemical engineering background or the petroleum engineering background, and mechanical engineering background. So probably most of them have a bit idea about the oil field and oil recovery, but there are other people who are from organic chemistry or the instrumentation engineering background. So they probably don't know about all the recovery processes. So what I'll do is I'll go through the recovery processes and the oil field microbiology. Initially, I rush through the recovery processes and the origin of the oil, and then I'll pay a more attention towards the microbiology of the oil fields. So I'll share my presentation now, and so sir, do I have to do the entire screen sharing or a window sharing?
Application. After you click screen, applications will come.
Entire screen? Is it?
And two options are there.
So
One
it
is
is
create
coming entire
application. Just
screen.
click.
Yeah. All right. Let me share and then see if I get it. So is my presentation visible now?
Yes, yes.
Sir, my presentation is visible?
Yeah, yes, yeah. If you can put
Hello?
in this, yeah.
Yeah, it's
Screen is,
visible. All right. So can you see? Yeah, you can see the first slide, right?
yeah.
Yeah, because
It's
I
with,
cannot see you guys, so I am just looking at my presentation. So yeah, just let me know if there is any problem. I'll go through my presentation right now. Okay, so thank you very much. Again, we'll start with the thank you for giving me the opportunity to talk in to our these esteemed faculty members, which are probably much more knowledgeable than what I can talk about petroleum microbiology. But nevertheless, I'll try to share my knowledge, whatever I have, and see, this is all what I've gathered from during my PhD and postdoc. So most of the things probably more of experience which I'll be sharing with you. If I have I am wrong at some place, please let me know, and we'll try to correct it at that moment only. And so let's start it with the first slide. These are in our at the very first slide. I will try to say thanks to our collaborators from government, which is like SERV, Department of Biotechnology, the Ministry of Science and Technology, and MHRD, which has given us a very huge project known as Imprint 2 for developing a new microbial enhanced oil recovery technology. And then the Department of Science and Technology, Rajasthan. And then these are some of our industrial partners, which are ONGC, Oil India Limited, Kane India, and some other academic partners like TERI, Assam University, and now the Dibrugarh University also, because now I am collaborating with Professor Subrata on a project which has been funded by the SER. And before I start, I would like to congratulate all you and wish you a very happy Women's Day. And this actually makes a lot of relevant here, because when we talk about the petroleum industry, it is more of man-centric industry. Lot of, when you go to a field, we rarely find any woman there. So so I can dedicate my this talk to the at least the three ladies whom I know are working in the field. Of course, Professor Subrata, who is a scientist in petroleum technology, Dr. Shikajan, who has a his own industry, Enercos Private Limited, and they are providing service of the petroleum industries. And Sugandha is a student working on enhanced oil recovery in my laboratory, and many more people, women who are working. So I am dedicating my talk to those people. Uh, and let's start with the outline of the talk. So, uh, what I'll be talking about is introduction of oil fields, origin of oil. So initially, I'll give the introduction of the oil field, what kind of oil fields are there, and then how the oil is originated. This is very important because we should know that the microbiology plays a very important role even in the origin of the oil. Okay, and that's why it is just not like the we are talking about the production related petroleum microbiology. Microbiology also plays a very important role in the origin of oil. Probably if there are no microbes, there is no oil which have been present on in beneath the earth's surface. And then there's a microbe which are present, microbial problems in the oil field, and their solvable solutions. So, and then I will talking about the two case studies, one about the oil field soaring and another microbial enhanced oil recovery. These are the topics which I will be talking about. So let's start with the oil introduction of the oil fields. And we know that oil is not going to finish very soon. Like me, that why you are working on the oil industry, oil fields, when people are shifting to the green energy or the renewables. Okay, why it is uh, important to work on the oil fields? And my answer is that probably for the next 35 or 40 years, oil is again going to be the largest energy source. And if we see the total oil consumption per day is like 97 million barrels, and this is not going to finish in one day. And if we want to keep the pace of the development in around the world, we have to remain dependent on the oil. So all the petroleum scientists who are working in this field are actually trying to make the oil production more greener, more eco-friendly. And that's why all of them has should be looked with the same respect with the people who are working in the renewables also. Because we what we are trying to do is we are trying to make the oil production more eco-friendly by using the microbial technologies. When we talk about the oil field, I'll go through this very fast because probably by now you must have been known about this oil field. So we have two kinds of oil fields. One are onshore oil fields, which are on the land, and other kind of fields are known as offshore oil fields, which are on the sea. Okay, so onshore oil fields, the production process is most of the production process or the technology is same for both of them. Only thing is, when we talk about the offshore oil fields, we have rigs there. On the rig, the whole platform is there for the from where the water is injected in the field and the production is done. While on the land, we have a surplus area where you can use the land for all the oil processing fit to put all the oil processing terminals. When we talk about the recovery of the oil, there are three processes which are three stages of oil production: from primary recovery, secondary recovery, and the tertiary recovery. So initially, when the oil field is found at any place, how the oil fields are discovered, probably I will discuss that also in the later stage. So initially, the oil well is drilled, and then the oil is
So your voice is not coming in.
There is no screen is coming.
Okay, sir, your voice is not coming. Okay, sir, your voice is not coming. You're not audible.
Hello, hello.
Yeah,
Am I audible now?
yeah, it's coming.
Yeah. Okay. Yeah. I guess there was a it broke in between. So anyway, I'm starting it again. Yeah. So my slides are visible now.
It's visible.
Yeah. Okay. So I was talking about the petroleum microbiology, how the microbes become important for the oil fields. So the first evidence for the microbes present in the oil industry, it came in 1926 when the Bustin in 1926 published a paper in Science which shows the presence of sulfate reducing bacteria in the oil field waters. Before that, it was sterile conditions, right? There are no microbes, there is no life present inside the reservoirs, and the most of the reason, most important reason for that was that the oil reservoirs are mostly the very high temperature. Some okay, and because of that high temperature, probably the microbes cannot sustain that temperature, and people used to think that the oil reservoirs are the sterile condition. There is no microbes which are present in the oil fields. But after 1926, this idea was changed, and there was number of papers and the discoveries came up in the later years, which made this claim more stronger. That yes, the microbes are present in the oil reservoir, and they are even important for number of microbial processes. So in 1946, Joel published a seminal review entitled "Action of Microorganisms on Hydrocarbons." Then in 1967, J.B. Davis wrote a book of petroleum microbiology, so forth and so on. There were a number of discoveries which made this claim more and more stronger. And now, probably each and every person in the oil industries, all petroleum engineers, they actually admit that the microbiology plays a very important role in the oil industry, and oil industry started hiring the microbiologist. Okay, to see the problems in the oil industry with a different lookout. Then if I talk about the, as I told you that I will also talk about the crude oil formation. So why I am talking about this, to show that how important the initial process of oil formation also contains, also have a higher contribution of the microbiology. So initially what happened, like there is a lot of uh, this biomass like the phytoplankton, zooplanktons, algae, and higher aquatic plant, invertebrates, and fishes. They buried inside the either in the seafloor or on the land. They started when there was a mass destruction. All of these biomass, they started burying inside the land, and they with time they what happened, they started settling down in the seabed, and then they started moving down in the sediments. And with time, because of the temperature,
It's not audible again.
yes,
Yeah, yeah, it's perfect. Yes, it's coming.
now it is audible now. It is
Yeah,
audible.
yeah, yeah, it's audible.
Hello.
Yeah, yeah, it's
Yeah,
audible
okay,
now.
all right. Yeah, yeah. So then this kerosene is converted into bitumen and then petroleum. Okay, so conversion of kerosene to petroleum is known as catagenesis. It is done at high temperature, 50 to 150 degrees centigrade, and this process is not microbial process, but the initial process of conversion of biomass to kerosene is a microbial process. And then we have a version of a this immature rock to this immature source rock to a gaseous form is known as metagenesis. So this is a same diagram which shows that the kerosene is converted into bitumen, and bitumen is converted into petroleum, and this process is known as catagenesis. And during the catagenesis, what happens, as soon as this petroleum is formed, it start migrating from the source rock towards the reservoir rock. Okay, so there are two windows which are present. One is oil window where the oil is generated, and there is another window which is known as a gas oil and gas started migrating from the reservoir rock. So what happened? There are three. When we talk about the migration of the rock, we need to know about the three different type of rocks, which is source rock, reservoir rock, or a cap rock. So source rock is the rock where actually the petroleum is generated, but as soon as it's generated, it starts moving through a porous segment of the
Again, your voice is not coming.
Hello. Yeah.
Yeah, it's
Hello.
coming now.
Yeah. Yeah. Okay. Yeah. So biomarkers are could be protein or carbohydrate. Okay. Do not. Okay. Hello. Sorry. The protein or carbohydrate do not survive at high temperature. However, the lipid are the compounds which can survive the high temperature, and thus they are present in the are as a biomarker. So carbon skeletons of the biomarkers remain intact through catagenesis and are a part of petroleum. Okay, so biomarkers share the carbon skeleton with compounds found in living organisms. So that's why we can trace them towards the which microorganism is responsible for the formation of the petroleum. And that's why these are very important for the discovery of the oil fields, for the discovery of the source rock where the oil is produced, and probably finding that at which era or at which time that oil reservoir has been formed. So these biomarkers are used by number of scientists for even for finding that a probable oil field. Nowadays they started using them as a to finding the probable oil field can be present at any place of the earth. Okay, most important biomarkers are steranes, isoprenoid, porphyrins, and carotenes. So these are the four different type of biomarkers. I'm not going to details of this, although I'm going to show you the structures of some of these. So these are the biomarkers which are kept in the universities. Okay, four main biomarkers are there, five biomarkers which are known as C35 Hopin. And you can see that their structure, when you compare their structure, you can always see that of the Hopins are is as similar as, sorry, the structure of four rings is as similar as a the structure of the cholesterol. How and the five rings are bacteriopentetrol. So these are the five rings structure which is actually present in the bacteria, and can these biomarkers can be traced up for those bacteria. So you can understand this, these biomarkers can actually gives the idea of which kind of biomass was used for the production of that oil. Biomarkers, that's why these biomarkers can be used for when we talk about to the petroleum geologists or the petroleum chemists, they can use the biomarkers for identifying the petroleum source rock, identifying the source organism from which the petroleum is derived, geological and thermal history of petroleum reservoir formation, and degree of biodegradation of the oil reservoir. So that's why those biomarkers are very important, and they are of biological origin. So these are the things why I'm telling you these things to show that this microbiology plays a very important role, and it cannot be keep aside in the petroleum industry. All but they should the microbiology and the petroleum industry, they should move hand in hand, so that they can number of problems which are present in the petroleum industry can be solved by the microbiological processes. The microorganisms which are present in the oil reservoir are mostly anaerobic. So what does anaerobic means? So anaerobic are the microbes which does not require oxygen for their respiration. So those are the microbes are known as anaerobic microbes. So because the oil reservoirs are the places which is devoid of oxygen, there is no oxygen present as such inside the oil reservoir. So the microbes which are present should have the capability that they can use other electron acceptors rather than the oxygen, and that's those organisms which can use the other electron acceptor for for their process of respiration are known as anaerobic microbes. So these microbes which are present in reservoirs are nitrate reducing bacteria, metal reducing bacteria, sulfate reducing bacteria and archaea, sulfur reducing bacteria, fermentative organisms, and methanogens. We'll read about them one by one, but before this I just want to know from the audience that till now whatever I have told is was understandable, or if any question is there, I am happy to answer that, and otherwise I'll go ahead with this thing. Just let me know that if if I'm going at a right pace, or do you want me to go a bit slower or a bit faster or whatever, in whichever way you want me to. Hello,
Topic.
can anyone any of you can answer? Is the pace okay, or should I go with a less faster, or CLP,
It's okay.
or I can go with the same pace? Hello.
Same phase is in W.
All right. So I guess it. All right. So yeah. Okay. So reservoirs are anaerobic, as I already told you. So the microbes which are present there are anaerobic, and which are nitrate reducing bacteria, metal reducing bacteria, sulfate reducing bacteria, archaea, sulfur reducing bacteria, fermentative organism, and methanogens. Let's read about them one by one. So when we talk about the nitrate reducing bacteria, what are those organisms? Nit- Nitrate reducing bacteria are those bacteria which can use nitrate instead of oxygen. So they use nitrate as a terminal electron acceptor. So when we talk about the nitrate reducing bacteria, there could be a two types of nitrate reducing bacteria. One are heterotrophic nitrate reducing bacteria. So heterotrophic, the term itself tells that these are the organisms. Heterotrophic are the organisms which does not make their own food. They use the food which has been made by the other, other organism. Okay, so basically what they use is they use oil as their food. Okay, and then in the process of driving the energy from the oil organics or from the oil, they use nitrate as a terminal electron acceptor. So heterotrophic nitrate reducing bacteria are those bacteria which can use the oil. So if you can see the reaction which is written in the bottom of this slide, you can see that the oil is converted into CO2. In the process, the nitrate has been converted into nitrite and ultimately to nitrogen. So those kind of bacteria are known as heterotrophic nitrate reducing bacteria. Second kind of nitrate reducing bacteria which is present in the oil field, and these are very interesting organisms because these are specifically found in reservoirs. Okay, so heterotrophic nitrate reducing bacteria can found in other places also, but SONRB, when we call them as sulfide oxidizing nitrate reducing bacteria, these are very specifically present in the oil reservoir or the places where the sulfide is present. So generally in the oil fields we also have a production of S2S. I'm going to describe about the S2S, how it is present in the reservoir, but the oil S2S is present. So these sulfide oxidizing nitrate reducing bacteria are the organisms which drive their energy by oxidizing the sulfide into sulfur or sulfate, and in the process they use nitrate as a terminal electron acceptor to convert nitrate to nitrite or nitrogen. So those are known as sulfide oxidizing nitrate reducing bacteria. So these are chemolithotrophs. Okay, so heterotrophic bacteria are heterotrophs, which means they use the already made organic compounds. However, sulfide oxidizing nitrate reducing bacteria are chemolithotrophs, which means they are using the chemicals, inorganic chemicals, for getting their energy. So those are known as sulfide oxidizing nitrate reducing bacteria. Other kind of bacteria which is present in the reservoir are iron reducing bacteria. So similar process as the heterotrophic nitrate reducing bacteria, they use the oil to convert it into CO2. In the process, they convert Fe+3 to Fe+2. So iron reducing bacteria are the other bacteria, other microorganisms which are present in the reservoir. Then we have sulfate reducing bacteria, most notorious bacteria which is present in the reservoir. So sulfate reducing bacteria and archaea are the bacteria which use sulfate as a terminal electron acceptor. So they use the oil or the lighter hydrocarbons, and these sulfate reducing bacteria can convert this oil organics into CO2, and in the process they convert sulfate which is present in the reservoir to S2S. S2S is sulfide. So when the sulfate is present in a reservoir, what these bacteria can do, sulfate reducing bacteria, they can convert the sulfate into S2S, which is sulfide, and this sulfide, being a corrosive gas, creates a number of problems in the reservoir, which we are going to discuss in coming slides. But so sulfate is converted into S2S when the sulfate is present in the reservoir, and we are going to see how big, how huge problem is this, as the oil industry is already spending billions of dollars every year just to control the sulfide in the oil fields. Number of oil fields has been just shut down because because of the higher production of S2S from these oil fields. So we are going to discuss this in very details in the coming slides, but right now just you get an idea about water sulfate reducing bacteria or archaea which can convert the sulfate into S2S. Those are known as sulfate reducing bacteria. Similarly, we have a sulfur reducing bacteria which can convert sulfur into S2S. and so those are sulfur reducing bacteria. Both of them are different, right? Some of the species of sulfur reducing bacteria cannot reduce sulfate. Okay, so that's why these two of them are written separately, because sulfur reducing bacteria does not have a capability to reduce sulfate. Similarly, some of the reducing bacteria does not have a capability to reduce sulfur. Sulfur is very stable compound, and that's why reducing it's kind of tricky. Then we have other organisms which are known as fermentative organisms, which are present in the reservoir, like a bacteria, archaea, and eukarya, which are present. Not the eukarya here, but the bacteria and archaea, which are present in the reservoir, which can, do the carbohydrate fermentation. So carbohydrate which are present in the reservoirs, like the volatile fatty acids, which can be converted into the, which can be fermented by the carbohydrate reducing bacteria. Some organic acids, fermentative bacteria are also there, which can convert the organic acids like the propionic acid, butyric acid, or the acetic acid into the uh, compounds like the CO2 or to methane. So generally a consortia of syntrophic organisms and the methanogens, they do this trick. What they do, syntrophic bacteria are those bacteria which can convert the organic compounds or the organic acids into a lower compounds like the CO2, and this CO2 and hydrogen is actually an intermediate which has been used by the methanogens to convert it into a methane. So syntroph and methanogens grow in consortia together. We cannot
Hello. Can you hear me?
Am I audible?
Yeah.
All right. All right.
Your
So then we have
cinematography.
hydrocarbon fermentative bacteria. So when we talk about these syntrophic and methanogens, these are very important oil field microbes because they grow in a association. Like it is like a syntrophs cannot be grown separately without the methanogens, and methanogens cannot be grown separately by the because of the without the syntroph. So this is a very good example of two how two different communities are growing together in the reservoir. Okay, so when we monitor the oil field microbes, generally what we monitor in the laboratories. Let's come to that. We can we in the laboratory, the microbes which we monitor are heterotrophic nitrate reducing bacteria, sulfide oxidizing nitrate reducing bacteria, and sulfate reducing bacteria. Why sulfate reducing bacteria? Because as I already told you, the sulfate reducing bacteria and they produce sulfate by the reduction of they produce sulfite and by the reduction of sulfate. Okay, so this how the sulfide is dangerous, we are going to discuss it in the microbial soaring. So now I'm going to talk about the microbial soaring. So this is what I have to make the background of how this sulfate reducing bacteria is uh, are harmful to the oil fields. So when these sulfate reducing bacteria are present in the oil fields, what they do is they convert the sulfate into sulfide. Okay, and this sulfide which is present in the reservoir, the concentration when the concentration of the sulfide increase in the reservoir, it is known as soaring or a reservoir soaring. So when we call it as soaring or microbial soaring or reservoir soaring is the same term which can be used in the oil as a synonym. So what happened in the oil fields generally, that when this sulfide is present in the reservoir, it has number of negative impact, or there are number of negative impact of soaring. Soaring is corrosive in nature. So what happened, this sulfide can is corrosive, and the pipes which are drilled for the oil production, they can corrode those pipes, and this could be very hazardous. Okay, and and the sulfide is again a very dangerous gas, as we know that 10 ppm of sulfide for 10 minutes could be fatal. Okay, you can a person who is inhaling the sulfide for 10 minutes, even the 10 ppm could be very fatal for the oil field workers. And this happens at number of fields initially, when people were not knowing about that sulfide could be that dangerous. A number of accident has happened. Nowadays people has become more and more vigilant, and probably we have to take the trainings of how to remain safe from the sulfide in the fields. But this is very dangerous. Second thing is that sulfide, because the density of the sulfide is higher than the air, so it remains, whenever the sulfide is produced in the field, it remains in the ditches or in the deep in the underground. So if there is a terminal unit of a oil fields, and where this in the terminal unit, suppose there is the underground go down, and when you go to in the go down, if sulfide is leaking from somewhere, it will not go out from the go down, because it has a higher density and it remains in the go down. And when if person is going to that place for something, or for clear for um, for repairing that leak, probably it could be fatal at that time. So it has number of casualties has happened before because of the hazard of the sulfide. Then it costs billions of dollar every year for replacement and repair of pipes. So this can show us the how bigger this problem is. Billions of dollars are every year just used for replacement and repair of the pipelines. Okay, and this data which I can give you the exact data, and this is the data just from the United States. So we can see about how much money we actually spend on the controlling the soaring in the oil fields. Okay, and one more problem of the soaring is that if the sulfide is higher in the produced oil, then generally this that oil is not considered as good, and can be rejected by the refineries, because they just don't want to take risk with the soaring problem. Okay, so all of these negative impact of soaring makes it very very important for the oil fields to keep the soaring into a range, so that it should not increase a lot in the oil fields. Okay, I have worked with number of oil, on this soaring for probably for number of years, and in those years I have understood that if there is a small amount of sulfide which is producing in the oil fields, the producer is has a great, can be in very great troubles. Number of oil fields has been just shut down because of the problem of soaring. So how this soaring is controlled, can be controlled in the oil fields. Number of processes are used by industries to control the soaring. One of the process is sulfate removal. So the water which we have inject in the oil reservoir, so as we have already discussed that during the secondary recovery, a huge amount of water is injected into the oil fields, and this water from where, this is a huge amount of water is required. It's just not like 1 or 2 barrels, it is like millions of barrels of water is required to be injected in the reservoir. Okay, and when this water is in so from this, where this water comes in the sea, when the in the offshore field it is directly taken as a sea water, while in the offshore field generally it is taken from the underground aquifers or from the sewage treatment plants. Okay, and that much amount of water, okay, is generally have the sulfide, because seawater has almost 30 millimolar sulfide. And when we talk about sewage treatment plants water and all those water, they also have a sufficient amount of sulfate which is present in those water. And this sulfate which is present in those waters, if this sulfate is going in the reservoir, it is going to convert into sulfide. Okay, because sulfate reducing bacteria are indigenous to the reservoirs, they are present in the reservoir. As soon as this sulfate is going in the reservoir, they found a very conducive conditions, because the oil is present as an electron donor, sulfate is present as an electron acceptor, and when these both were places, when the sulfate and the oil both of these two things are present for the bacteria, they started converting the sulfate into sulfide. Okay, so first and foremost, if we talk about controlling the soaring, if we can just inject the water which does not have sulfate, then the problem is solved. But again, it can be done with the help of ultrafiltration or by the reverse osmosis. And doing the reverse osmosis or the ultrafiltration for such a huge amount of water is not possible. And that's why generally the industries do not care about ultrafiltration of the that much of amount of water, because this is huge. Then the sulfide scavengers are used by the oil industry. All the oil industry use the sulfide scavengers, which can scavenge the sulfide which is present in the water. Biocide treatments are done: oxidizing biocide, non-oxidizing biocide. So what are biocides? Biocides are the compounds which can kill the bacteria. Okay, so oxidizing biocides are there and non-oxidizing biocides are there. All of them has a different mechanism. I'm not going to discuss those mechanisms right now, but these biocides are used by the oil industries. Okay, each and every oil industry is using the biocide for controlling the sulfide in the oil fields. Some of them are using the oxidizing biocide, other are using non-oxidizing biocide. If I talk about the Kane Energy, for which I was working on a soaring control project, they were using acrolein. So this acrolein is a non-oxidizing biocide. It's very dangerous also, and this biocide is used by them for to control the soaring. And then the next one, which is pretty recent techniques which is used to control the soaring, is injection of nitrate. How the injection of nitrate can control the sulfide? This is totally a biological process or a microbiological process. So in this slide, I'm going to tell you that how nitrate can actually control the sulfide in the reservoirs. So there are more than one mechanism how the nitrate can control the sulfide production in the reservoir. One is biocompetitive exclusion, that both sulfate reducing bacteria and the nitrate reducing bacteria, they compete for the in the reservoir, they compete for the same oil components. And when they when they compete for the same oil components, because the nitrate reducing bacteria has a more energy favorable reaction, they outcompete the sulfate reducing bacteria, because these bacteria are easy to grow. Their mechanism of growing is more easier. In a very, very layman term, they can grow very fast than the sulfate reducing bacteria, and their reaction is very energy favorable. These nitrate reducing bacteria, heterotrophic nitrate reducing bacteria, can outcompete the sulfate reducing bacteria, and when they outcompete the sulfate reducing bacteria will not grow. So this is the mechanism known as biocompetitive exclusion. Second is oxidation of sulfide. As we already discussed about sulfide oxidizing nitrate reducing bacteria, what it can do is it can convert the sulfide into sulfate, back to sulfate. So this is like a reverse soaring. All the sulfide which is present actually in the reservoir can be converted back to sulfur or sulfate, and in the process of converting nitrate to nitrate or nitrogen. So this is oxidation of sulfide. So the sulfide, which is a very dangerous gas, can be again converted back to the sulfur. Then the third mechanism is nitrite inhibition of DSR enzyme. So this DSR is a one of the very important enzyme of sulfate reducing bacteria. The process of conversion of sulfate to sulfide is has a very specific gene which is known as DSR gene. This DSR gene produces DSR enzyme, bisulfide reductase enzyme. So that bisulfide reductase enzyme is dissimilatory bisulfide reductase enzyme. So this is DSR, dissimilatory enzyme. So nitrite, which is produced in this process, can inhibit the DSR enzyme. Okay, so DSR enzyme also have a affinity with the nitrite. So once this nitrite is, you know, is bind to the DSR enzyme, sulfite cannot bind to that. The sulfite cannot bind to that enzyme to convert it into sulfide, and in that way it can inhibit the production of sulfide. And the fourth is increase of redox potential. Nitrate, when it is injected in the reservoir, it can increase the whole redox potential of the reservoir, and or a redox potential of a particular zone of a reservoir. And when this redox potential is increased, okay, sulfate reducing bacteria anyway cannot grow in the reservoir, because the sulfate reducing bacteria require minus 70 millielectron volt as redox potential, and nitrate reducing bacteria, and as soon as the nitrate is injected, it can increase the redox potential of the reservoir. So these are the four different mechanisms by which nitrate can control the uh, sulfide production in the reservoir. This is in theory we have four mechanisms, but when we talk about the practically how, if the nitrate can control the soaring in the reservoir, that has a very different results. Okay, so I'm talking about the first case study. So till this part it was a basic study of microbiology which I have told you. Now let's come to the more practical part of petroleum microbiology. Okay, so this is the first study from the oil field which is present in the Badmer, Rajasthan. So this project was given to us to control the soaring which is present in their oil reservoirs, in the three oil fields which are producing which are actually running there: Mangla, Aishwarya, and Bhagyam. So all of these, most of those production wells are producing the sulfide. So they has given us to the project to first of all identify what all sulfate reducing bacteria is present there, and if we can design a method to control those sulfate reducing bacteria, or to control that sulfide which is produced in this oil field. So in this oil field, when we talk about this oil field is moderately high temperature oil field, which is like 70 degrees temperature is there in this oil field. The water which is used in this oil field for the recovery is from the underground aquifer, which is known as a Thimbli aquifer. So from the Thimbli, the water is brought to the surface, and it is again injected into the reservoir rock. Okay, so that the oil can be produced. I'm going to show you this whole process how it is done. So you can see here this in the diagram on the right side below. You can see this is a Thumbli deep saline water aquifer. So this is a Thumbli aquifer from where the water is taken out. This water is brought to the water storage facility, and in this water, the water which is actually separated from the oil which is produced is mixed here, and then this is again injected into the oil fields, which are Mangla, Bhagyam, and Aishwarya. These are the three oil fields. So this is again injected in these three oil fields. So this is a process which is taking place in the uh, which is taking place in the Barmer oil field, and when the produced water which is produced in the oil field is again injected back into the reservoir, the process is known as PWRI, produced water reinjection. So produced water reinjection is done in this oil field. What is a problem? The oil field as such does not have high sulfate, but the water which is coming from this deep saline water aquifer, Thumbli aquifer, has almost 5 to 6 millimolar sulfate. This 5 to 6 millimolar sulfate is ultimately going to convert into sulfide at some point of time when if it is injected into the reservoir. So this water which is coming from this is which is injected into the oil field. So when we brought the samples from the oil fields, and we did the sequencing for this amplicon sequencing of the oil field sample to find out which microbes are present in these different samples. So we have collected the samples from the aquifer, we have collected the samples from the water storage facilities and the oil on the oil and all the oil fields. I'm going to show you some of the representative results of this sequencing. So amplicon sequencing is a technique by which you can, isolate the DNA, initially isolate the DNA from the sample which is present. The DNA composed of DNA of all the microbes which is present in the reservoir. Okay, so what we do, we generally don't grow the bacteria in the laboratory, but we brought the sample directly, the water sample. Directly, we have isolated all that DNA from that water sample. So the microbes which are present in that water sample, all of them has all the DNA of those microbes are present in that. Now we have that DNA, and now what we do the sequencing of that DNA, so that we get the sequence like ATGC, a DNA sequence. I'm sure all of you know about the DNA sequences, and that DNA sequence is then identified with the help of softwares to find out which microbial communities are present there. So when we talk about this amplicon sequencing of a source water, which is a Thumli aquifer, we found that almost 80% of the 70% of that community is bacillus. Bacillus, and there are other few communities which are present. I'm not going to detail of this. And then we talk. So when we did the sequencing for the injection water, we found out that one of the major community which is present here was a Tepidiphyllus, and Tepidiphyllus is a known nitrate reducing bacteria. So what this nitrate reducing bacteria is doing in the reservoir when there is no nitrate injected in the field, and we came to know with a very interesting phenomena which is taking place in the reservoir is that this nitrate reducing bacteria Tepidiphyllus, although it is able to inject to reduce the nitrate when the nitrate is present, but in the absence of nitrate it can work as a fermentive microorganism. So you can this is a microbe which is switching its capabilities according to the food which is present for it. If the nitrate is present, it can work as nitrate reducing bacteria, and if the nitrate is not present, it is working as a fermentative bacteria. So this was one of the important microbes which we found out, and this has given us some idea that if this microbes is present, and if this microbe was not present in the source water but it is present in the injection water, which is a mixture of source water and the produced water, shows that this Tepidiphyllus is coming from the produced water, and which means it is present in the reservoir. And this gives us an idea that probably the nitrate injection in this field can do the job, because if we are injecting a nitrate, we need to be sure that nitrate reducing bacteria are present in the reservoir. If the nitrate reducing bacteria is not present in the reservoir, probably will not be able to control the sulfide by injection of nitrate. Then we have done the amplicon sequencing for the produced water also, and we found a higher percentage of Tepidiphyllus there also. So this was actually again proved that this Tepidiphyllus is actually coming from the reservoir. So which shows that reservoir already has this Tepidiphyllus organism, which can actually a very good nitrate reducer present in the reservoir. Other microorganisms which are present are some of them are sulfate reducers, some of them are fermented bacteria. Hello, is there any question? All right, if no, I'll go ahead with this. So, in summary, what was in the source water we have a bacillus, which is a chemolithotrophic bacteria. However, in this uh, this uh, produced water, we have Tepidiphyllus, which is a nitrate reducing bacteria, and this nitrate reducing bacteria and sulfate reducing bacteria both are actually using the organic acids or the carbon source which is present in the reservoirs. So the idea was to control the sulfate reducing bacteria in the oil fields with the help of nitrate. So we did some tests for this. So initially tests were done in the laboratory, which was done with the help of these bioreactors column, oil field simulating columns. So these are the small columns. So these are like the small oil fields which we have prepared in our laboratory, and try to see that whether we are able to control the soaring problem in our laboratory with the water sample which is brought from the lab from the field, to see whether if we inject this water in these columns and we try to control the soaring in these columns with the help of nitrate, whether we can do it or not. So these act as a mini oil fields. Basically these are made up of syringes. So these are 60 ml syringes which has been uh, the sand has been filled in these syringes, and then the oil was injected in this, and then the water flooding was done with the water which has been brought from the laboratory, from the field, and these has been kept at the high temperature like 70 degrees, which are the field with a downhole field temperature, for the establishment of soaring. After 15 days, what we found out that these columns, these oil field columns which we have made, all of these has a all of these columns were producing the sulfide, which means the sulfate reduction has already started in these columns. Okay, so once this sulfate soaring has been established in these columns, we try to control the soaring with the help of injection of sulfate, injection of a biocide which is known as benzyl acrylonium chloride. Why we use benzyl acrylonium chloride? I'm going. This was actually, with the discussion with the oil field persons, and with our knowledge, we thought that benzyl acrylonium benzyl acrylonium Belgian acrylonium chloride is a biocide which is compatible with the nitrate. So we have done some experiment initially, which I have not shown here, and try to find out that which biocide is actually compatible with the nitrate, which biocide is actually showing the synergistic effect with the nitrate. And although in those experiments, we found out that the benzyl acrylonium chloride is a biocide. It is a non-oxidizing biocide, which can actually has a very good synergy with the nitrate. And so we have used the benzyl acrylonium chloride and the nitrate as a to control the soaring. So in the reservoir, so four treatment which we have used. One, we were just injecting the sulfate rich water in the columns to to establish the soaring in the field. In the second column, what we are injecting was just the benzyl acrylonium chloride to see whether benzyl acrylonium chloride is able to, or the back is able to control the soaring in those columns. In the third column, we were just injecting the nitrate to see that whether the nitrate is able to control the soaring in the oil field. And in the fourth, we were injecting both nitrate plus benzyl acrylonium chloride in the half concentrations to see whether it is able to control the soaring in the field. So I'm going to describe this is a whole setup which has been done in the lab. Right now, I will describe the results of this experiment. So you can see two graphs here. This is our column. The inlet of the column is down. So the sulfate rich water is injected from the down port, and this water moves and come out through the outlet. in the whole process, this work as an injection well, probably this inlet, and the outlet works as a production well. Okay, so when this sulfate rich water is injected, what we found out that all the sulfate is actually get reduced as soon as we start injecting the sulfate rich water, which means all the sulfate reducing communities, as soon as this sulfate is coming into this column, they are reducing all the sulfate at the injection port. So here when you see this graph, the lower one is of inlet, the red line shows the sulfate, and the green line shows the sulfide. So you can see that within 4 or 5 days all the sulfate has been reduced, and then sulfate was continuously reduced, and we can find the same concentration of 2 millimolar sulfide which is producing at the inlet in the sample. So when we took out the sample, this is a result of sampling which we did after, every day from these columns. When we talk about the outlet, at the outlet again there was no sulfate present, but the sulfide which was moving upside was also, we were also able to find some sulfide in the outlet port. So this shows that both inlet and outlet the sulfide is present, and all the sulfate which has been injected in the reservoir was reduced at the inlet port. When we did the same experiment, so this was like a control column. Okay, so in this sulfate, just we are injecting the sulfate rich injection water. This is the first treatment which was done with the Beck. So we use the concentration, the 1.5 millimolar concentration of the Beck biocide, and what we found out that at the inlet port, as soon as we injected the Beck on the 15th day, what we found out that the sulfate again revert back, which shows that the sulfate reducing bacteria which was growing at the inlet port is probably not has been killed by the biocide, because the biocide has obviously the biocide a function of killing the bacteria, and thus the sulfate was not reduced at the inlet port. However, when we talk about the outlet port, because this if the sulfate is not reducing here, it is moving upward, and all of this reservoir has a capability of reducing the sulfate, because sulfate reducing bacteria is present in the whole reservoir, right? So at the outlet port we didn't find any difference. At the outlet port the sulfite was produced again, there was a production of sulfite, which means the sulfate was reduced. So although this Beck was able to control the uh, you know um control the sulfide production at the inlet port, but not at the outlet port. And this is what happening in the oil fields. When the biocides are injected in the oil fields, probably as soon as you start with the biocide, you find a very good result, that because of as soon as you have injected the biocide, the bacteria present at the inlet port has all that bacteria has been killed, and suddenly you have a dip in the sulfide. But in the rest of the reservoir, which where also that sulfate can be reduced, it takes some time. There is a time lapse when these bacteria in the other part, in the deeper zones of the reservoir, are growing. It takes some time, and within that time, you know within that time we see that we see the dip in the sulfide concentration. But after some time again, the sulfate reducing bacteria started growing deeper in the reservoir, and we see that the sulfate is reduced and the sulfide is produced. So you understand this point here. What I want to say is that this is what generally happening in the oil field. Although oil fields are oil field personals, they are using number of biocide, but that is not like a permanent solution for the for controlling the sulfide, because as soon as you inject the biocide, it will stop the sulfate reduction, it will stop the sulfide production in the field, but after some time it will again revert back, and then you keep injecting the biocide, it is not going to change anything. When we just injected the nitrate without the without the biocide, what we found out, it was kind of a similar results. As soon as we start injecting the nitrate, the sulfate revert back at the inlet port, and sulfite was decreased. So we thought, okay, at the inlet port it is good, but at the outlet port the condition was same. There was no control of sulfite, which means deeper in the reservoir the sulfate get reduced. Okay, only in this part where the nitrate was coming first, the nitrate reducing bacteria are growing right here, controlling the sulfate reducing bacteria. But sulfate reducing bacteria has a whole reservoir. Deeper in the reservoir they can grow, and then they are able to and reduce the sulfate to sulfide. So this is same which was happening here, right? So after when we discussed these results with the keen personnel, they told us, why don't you do an experiment where you use both nitrate and sulfide together? And we did the same experiment. And what we found out is that when the 2 millimolar nitrate and 0.75 millimolar benzene eclorium chloride or the biocide was used, both at the inlet and the outlet port, the sulfide was decreased, and there was no sulfite which has been seen. Okay, and the sulfate, as such, the sulfate which is injected is coming out of the outlet port, which means in the whole reservoir, in the whole column, the sulfate was not reduced. And why this was happening, we try to see it, because we are, of course, we are injecting the two controlling agent, one is BEC and other is nitrate. But what we try to figure it out here is in this, this was a hypothesis, or this was a theory which we gave about this, that initially what happening is that the biocide which is going in the reservoir, it is killing up the nitrate reducing bacteria here, sorry, sulfate reducing bacteria here. And this is, and all the bacteria, even the nitrate reducing bacteria, because the biocide are not specific, they are both killing both nitrate reducing bacteria and the sulfate reducing bacteria. So all the biocide which is coming here is killing all that nitrate and sulfate reducing bacteria here in the, at the near to the inlet port, near to the injection well. And this helps the nitrate to go deeper in the reservoir, because all the microbial community has been, is controlled here by the biocide. This nitrate is moving deeper in the reservoir, and when this is moving deeper in the reservoir, probably it is able to control the sulfate reduction in the deeper zones of the reservoir. And this was a reason for getting the control when we are using the concentration, when we are using the two different controlling agent in the field. So this was a, when we showed this result, they told us to do it at a, in their, they want to repeat that in their laboratories with the core flooding. And we told, okay, this is fine with us, and probably we'll have that results very soon from them. But this is what this is what has been proposed right now for this, for the field to do this in their fields. See, this is happening because this oil field is a moderate temperature oil field. It is not a high temperature oil field. If it is a high temperature oil field, high temperature oil fields are generally sterile, which means there is a very less microbial activity in the high temperature oil field. So the only activity which is present in the high temperature oil field is near to the near injection wellbore region, because lot of cold water is generally injected in the reservoir. And when this cold water is injected, a zone near to the injection well start cooling there. When there is a cold zone near the injection well, the microbes can grow at that zone. And controlling them is very easy, because you just have to treat the near injection wellbore region. Rest of the reservoir is anyway sterile. But when we talk about the lower temperature oil fields or the moderately high temperature oil fields, the microbial activity is possible in the whole reservoir, deeper in the deeper zones also. And that's why it is very hard to control the soaring in the moderately temperature oil fields. In the high temperature oil fields, it's not a huge problem. Once you are able to control the sulfide production at the injection well, probably there will not be any activity in the deeper, because this whole reservoir is at a high temperature. All right, so this was a conclusion for this study, was that the treatment study used as combination of BEC and nitrate is able to control the soaring both at inlet and outlet port. with the from the Kane India, we have published this paper also for this. Now, the second thing which I want to describe is about the MEOR, microbial enhanced oil recovery. But before that, I would like you to tell me if you have any questions regarding this. I can answer those questions. You can write in the chat box, or you can just let me know, but by unmuting yourself. Any question? How to test the sulfur content in oil samples? Tests related to inorganic sulfur and organic sulfur. Sir, we have the protocols for doing that. Just share your email address. I'll let you know those tests to control the to measure the sulfur content. Sulfate can be done easily with the help of spectrophotometric test. Measuring sulfur is a bit tricky. If you are asking sulfate, how to measure the sulfate, it's a very standard test which is done by the oil industry also. It is a spectrophotometric turbidity based test. A protocol is there. We measure the turbidity at 420 nanometer and find out how much sulfur is there. So for the sulfide measurement of sulfide, it is again done by with the help of a spectrophotometric method, with the help of diamine method. And nitrate we for measuring the nitrate in the fields, we are using the HPL method, high performance liquid chromatography. And for the sulfur, we generally don't measure sulfur, we generally measure sulfate and sulfide, but we have the protocols for that. It is I if you share your email address, I can tell you. All right. Okay. So this was a question from Vijay sir. And all right, so sir, if there is no more question, I can go ahead with this. Ranjan sir.
Yeah, yeah. Please go ahead.
So microbial enhanced oil recovery. So as we have already discussed about, different types of about the different kind of recovery, chemical enhanced oil recovery, thermal enhanced oil recovery, and I am sure there are a number of chemical engineers which are present in this FDP, as well as the petroleum engineers. They know about the chemical enhanced oil recovery or the thermal recovery. So I'm not going into the details of those a lot, but let's discuss more about microbial enhanced oil recovery. So what does microbial enhanced oil recovery aims to? It aims to alter oil, water, rock interfacial properties, change flow behavior, so that the more oil can be taken out with the help of microbes, microbial products, or the nutrients which can be injected inside the reservoir. So that is known as microbial enhanced oil recovery. Okay, microbial enhanced oil recovery can be grouped in two categories: well stimulation and another is microbial enhanced water floods. So what is well stimulation? So well stimulation is a well intervention performed on an oil to increase the flow of hydrocarbon from a drainage area into a wellbore. So basically, when same production for injecting the microbes or the microbial compounds, and then close the well for some time, and then again start the production and see whether that oil has started producing more oil, that is known as well stimulation. So we are doing what we are doing, we are injecting the chemicals into the marginal well which is not producing any more oil. Okay, so we inject that those chemicals in the reservoir, in that we close that well for next 15 days or 30 days, and then after 30 days, when the production is again started, to see whether those chemicals, if there is more oil is produced, then we can say that those compounds which has been injected in the reservoir has done their job, and the oil recovery has started. Okay, so microwave enhanced oil well stimulation is also known as push pull technique, where you are initially pushing the compounds, and then we are waiting for some times. Okay, and to stimulate the production of large amount of acid gases, solvent, biosurfactants, bioemulsifiers in one well, and near the well region, to improve the oil production rates. So what we are doing, we are injecting the microbes or the microbial products or the chemicals which can be utilized by the indigenous microbes which are present in the reservoir, and if they can produce large amount of acids, gases and solvents or the biosurfactants which can which can help in the recoveries. Okay, and then so that is known as well stimulation. Okay, so this is same figure which is showing the well stimulation. Injected microbes and nutrients, metabolic activities are started in this region, and then the oil is produced from the same well. Second is microbial enhanced water flooding, where we are using another well for injecting the chemicals or the microbes or the micro product, and then so it is just like a water flooding, right? But the water which has been injected has the chemicals or the microbes or the can actually increase the oil production by producing some acids, gases or biosurfactants. There are number of chemicals which can be produced by the indigenous microbes, and when these chemicals are produced, they can increase the oil recovery. So they can reduce the capillary forces trapping the oil on rock, improve sweep efficiency by blocking the high permeable zones, and forcing fluids out of less permeable zones. So this is what uh, is a hypothesis which we generally give for microbial enhanced oil recovery, that we can plug some of the zones of the inside the reservoir where the high permeable zones, so the water will move from the zones which are less permeable, and when the water will change its path, it will come in contact with the oil which has not been come in contact before, and thus can produce the more oil. So this is about the microbial flooding. Okay, so the chemicals are injected, chemical and nutrient are injected. You can see the nutrient, and then the microorganisms are using those nutrients, and then microbial products are produced, and these microbial products which has been produced are forcing the oil out of the reservoir. So that is known as microbial enhanced oil recovery. Microbes, or what are product or activities of microbes useful for EOR? So one are, I already told you, acids. So microbial metabolism can produce acids like volatile fatty acids like acetate, propionate, and lactate, and they can be useful for removing the moving the oil towards the production well, or to increase the oil recovery. Then they can produce some solvents like the acetone, butanol, ethanol, and when these microbes are producing the solvent, this oil can be taken out, dissolve or swell any of the precipitated organic deposit, alter wettability, improve the mobility of the oil phase. Then they can produce some gases, and these gases can repressurize the reservoir and can produce more oil. Then they can produce biosurfactants. There's a product, they could produce biomass which can which can block the higher permeable zone so that the water can move to the lower permeable zone, which this is known as selective plugging. So plugging the zone from where the water is moving, so that the water has to find another way, and if this another way if the water is moving from another zone, it will come in the contact with the oil which has not uh, you you know uh, recovered earlier, and can be used, and the oil recovery can start. And then the biopolymer producing, and this biopolymers can increase the viscosity of the driving fluid, and thus can produce the more oil. So these are the different microbial activities. And then the biodegradation of the oil, some of the microbes can degrade some of that oil which is present in the reservoir, and can bring it to a more soluble state, so that it start moving more flowing state, so that it start flowing. So all of these are different products or different activities of the microbes which can be utilized for the enhanced oil recovery. So now I'm again going to discuss about the another field project which we got from the ONGC oil and ONGC and MHRD. I was talking about the project Imprint 2, which is a industrial project along with the ONGC as well as the academic partner is Ministry of Education. So both of them has given us this Imprint project to find out another technique which we describe as a biochemical enhanced oil recovery technology or a BECOR technology. So what does BECOR technology actually means? So polymer flooding, generally we know that the polymer flooding is we inject a polymer in the oil fields, and this polymer, what it can do, it can increase the viscosity of the driving fluid to move the more oil from the reservoir, because if the viscosity of the oil is increased, if the viscosity of the injection water is increased, that can move more oil from the reservoir towards the production well and can produce more oil. While the MUR, when we talk about the microbial enhanced oil recovery, we talk about the well stimulation. We have just talked about the number of activities which microbes can do in the reservoir. Okay, so can we have a technology which can have a characteristic of both microbial enhanced oil recovery and the chemical enhanced oil recovery? So with this idea, we have started working on the Ankleshwar oil fields. So the idea behind that was to find out or to develop a technology which can or to develop a single injection fluid which can work both as a chemical enhanced oil recovery and the microbial enhanced oil recovery. So you can see this as a initially there is a water flooding which is done. This is the initial oil. When the water flooding is done, you can see that in the B diagram of this slide, that the water has been injected and this water is moving through the reservoir. Okay, and the oil which is actually present in this continuum has been moved out. However, the oil which is present on the surface of the rock or the oil wet rock has not been moved. So the oil which has been adsorbed on the rocks is not moving with this water. The oil which was present in continuum has been moved. Okay, and the oil which has been trapped between the rocks has not been moved. Okay, so when we do the polymer flooding, what we do, we are able to move bit more of the oil because of the increased viscosity of the driving fluid, as well as the polymer also have uh, some other properties which can you know which can move the oil, increase the sweep efficiency of the driving fluid, and thus the more oil can be moved out. Still, we can see that the oil which has been adsorbed on the rock surface has not been moved. And then when we talk about the biochemical enhanced oil recovery, what we are doing is we are trying to mix two things. One is increasing the viscosity of the driving fluid by adding a polymer, and then the same polymer. Hello, hello, hello.
Yeah, yeah.
Is there any question?
No, no. Please go ahead.
All right. Okay. Yeah, yeah. All right. Yeah. So what this polymer is doing? If the polymer is doing a function of a polymer, which is increasing the viscosity of the driving fluid and moving the oil from the reservoir. Second thing, what it is, if this polymer the polymer which we want the polymer to do is to do the wettability alteration. So if that oil wet rock to a water wet rock. So wettability alteration, if this polymer has a capability of same as surfactant, probably it can uh, uh, convert the oil wet rock to a water wet rock, and thus the more oil can be uh, can from the reservoir. So this was rationale behind this biochemical enhanced oil recovery. So the polymer, for this, what we have to do was we have selected number of polymers. I'm showing the results of here like a 6 polymers here. No, sorry, 8 polymers here. But we have actually screened
So again, the voices are coming.
Not audible.
Hello, am I audible now?
Yes, sir.
All right. Okay. Okay, sir. So let me know if this video is audible.
Yeah.
On average, only 35% of oil is recovered from the ground later and treated behind. With demand for energy increasing by more than 30% by 2035, the world needs to produce more oil more efficiently from existing resources. We appear to have reached the point globally when the potential for enhanced recovery from existing resources exceeds the potential from new discovery. EOR creates opportunities for lower cost production with less environmental impact. This work relates to the development of wet water formulation for biochemical enhanced oil recovery technology.
Under the product which we have developed at EER level, it has two characters. One is viscosity enhancement and another is wettability elevation. So when this product is injected downward in the reservoir, it can increase the viscosity of the driving fluid and can alter the wettability of the rock from oil wet to water. And both of these characters will increase the oil recovery by almost 5%, which will cost actually millions of barrels of oil. We are targeting this project specifically for the Indian oil industry of northeastern oil fields and the ONGC sector. Development of vessel formation is sponsored by Infinity project of DibrU, DBT, as well as it is funded by industries like Oil India Limited and OTVL or ONGC Daily Biotech Limited.
During the initial studies, the wet water rheological characteristics were evaluated and compared with commercial polymers to assess its potential for EOR. For the rheological studies, the viscosity of solver solutions dispersed in artificial dry medium were evaluated at different temperature ranges. It was observed that the viscosity of wet water formulation was much more stable at 30 degrees C and further increased with increasing temperature at 65 degrees C, while the commercial polymers showed reduction in the intrinsic viscosity value with increasing incubation time. To find out whether the wet water formulation and the commercial polymers have the ability to form emulsions with oil and water, the emulsifying properties were therefore evaluated. On evaluating the emulsion stability, it was found that the wet water formulation formed stable emulsions at higher temperature, wide range of pH, and changing salinity conditions, as well as it had a higher storage stability than other commercial polymers. Reservoir rocks are oil wet in nature, and a greater percentage of oil is left unrecovered owing to this property. Therefore, wettability alteration potential was evaluated for different polymer solutions. While conducting the qualitative wettability test, it was found that the wet water formulation was showing positive results for flotation and two-phase separation studies. Contact angle measurement was also conducted as a part of standard test for evaluating the wettability alteration. It was found that the contact angle of wet water formulation was able to alter oil wet character of reservoir rock to typical water wet behavior. This result was comparable to that of a surfactant, Triton X100, which was taken as control. The FTI results confirmed that the wet water formulation removed crude oil components from the rock surface, as well as the weight loss of absorbed materials on the rock surface was monitored by thermogravimetric analysis, which also confirmed the removal of crude oil and low retention of wet water on the surface of reservoir rocks. While the standard parameters for evaluating the predicted that wet water formulation formulation. Under the oil reservoir simulating conditions, the bioreactor were flooded with wet water formulation with standard conditions. The flooding study showed that the novel wet water formulation was able to increase the recovery of residual oil from the bioreactors more than the existing commercial polymers.
This wet water solution contains a polymer that enhances the mobility ratio of the injection fluid such that its efficiency is enhanced and amount of residual oil is recovered from the oil fields.
Currently, the wet water pre-flooding evaluation has been completed. The logistics and feasibility of field trials are designed as funded by Imprint's project, and
All right. So this was just a brief summary of the work which we have done for the imprint project. So as in the presentation also it was mentioned that initially we the novel polymer which was known as wet alter in this video. Okay, so when we check the viscosity of this uh, polymer at different temperatures, 60 degree, 50 degree, and the 30 degree, 50 degree, and the 65 degree, what we found out that in the brine solutions, the the viscosity of this polymer was actually was has been not able to hear. Now is it okay? All right.
Yeah, now it's okay.
Yeah. Okay, sir. Yeah. So so these are the different each set of graphs shows up for one particular polymer. So first one is xanthan gum, second is PHPA, third is HEC, fourth is CMC, fifth is trachagant gum, sixth is gum arabica, and seventh one was our galactomannan polymer. Right. So these are the different polymers which we have used. Okay, and this different colors shows the viscosity at different temperature, right from 30 minutes to sorry different time, right from 30 minutes to 180 minutes. So what we found out that this the galactomannan polymer which we are actually trying, which was asked us to check, what we found out that this polymer has a very good viscosity characteristic, and even it increased at the higher temperature, a bit increased, and it was very stable. However, when we talk about the xanthan gum and PHPA, the viscosity was although the viscosity was very higher in the distilled water, but as soon as it comes to the brine, the viscosity, they have lost their viscosity. Okay, so that was a problem with the xanthan gum and PHPA. If you check the viscosity in just in distilled water, they show a very huge, very good viscosity. But as soon as you put it in them in the brine, the viscosity was lost. And that is the problem, probably the reason that we have to check all those viscosity experiment in the real, oil field waters. Okay, so this was this shows that the polymer which we want to use has a good viscosity characteristic. Now we started moving towards to see that wettability alteration characteristic of this polymer. So when we have to check the wettability alteration characteristic, we also need the rocks, reservoir rocks. So the reservoir rocks were taken from the one of the sandstone and the carbonate. Sorry, one of the sandstone reservoir and the carbonate reservoir. These rocks were cut into a very small pieces, and when after putting them in the pieces, this is a very standard protocol. We initially they were dipped in the brine for few days so that these get becomes a water wet, and then they were put in the oil for a very longer duration at the 70 degrees centigrade, so that these all of these rock will become oil saturated rocks or the oil wet rocks. So these all are, you can see in the next figure D, which these are the oil wet rocks. Once these rocks are becomes the oil wet, we have put them in the different polymer solutions and did all the different experiments which we need to do. Okay, as well as what we have done is we have uh, we have crushed these rocks. So the rock which is initially the water wet rock and the rock which is actually the oil wet rock, both of them, these rocks were crushed also for the sandstone and the calcite to do the flotation test. Okay, so these oil wet rocks, when we do the FTR analysis for these different rocks, here I am showing the result of calcite rock. So you can see the FTR, different peaks of FTR for the calcite rock. Okay, when we and the and the FTIR peaks for the crude oil. When we did the FTIR for the same powder which has been for the oil wet calcite, we found that the peaks of both crude oil as well as the calcite were shown in this middle graph. So which shows that the oil has been actually absorbed on the rock surface. So we know we were able to show that the oil has been absorbed in the rock surface very well, and then we started our further experiment. The first experiment which was done was a contact angle measurement. So contact angle is, if the oil is water is if the oil sorry if the rock is water wet, then the angle which it will make is a acute angle. The water droplet will make a acute angle. However, if the rock is oil wet, the water droplet will make a obtuse angle. So the contact angle was measured for the initially for the control, just where the rock was water wet, where the rock was oil wet, and we see the angle was 102 degrees, 102 degree. Okay, and when it is done, when it is checked for the different polymers, what we found out that the galactomannan polymer which we are using was able to decrease the angle to 281 degree, which shows that it has made the obtuse angle to a acute angle. Means the wettability of the rock has been changed by this polymer, and this was the first idea which we got, that this polymer has a surfactant property. Okay, and then we try to see in the literature also whether anything is known for this polymer as a surfactant property. We couldn't find anything, and the probable reason is nobody has analyzed it. It is not like that we have discovered a we have actually invented a new property. No, that this property actually lies in the polymer, but it has never been tested. So this was the first time when this polymer was tested for a wettability alteration or a surfactant behavior. Okay, so this again give us an idea that this polymer will be able to work as a wettability alteration polymer also, so that probably it can remove the more oil from the reservoir. Then there were other tests which was also done. This was for the sandstone. I'll probably rush through the results, as probably have 10 more minutes to go. And then the interfacial tension was also checked, and we see that the interfacial tension of the um, uh, was was much lower by the novel polymer which we are using, galactomannan polymer, than the other polymers which has been used. Flotation test. So this is more interesting test which we need to see in this diagram. When you see that the calcite rock, when the rock, the powder not floating. However, when the rock powder, which was oil wet powder, was put it into the brine, this was floating on the brine. So this shows the nature that it is a oil wet rock, because oil floats on the water, and that's why this rock particles were floating on this water. This is a very standard test, flotation test, which is used by the oil industry. Okay, similar thing was done for the sandstone sample also. When we added the polymer solution to these brines, what we found out that the galactomannan polymer was able to convert that oil wet rock, rock, to a water wet wine, because this rock has been suspended. As soon as the polymer was added, this the rock powder was get suspended into the tubes. This shows that the oil which was actually on the rock powder has been removed by the polymer, and thus that powder has been settled into the tubes. This when I talk about the other polymers, I've shown it here for the other four polymers. None of these polymers has this property, a flotation test. So this flotation test we did it by ourselves, and then we send out the samples to one of the companies in the United States known as Engineer Salinity. They also did the same test, and they confirmed our result that this polymer has a property of changing the wettability. This was a two-phase separation, same kind of test, but done in the two different phases, hexadecane and brine, and same results we got for the polymer, that the polymer, galactomannan polymer, was able to from oil wet to water wet. which make the small droplet and can have a for a long duration. Qualified higher wettability alteration characteristic, and probably it has a good characteristic of both to increase the viscosity of the driving fluid as well as to remove the adsorbed rock oil from the rock surfaces. With this, we have done the laboratory trial with the same kind of columns which we use for most of our experiment. And what we found out, I'm not going to explain this setup right now here. And what we found out that the additional recovery which we got from this polymer is 9.47 of original oil in place, and the 16% of the residual oil in place, which is higher than the other polymers. So this also give us a confidence that this polymer has a good property of converting the good property of enhanced oil recovery to good potential of enhanced oil recovery. We have also done the microbial community analysis for these columns to see whether which microbial communities are growing here and how they are able to probably add up to the microbial enhanced oil recovery. But probably due to a shortage of time, I'll just leave it here and keep the next 7 minutes for the discussion. So, the conclusion for this work was to uh, the conclusion for this work was to see that whether the novel polymer which has been used has both wettability alteration characteristic as well as the viscosity enhancing characteristic, and thus was able to can be used as a single injection fluid to increase the oil recovery from the reservoirs. Thank you very much. So this is our team which we are working with, and a lot of new people has come. There are some old faces also in this slide, but yeah. Thank you very much for your kind attention. And I'm ready for the questions if you want to ask anything.
Thank you, sir. Thank you for the nice
Ranjan sir.
presentation. Yeah,
Yes, sir.
thank you.
Yeah, sir.
So any query from the participants? You can type
So
in the
I'm not
chat
sure
box.
if, uh, yeah, you can type in the chat box if there is any question, or I can I can put my email address, sir. If there is any question and people want to ask, I will be able to answer that on the email. And I'm not sure if people are able to understand what I was if I am I able to convey about the microbial enhanced oil recovery or the petroleum microbiology to the faculties. Any feedback on the presentation?
I'll send you the feedback later. But if anyone has anything to say about first lecture, a very good question. So people like your lecture.
Anyway, thank you, sir. I guess you have to go for the next session, right? In the
Yeah,
5 minutes, probably.
I'll give the end remarks. So on behalf of everyone present in this program, I want to thank Dr. Akhil Agarwal sir for his informative and enlightening presentation on the different aspects of production related to petroleum microbiology. We appreciate the time you took out of your busy schedule and for sharing with us your knowledge and expertise. I'm sure everyone liked your presentation. It was very lucid, very easy to understand. Thank you very much, sir. So once again from
Thank you, sir.
the organizers, thank you, sir.
Thank you, sir. Thank you very much.
So we are going to start the next session, the fifth session of this FDP after some time at 2:30 probably, because one of the resource person he had requested for fixing the presentation because some other works are there. So the resource person for this session will be Dr. Manish Kumar of All India Limited. So he will be speaking on the water injection, subject of water injection.
Dr. Ranjan, can I share my screen? You can make me the presenter.
So I've made you the presenter. You can share screen.
Okay, okay. So is my screen visible to everyone?
Yeah, yeah.
Okay, let me.
So I'm very pleased to welcome our resource person, Dr. Manish Kumar of All India Limited. He will be speaking on the very important topic of upstream petroleum sector, the water injection. Dr. Manish Kumar is currently working as DGM Reservoir, Subsurface Manager, Eastern Asset, Oil India Limited, Dibrugarh. He did his BTech from the Department of Petroleum Engineering from Indian School of Mines, IIT, Dhanbad in the year 2003, and PhD from the University of Petroleum and Energy Studies in the year 2019. He has published several research papers in national and international journals and conferences. His research interests are enhanced recovery, field development planning, well testing, and reservoir simulation. So please join me in welcoming Dr. Manish Kumar. Over to you, Dr. Kumar.
Yeah, thank you, Dr. Fogan, for the introduction. So today I will be talking on the topic water injection. I request listeners to mute themselves. I think there is some issue in the some. It is reiterating. So the outline of the presentation starts from the stage of recovery, and it will go from water injection till move to water flooding, and what are the factors that are important for water flooding, what are the patterns, followed by water flood screening, sources of water quality, effectiveness, and lastly conclusion. So in this slide you can see there are several barrels which have been placed. The first barrel that is in place is represents basically while in place, and you can see a number is represented there, 366 mmSTP. And in primary recovery, that the 25% recovery is obtained, that is equivalent to 90 million barrels. And if you go for secondary recovery, it is equivalent to 155. And if you go for tertiary recovery, it goes to as high as 235. The same thing has been represented on the diagram below in a field while rate versus time. So today we will be talking on the secondary recovery technique, and the one of the technique of the secondary recovery is water injection. Although gas injection is also a technique for secondary recovery, but we will talk mainly on the water injection part today. So now we need to define what is water injection. Basically, it is a secondary process by virtue of which we try to increase the production from oil reservoirs. So I want to bring your attention to the bottom graph, where you can see there is a graph where representing on y-axis it is reservoir pressure, on x-axis it is time. and you can see the line, the orange line, orange solid line. It is representing the decline in the reservoir pressure, and there is a blue line which indicates that this is a point where we are initiating the water injection. So what I mean to tell, if we try to produce oil and water and gas from a particular reservoir, this reservoir pressure depletes, but we need to know when we should start the water injection. So the mainly two factors are important in this aspect. The first is the pressure should be greater than hydrostatic pressure, and it should be greater than bubble point pressure. For the knowledge of house, I will just reiterate the definition of bubble point pressure. It is the maximum pressure at which the first bubble comes out of the solution and goes out. So we should avoid the reservoir pressure to reach bubble point pressure, and start initiating a water injection before the bubble point pressure. And at the same time, the pressure should be greater than hydrostatic. Let's take an example of a well which has a depth of around 3000 meters. So if you calculate the hydrostatic pressure, the gradient is 0.1 ksc per meter. So that way the hydrostatic pressure will be 300 ksc. The reason why I am pointing towards hydrostatic pressure is, if your reservoir pressure is not greater than 300 ksc, it will not be able to lift the amount of water that is being produced. So these are the two important factors. The first one is the hydrostatic pressure, and the second one is the bubble point pressure. These are the two important things that is required for the initiation of the water injection. And the purpose which is being served by the water injection is voidage replenishment. So injection of water to maintain the reservoir pressure and displacement of oil by water from the pore spaces is basically accomplished by water injection. Now I am a little bit deviating from the topic of water injection and trying to define a term from EUR, that is low salinity water injection. This is the same thing you might have heard several times about this term low salinity water injection. This is nothing but generally the water we are injecting into the reservoir is from the produced water. If you are taking water from your water table or from river, the salinity is low. So to quantify the salinity, I can take an example of your drinking water. Generally, the salinity of drinking water is less than 100 ppm, or it may go as high as 200 ppm. So if you are injecting this low salinity water injection, it acts both the purposes. It replenishes the voidage replenishment, increases the reservoir pressure, and at the same time it also acts as a EUR. There is a mechanism for LSWI, which I am not going to deal in detail, but just to brief it, it reduces the residual bisaturation basically, which is the primary target of any EUR, and it can be quantified. So in Oil India Limited, we have tried to quantify it, and we have seen that the residual well saturation has gone down to a level of 5.9, and that is approximately 6%. So this was a glimpse of what is low salinity water injection, what it does. And on right hand side, you can see a table which is depicting different EUR methods. So this, you can see that low salinity water injection is a designated EUR technique, and it, as per EUR policy that has been given by Directorate General of Hydrocarbons in year 2018, that has been just given in a blue line. You can see it. So that's way water injection is serving both the purposes of pressure maintenance as well as EUR. So I have shown you the low salinity water injection. I will be giving you some field examples also in the end of the presentation. I have got two examples of two different fields where you can see how it has impacted. Now, as I have already told that we need to do water injection, and there is a criteria for doing water injection. The first criteria was the pressure should be greater than bubble point pressure, and it should be greater than hydrostatic pressure. But why should we inject water? The primary objective is to maintain reservoir pressure, that is the pressure maintenance, and the second is the supplement natural water influx. So as you know, if you don't inject water in any of the reservoirs, even though there is some amount of water that is being produced, while alone is not produced, water also comes. But the water which comes without water injection is basically coming from the natural water influx. It is the energy of the reservoir which comes of its own by supplementation of natural water influx. So these three things, like maintaining reservoir pressure, increasing reservoir pressure, and supplementing natural water influx, these three things are a requirement of any water injection. Now there is a potential of water flood. So if you can see in the middle of the column, you can see the primary recovery ranges. You can see in water drive, the bottom row, you can see water drive that has got the maximum recovery factor. It ranges from 35 to 50%. So I was talking about the natural water influx. You can see if there is a natural water influx in the form of a water drive, the recovery can go as high as 50%. And as you go on reducing the drives, like if you go only in the fluid expansion drive, you can expect a recovery of 3 to 10%. But generally in any of the reservoir, there is a combination drive. Gas cap is also present somewhere water is present, and somewhere gravity also plays a role. So definitely the primary recovery that we obtain is a combination of all this, and we get a mixed kind of recovery. So you can see there is a potential for water flooding, where we can do water flooding. The solution gas drive reservoir is a potential for water flooding. It's a good, and also in your fluid expansion drive, both are ideal candidate for doing water flooding, or let's say water injection. In water drive reservoir, since there is a natural energy influx and the water comes of its own, so there is not much requirement. But in solution gas drive, definitely there is a requirement of pressure supplementation, and it's a good candidate. Now to illustrate more on this, I have given an example. So in this graph you can see there are primary vial and the secondary vial. The primary vial is shaded in the texture part, and the secondary vial is given another shade. So you can see the secondary vial that has been obtained mainly by doing some supplementation of pressure. It can either be through water injection or it can be through gas injection. And you can see the different periods, like when we have started the injection. So the number A, you can see an alphabet A, this is the initial fill-up period. So to give more illustration on initial fill-up period, let's suppose you have got a reservoir from where you have started the production for 5 years. So there is some void that has been created, and you have not started your water injection from day one. So definitely there will be some gap that has been created in the reservoir in form of porous spaces by production of oil, water, and gas. And you can see there is a decline in pressure. So if there would not have been any decline in pressure, so this initial fill up should have been done by natural energy. But now you can see that the reservoir pressure is declining, and the injection has been started by the first dotted line. So if you see the part A is the initial fill up period, and after that there is an increase in the production by secondary vial. So you can see clearly by implementation of secondary recovery technique, that is water injection, there is a gain in vial production. So this is a typical representation of by a particular reservoir where you have initiated water injection after a certain point of time, and then the reservoir responds and there is an increase in production. So just try to look into the future where what might happen if you are having a depletion drive reservoir and your water drive is not that much strong. So in the top figure you can see the initial oil water contact and the wells have been drilled, there is no production. But after some time you can see the oil water contact has moved up, and you can see the representation on the right hand side that oil rate has declined, water cut has gone up, and GOR is flat basically. So this is only because there are two drive mechanisms that is acting on it. The first is a gravity drive mechanism because it's a dipping reservoir, and the second thing is there is a natural water influx by virtue of which this water is encroaching towards the perforation of the bottommost producer wells. The second instance you can see in the edge water and the bottom water, basal water or bottom water basically. So if you can see in edge basically, edge water drive reservoir, the one end is blocked basically. One end is blocked, but in the bottom water drive reservoir, you can drill in any of the wells. You can even convert the producer well to an injector well, but that facility is not available in edge water. Let's suppose if you want to convert this, if I can get an option to draw, if you want to convert this particular well into an water injection well, that is not possible. But in bottom water drive reservoir there is a flexibility. So this well can be converted to water injection well, but this well cannot be converted. So in edge water drive reservoir there are typical characteristics. This well will be watered out on a very first instance because water will be encroaching in this direction, followed by this, and lastly this. So this well will be this particular well will be giving almost clean while what I can say to a maximum production history. But these wells, this particular well will be watered out very soon, and this will be following in the similar sequence. So let me know if there are questions in between. I can take the question in between. Otherwise, I have dedicated a different time slot for taking the questions from all the attendees. So you can interrupt whenever you want to do so. Okay, I have to erase it. So now we'll see how does a water flood work basically. So as I have told in the previous slides, some wells are converted to water injection wells, and I've already told that there is a flexibility of conversion of production water to injection wells in bottom water drive reservoir, but that flexibility is not present in edge water drive reservoir. So other oil wells remain as producer, and the injector water displaces or pushes oil to the producer wells. This is a concept of basically water flood. So if I can show you, if you can see this particular diagram, I am talking about this particular diagram. So you can see how this water injection, all the wells like these are basically water injection wells, water flooding wells basically, these wells, and these wells are producers. So you can see how this water has been injected in a while pool, and water is expanding, and it is trying to push the oil towards the producer well, and it is getting produced. So water flood is acting in two ways basically. It is increasing the reservoir pressure, as well as it is trying to make a push of this particular oil. This is oil basically. This is pushing into the producer wells. And the second, if I take a cross section of this particular image, I can point out on this image where you can see this is the injector well and this is the producer well, and this is the vial column. Basically, you are injecting water in a vial column, and this is how water is moving, and it is trying to push this vial towards the producer well, and it is getting produced at the surface. So there is a slight difference between water flooding and water injection, and I think this is the right slide to illustrate the same thing. You can see that in water flood you are injecting water in vial column, but if you see this particular injection in this particular well, this is the color that is marked in blue. This is basically represents nothing but water, and this black part is vial. So you are injecting in the water column only, and this is vial. This black portion is vial basically. So you are doing a pressure maintenance, and simultaneously there is still some layers. The layers can be in these directions also. If the layer is like this, if I try to draw the layers based upon the bottom layers, the water will try to follow this path. And if you can see, it is trying to do flooding mechanism is also being applied. Even though you are doing water injection, but some kind of flooding is also being applied, because water will not move horizontally. It will try to move in a particular layer. And according to the depositional environment principle, this layer will not be this layer has been deposited at a particular angle. So this is the particular strata that it is following basically. So this will the preferential movement of water will be definitely in this direction. So interchangeably, I will be using the term water injection and water flooding, since if you have got a horizontal bedding plane, which is being explained in this particular image, then water injection will do only pressure maintenance job. But if there is a dipping plane, the water injection will act as a water flooding. So I think I am able to explain the term water injection and water flooding, which is very important. And let me know if you have some questions on this. Now, there are various reservoir factors to consider for a pressure maintenance or water flood. The first thing is reservoir geometry. What is the geometry of the reservoir? And lithology. What is the porosity, permeability, all those things, and the fluid properties and relative permeability relationship, and lastly the pressure performance. So we will try to go one by one for each particular factor in detail. The first thing is reservoir geometry. Reservoir geometry is nothing but it's a structure or stratigraphy that controls the location of the wells and to a larger extent dictates the method for producing a particular reservoir. So reservoir geometry, if I try to depict in a detail, I have to go to the previous slide. So you can just consider this you can take this cross section and if you can see the bedding planes. This is almost following the top of the structure basically, and this is the injector, and then this is the producer. So there is no dip basically, and even if there is a dip, it's a very gentle one. And there are different kind of structures. I think you all might be knowing, like anticlines. This is the typical anticline. Like syncline is also there. Some faulted structure is also present. Like suppose you have a dipping structure and a fault can cut it through. So this particular part might go this might go in the upward direction and this go in a downward direction. So it will definitely impact. So by virtue of reservoir architecture, I mean to say there can be different architecture of the reservoirs. It can be anticline, it can be syncline, it can be a faulted reservoir, and it will also deal with the fault. What is the throw of the fault? Throw of the fault means, if I try to illustrate in more detail, we'll just draw. Let's suppose there is a fault, and the thickness of this particular bed is around, let's suppose, 10 meters, and this particular part is around 2 meters approximately, and let's suppose this is also 10 meters. Now just think of what are the chances of this particular wire in communication with this particular part. If these two parts are not separated by a particular, this is not a cell, if there is not a cell barrier, then this particular wire will be in communication with this, even though there is a throw of 2 meters which is separating it. So this wire will be in communication with this one. So all the things like your structure, like anticline, syncline, deep of the bed, fault, the presence of impermeable layer over the faulted layers, all these come in the reservoir architecture. Let's try to keep an water injection well. If I am keeping an injector well in this particular zone and trying to inject it. So if this is in communication, then the pressure will try to migrate, or let's suppose this while will be migrating in this direction. You are trying to push it from this direction, this will migrate in this particular direction. So this should be in isolation. So reservoir architecture is very much important, and to know the reservoir architecture, the best thing is you should take the help of seismic, whether there is a fault pattern which can be seen or not. And if you have seen the structure contour map, it clearly depicts what is the how much is the isoplate thickness, how deep it is, whether a throw is present or not. So all these things are present in a structure contour map. Now coming to the lithology. So lithology, basically it depends on there are three terms which are very much important. First thing is porosity, second thing is permeability, and the third thing is clay content. Porosity, by definition, everyone knows porosity is nothing but porous space that is available in the between the grains, and the permeability is the ability of fluid to pass through it, and the clay content is nothing but the silt percentage that is present. So all these parameters like porosity, permeability, and clay content, all these things can be measured directly or indirectly. You can measure porosity, permeability, and clay content in a laboratory. If lab data is not available, you can take help of logs, well logs. There are some logs which can measure permeability, but the porosity and the clay content can be measured by your, let's say the most simplest of log is, in earlier time it was SP, and currently it is gamma ray. So by using gamma ray log, you can estimate porosity and clay content, and permeability you can estimate by a porosity permeability transform. But if you don't have some sonic logs available with you, so porosity is directly relates to the total oil recovery from a reservoir, and the reservoir of permeability controls to a larger degree the water injection that can be sustained for a specific sand phase pressure. So if there is no interconnectivity, let's try to give you an example. Let's say this is a reservoir, and I am keeping this is an injector, and this is a producer. I am trying to inject by this particular area. There are several layers present. And if you see that the layer in which I am injecting has got a, you can measure all the properties on this wheel scale only, at this scale and this scale. But what about the heterogeneity between this injector and producer? You are not knowing. So the estimate of porosity and permeability is generally done on a stochastic basis, and you are trying to estimate what might be the porosity or permeability between these injectors and producer. So you are trying to inject in this particular zone, considering this is your base zone, very clean, and the water should go through. But what might there might be some small barriers. The percentage of cell has increased. This is, let's say, suppose this is cell. It will not allow to move the fluid to pass through it. Rather than fluid will try to move and choose this direction or choose this direction basically. So basically, permeability can be measured on a well scale, but the interwell connectivity is very much important, which is not known to us, and this is totally on the stochastic measurement. And what is happening inside the reservoir is least known if we are trying to just inject in a particular formation and we are not seeing in the producer. So the interconnected permeability is very much important from the point of view of injectivity. And porosity is the parameter which is important from the point of view of basically in place recovery factor and high withdrawals. But the permeability is the main important element, and permeability deals with the clay content also. If it is the reservoir is having a very less clay content, then the permeability will definitely be reduced, and it is a very if the clay content goes on the higher side, the permeability will be decreased and vice versa. Now coming to the fluid properties. So there is one very important parameter, that is mobility ratio. The mobility ratio is nothing but mobility of the displacing fluid to that of the displaced fluid, and ideally it should be less than 1. So what might happen, just give me a minute, I will draw again the same thing. This is an injector and this is a producer basically. What might happen if I am injecting from this particular zone and the mobility is greater than 1? So what might happen? This particular water, this is, let's suppose this is in wild zone and this is water zone. So what might happen? Water will create a channel of its own and try to reach this particular part. Again in this particular part. So it will not try to make a piston-like impact. So if mobility is less than 1, this particular this particular partition, this will move uniformly at time t is equal to 0. Let's if this position is here, so at time t is equal to t1, the position will be here like this. So there will be piston like displacement if this mobility is less than 1, and if it is greater than 1, definitely this injection water will be break through in the producer well very soon. So this is the definition, and if I can write, mobility is equal to permeability divided by viscosity. So this is the k by mu of the displacing fluid. This will be for water, and divided by k by mu of oil. So it should be less than 1 basically. Now the another factor that affects the mobility ratio is the relative mobility of the reservoir of to the displacing and displaced fluid. So these are the two important terms which are important from the point of view of water injection. Now coming to the pressure performance. Now the reservoir pressure in the water plant should be held higher than the saturation pressure to maintain the pressure close to the initial pressure. Now, if I have dealt in detail on a very first slide where I have told that reservoir pressure should be greater than saturation pressure as well as the hydrostatic pressure. And now I am trying to tell that this should be pressure should be close to saturation pressure to maintain the pressure close to the initial pressure. So the term the saturation pressure is very much important. And the initial pressure is the pressure when we have drilled the well and tried to take the static bottom hole pressure or take a pressure build-up survey. So our main objective from a layman's point of view will be that they should be meeting two objectives. The initial pressure is known to each and everyone. In absence of any PBT properties that is being taken on a oil and gas sample, we can know that this particular pressure, the saturation pressure, that is also known as the bubble point pressure. But if it is not known, you should keep in mind that the initial pressure should not be declining much. If it is declining much, definitely the lifting capability of the reservoir by virtue of its own energy will be reducing. And if I just need to mention one more point, suppose this is a well and this is a wellhead basically. So it is not always possible to take a static pressure, that is PS or as BHP you can tell. But on the wellhead you can take tubing head pressure. It is very easily available. So it is very imperative to see whether your THP is declining or not. So if your THP is constant and your production rate is also constant, then there is no worries. But if your THP is declining, then you need to measure this static bottom hole pressure. And if you're not able to measure, then you should do some correlations. You can take THP and you can use some correlation, the vertically flow correlations, and try to add and reach up to this particular point. You can estimate this PWF and have some estimation. So this pressure is very seems like it's a very easy task to measure the pressure, but their implications are much. Going off the context, let me give some more information on the tubing head pressure, what it might represent. So you might have heard about the Christmas tree and the blowout preventer that is being being kept on top of any wellhead basically. So every wellhead or BOP or Christmas tree has got a certain rating. So if your tubing head pressure is very high, let's suppose it's in the range of 5,000 psiz. So you need to be a little bit cautious, because in while India Limited, what we adopt is we have got two different kind of wellheads, and the one is of the rating of one wellhead is around 5,000 psiz and the other is 10,000 psiz. So if your tubing head pressure the suggests that the pressure is close to, you need to replace this. Otherwise, the well is unsafe. So this is out of context basically, but this thing I have noticed quite often. And if your tubing pressure is high on the higher side, definitely you have to do a workover, kill the well, and after that only you can replace this your wellhead. So I just want you to concentrate on this, is how significant it can be. Just looking at a particular valve or gauze, you can take a major decision in a well operations and do some prevent some unsafe practices. So apart from the sustaining the pressure to saturation pressure, to bubble point pressure or initial pressure or hydrostatic pressure, there are other factors also, like oil price. So right now, I think many of you are looking at the soaring oil prices, and it is right now at a level of around $128 per barrel or $130 per barrel. I think it's the highest oil price since last 7 to 8 years, as I remember, the marketing conditions, operating expenses, the availability of water. The water availability is also a major issue. So from where you can get water? In most of the oil fields, the produced water is treated, cleaned, and then it is made available for water injection. Legal considerations are also there, such as minimum spacing and adjacent leases, basically pattern selections and process considerations such as injection rate, response time. So let me give you some more time on injection rates, basically. What might happen if you are injecting at a very high rate? What might happen, and how you can determine whether a fracture has happened or not? So there is a plot called Hall plot, by virtue of which you can tell that whether this water that is being injected into the a particular well is not fracturing the reservoir. So injection rate is also very important. Response time. You are injecting in a particular injector well, and the producer well is around 200 to 300 meters away from this, and you can see what is the ideal time that there should be a change in salinity. So let me draw a figure again and give some illustration. This is injector and this is producer. So you are injecting in this particular well, and you are trying to produce from this well. How you will come to know that the water that you have injected has reached this producer or not? Because see, either you can use tracers, or if the tracer is not available, you can measure the salinity of this particular water. Let's suppose the salinity of the produced water injectors is around 500 ppm. And in producer water, the salinity is around 4000 ppm. So the day you are seeing that this 4000 ppm that is obtained from the produced water is reducing in a particular trend, or the water cut of this particular producer well is increasing, you may get some indication. Second thing is if the reservoir, the pressure, the flowing pressure, the PWF has increased. It might also give you some indication, basically. So these are the some indications of seeing the interconnectivity between injector and the producer. You can look at the salinity, water cut, wellbore flowing pressure. So now coming to the flooding pattern, basically, there are several flooding patterns that are being adopted in the industry. That is ideal. Although before showing the flooding patterns, I must tell you that these patterns are textbook examples, and in actual field practices, it is tried that this pattern should be followed, but it is not. In most of the times, this pattern is not being followed, because suppose I am showing you an example of line drive, basically. So you can see all the bottom part. This is the producer, basically. It represents the producer wells. This is the producer category, and this is the injector category, basically. So when you have drilled this and this, when you have drilled all these wells, ideally these wells have been producer, and at one point of time you are converting this producer to injectors. It might not happen this the same well this particular might be available for injection, or it might happen there might be some downhole communication, or the well has some fish inside the hole, or there is some well integrity issue. So in line drive, basically for each producer, just behind it there is an injector. Basically it's in the same line. That's why we call it line drive. It's in the same line. Now coming to the staggered line drive, it's just the name, as the name suggests. You can assume that for two producers you have got one injector basically. For these two producers you have got injectors. So there is a staggered basically. Now this is the flooding pattern, flooding for 5-spot pattern. So you can see there is a producer in the center. There is a producer in the center. There is a producer in the center, and you are injecting from 4 different corners. So you can see it's a perfect orthogonal shape. It is a perfect orthogonal shape. But ideally, the placement of well, either producer or injector, it can only happen in such a ideal condition if your reservoir is non-heterogeneous and layer cake perfect reservoir where you can place your wells. But it might not happen that way. So definitely, if this producer is at this particular position, the producer can be somewhere here, depending upon the structure contour, structural position, its pay thickness, your oil saturation, and the log signatures. So depends basically. So even though this is the 5-spot pattern, and there is another pattern which is the same name, but it is called inverted. It has not been shown. So inverted 5-spot pattern, you can just reverse it. In the center, you will be having injector, and in all 4 corners, this will be injector, and this will be producer basically. So just the inverse of 5-spot flooding pattern. Now same thing is being replicated here. Here you can see 7-spot flooding pattern. You can see 1, 2, 3, 4, 5, 6. 6 producers are there and 1 injector is there. So it's a 7-spot flooding pattern. Again, the 9-spot flooding pattern. You can see 8 producers and 1 injector. Now, when you are injecting in a particular pattern, so you can see how it behaves basically. So you can see the shape basically. This is the early life. After that, it is early life where water bank is expanding, and it's in the mid of the life, and it's late in the life basically. So how it is expanding, how it is moving ahead. Now coming to the next important agenda, that is the screening of water flood, the source of water, and the water quality. So you can see there is a process basically for water flood screening. The first one is the macro scale screening. The second is micro scale. Third comes the water quality, water source and quality evaluation, and the lastly simulation and implementation. So I will be going by one by one for all the screening process for this water flood screening and evaluation process. Just give me a minute. Okay, we can continue. So as I was talking about the water sources, you can see the first and very important is the produced water. The water that has been produced from the producer wells that is being re-injected. If I term it in a small form, that is produced water re-injection, that is PWRI. It is the most common of us. And the second is surface water, like the water can be from river or it can be from lakes. And the third one is a shallow groundwater. It is very similar to your water table from where our drinking water comes. And the next one is the best water streams, and sometimes often a mixture of some of the above, because it will not be possible to take the quantity or volume of water that is being required for water injection to cater from a particular area. Like the produced water cannot be the whole and sole part, so it can be supplemented from your surface water or shallow groundwater. So it's a combination basically. But these are the water sources that needs to be identified before starting any of the water injection. Now, injection water quality issues. So if you are injecting water in an injector well, so there might be some issues. So the first issue that might happen is basically you are injecting water and the water is not going into the formation. Then what you will do? So this is the primary thing that might happen. So there are some quality checks that is required on an injection water. So if you can see there are different contents which needs to be measured, and it should not be beyond a permissible limit in any of the injection waters. So the first thing that is known to most of us is total dissolved solids basically. The total dissolved solids should not be greater than a particular amount in the injection water. The second thing that is common is total suspended solids. The next thing is a specific ionic composition. If I take ionic composition, technically the presence of iron should be very less. And one thing which has not been mentioned is the presence of oxygen. So these are two important elements that should be removed before injecting the water into the formation. And the salinity, oil and grease content is another thing. This particular part comes when you are trying to do remediation work for produce water re-injection. Then this particular oil and grease content should be taken care of. And like in previous slide, I was telling about the water sources. So if you started a water injection in a particular reservoir through a water injector, so you should be also ensuring that whether this injection water is reliable or not. Suppose you are taking from 3 or 4 different sources, and whether those sources are sufficient to supplement your water injection requirement throughout the year or not. It needs to be uh, ascertained before initiating, and whether it is sufficient volume for future requirements. Let's suppose you have initiated a water injection in a reservoir where only 2 producers are there and only one injector is there. But later on, when more and more wells will be coming, there will be more withdrawals from the reservoir. And in order to supplement this fluid withdrawal, you need to have more water injection wells. And if you've got more water injection wells, the volume will also be increasing. So depending upon the field development plan, you need to quantify what is the withdrawal rate that is happening from the reservoir, what is the drive mechanism of the reservoir, whether this reservoir is depletion drive or solution gas drive, or it is active bottom water drive. So depending upon dry mechanism, your water injection requirement might vary. So these things needs to be ascertained, that is how much volume will be required for the future. Now, successful water flooding. There are some key elements for successful water flooding. The first thing is your high movable while saturation. Means if you don't have while saturation inside it, what water can do? If you try to inject water and produce water only, there should be movable while saturation. Moderate to low while viscosity. This particular term is being directly dealt with your mobility ratio. If you have calculated the mobility ratio, so it takes into consideration permeability and viscosity of displaced fluid as well as displacing fluid. So if you are measuring or calculating mobility ratio, then you need not worry about the wall viscosity of displacing and displaced fluid. Favorable relative permeability. Next is low permeability variation. Low permeability variation is nothing but the reservoir should not be very much heterogeneous. If the reservoir is heterogeneous, you are injecting water in a particular point and this water is going somewhere else. Pattern should be symmetrical. And next to this is ability to inject large volume of water. So the same thing has been dealt in the previous slide. Ability to lift larger volumes of reduced water. Yes, and the pumped of producing wells basically. So the last point which is mentioning the pump of producing wells, I don't know it is being understood in a correct perspective from all of you or not. So just let me tell you. Let's take an example of oil well. Let's suppose this is a packer, this is a tubing, this is a perforations basically. Let's suppose on day one, your water cut before initiation of water injection or water flooding, your water cut was nil. And when water injection started, the water starts approaching these perforations, and water starts getting produced with oil. So it is serving both the purposes. Your pressure is increasing, and your fluid inside this particular wellbore is being lifted to the surface without doing any intervention jobs. But what might happen if the volume of water or the water cut goes as high as 90 to 95%? The reservoir pressure might not be sufficient to lift this fluid. So in such cases, if the PI of the well is high, if the productivity index of the well is high, you might end in deploying a ESP pump basically. You have to incorporate a pump to lift that fluid. So this particular fluid can be lifted. Otherwise, the high density fluid inside this wellbore will exert a back pressure on this, and this will prevent the fluid from moving in this part. So if you create a vacuum or drawdown in this particular area, this fluid will be lifted easily. So at the same time, when you are injecting water, you should also have, that the water cut will be increasing in the producer wells, and you should have sufficient mechanism by virtue of which you can just pump off all the produced water. Now coming to the effectiveness of water flood, I think that there are two important things, that is the macroscopic effects and microscopic effects. I will be telling both the effects in the subsequent slides. So the macroscopic effects consider these four parameters: the heterogeneity, the permeability, contrast, the continuity of the reservoir, and the fault and the fractures. So these are the things that is on a broader scale basically. If you go to the poorer scale, that is being dealt by microscopic effects. So just let me read out microscopic effects, and then I will try to combine these two and tell you how these two things are combined to make a successful water plot. In microscopic, you are dealing with the pore size distribution and geometry. So I think many of you might be knowing the geometry of the pore. There are various distribution pattern in which your porosity percentage increases or decreases depending upon the geometry of the pores basically. The capillary pressure, which is mainly dependent on the grain size. The less the grain diameter is, your capillary will be high. High capillary will be built and your transition zone will be more. Wettability, relative permeability character, and injection fluid induced damage basically. So all these things is being dealt on a porous scale, and these things on a, you can see, on a reservoir scale. So we start with the macroscopic effects. If the reservoir is not heterogeneous, permeability contrast is not that much. One part of the reservoir is connected to the another part, and there is not, the reservoir is not faulted or fractured to an extent, then we can say this particular reservoir is well suited for your any water flooding. But even though these parameters are well and good, and your pore size distribution and geometry and capillary pressure and wettability and relative permeability, these parameters are not helping you out, then you will not be able to achieve a successful water flood. So all these parameters which are listed in microscopic effects are measured in a laboratory basically. So you can, or we can take the lab reports, try to analyze those data and try to come on a conclusion. Whether you can, well in advance, you can tell whether water flooding will be successful or not based on these macroscopic effects as well as these microscopic effects. So now I am coming to the different factors that will drive the outcome of a water injection project. So you can see a formula, and these acronyms are known to everyone, even though I have listed what they represent. In P is the cumulative water flood recovery, N is the while in place start of injection, and this EA, EV, and AD are different CPPC and C. Like A represent for aerial, V for vertical, and D for displacement efficiency. So there are if you consider only area of CP efficiency, it depends on various factors like mobility ratio, the pattern that we have selected, this line drive, staggered line drive, 5 spot, 7 spot, or 9 spot, directional permeability. Directional permeability, let me give you some more what is directional permeability. Let's suppose this is a particular reservoir. So I think you all might be knowing this fact that permeability has 3 components. It is permeability in X direction, permeability in Y direction, and permeability in Z direction basically. So this Kx and Ky, most of the times we assume that this Kx is equal to Ky. Means in laterally, if you see, or aerially, if I can say, these two parameters are pretty similar. If the reservoir is not very heterogeneous, but sometimes there is a directional permeability associated. Kx is not equal to Ky, so that thing is also to be noted. Let me illustrate you with this example. Let's suppose this is an injector and this is a producer, and your directional permeability is in this direction basically. then this injected water will reach this producer. But what might happen? But this is the case when you know that there is a directional permeability in the reservoir which is in this direction. But if this fact is not known to you, you will try to put this producer here, and you will not be able to see any effect, even though the distance between this injector to producer is more than this distance, even though the fluid will move in this direction and not in this direction, because there is a directional permeability involved in this. So the knowledge of directional permeability is very much important while implementing water injection. Now coming to the pressure distributions. Again, I take an example. This is a reservoir basically, and let's see that if one particular part, in this particular part of reservoir, you have done drilling of around 20 wells. 20 wells you have drilled, and in this particular part, I'm segmenting it. 5 wells you have drilled, and this particular part only 2 wells you have drilled. So what do you think that the findings will be maximum in this area, provided all are producing with the similar rates? So now, even though I am producing this particular reservoir at the same rate from all the wells, this voidage will be maximum in this area, and the pressure sink that will be created will be maximum in this area. If you compare data of this particular area to this area, so there is a pressure distribution. So this particular pressure will be low and this will be high. So you need to concentrate on this particular part. Your water injection is required firstly in this, then on this, and then in this. So this particular thing is being seen in many of the fields because depending upon the field development pattern or the known data available while drilling or the lease boundaries is specified at the time of the study, the development drilling in one part is the most and in the other part it is totally untouched. So there will be a gap of pressure. So the pressure distribution should also be seen. Cumulative injection and operations. Yes. Now the vertical CP efficiency. Vertical CP efficiency is totally dependent on kV by kH. This parameter you can get from your special core analysis that is being done in the lab. And E wall, this is the combination of these two, EA and EV. And ED is a function of primary depletion, KR, relative mobility, and viscosity. If we combine it, it is mainly dependent on mobility ratio. Now there is a formula for this volumetric CP efficiency that I have taken for calculation purposes. So you can just calculate what might be the volumetric CP efficiency by using this formula. So these are the various terms like HWC is the coordinate water saturation, HW bar is the saturation at breakthrough, NP is the produced volume, BP is the pore volume, VO is the formation volume vector. So it can just give you an ideal estimate of the volumetric sweep efficiency. Now coming to the, you remember when I started the slides that we will be discussing on some case studies, and these case studies belong to Oil India Limited. So for illustration purposes, I am using it, and it can be seen that how water injection has helped in terms of recovery as well as pressure maintenance. I think these were the two things which were targeted when water injection need was required. So just start with the field one. So there are two graphs. First of all, the top graph the top graph is representing the basically oil, water, and GOR. Oil is represented in red, water in blue, and gas in green. And you can see these black dots basically. These black dots are nothing but pressure trends. So these are the pressure data that have been obtained throughout the life of the reservoir. And I have tried to put a trend line which depicts how the reservoir pressure has declined, how the decline has been arrested, and how this has come forward. So I think if you remember the fill-up part, there was a fill-up part when I showed you in the second slide. There is a fill-up part. So this part can be attributed to the fill-up part basically. When there is a arrest in decline and this reservoir borders is being arrested and the void spaces are being filled. I just forgot to mention you in the bottom graph, you can see the water injection basically. This particular curve is your cumulative water injection, and this indigo color is being represented by your water injection rates basically. So you can see if I try to draw a line, so this is the initiation of the water injection. From this is the point where we have started water injection, and you can see there is a response. There is some response time. Even I have initiated water injection, there is a decline in the pressure. So some response time is required for pressure effect to be filled. And after that, you can see that the pressure has stabilized. And you can see as we have increased the water injection rates, the reservoir pressure is also going in upward direction. So this was one part of it where we can see that how reservoir pressure has responded in a particular reservoir, how the fill-up part has been identified, what is the response time. So all these things can be inferred from this particular field plot. So just look at the numbers basically. So this is an estimation in primary recovery, primary depletion. We could have got only 21%. In water injection, when we did a water injection, it went up to 35%. And after water injection, we have done some EOR method also in this particular reservoir. So I will restrict myself to this particular part only. So even though you can see that there is a jump, there is a quantum jump of around 14% additional recovery factor that has been attributed only by water injection. So this is the ideal example where you can see a reservoir which is producing from 1960s and it is producing till date. This reservoir is still producing, and the current recovery factor is around this 49%. So even though this was a depletion drive reservoir, which is a typical characteristics, the decline in reservoir pressure, there was some aquifer support, but that was not sufficient. So why I am telling this reservoir was a depletion drive reservoir and very weak aquifer support, only because of this particular fact. You can see the blue curves in this particular part. The very minimal water is being produced. Even we have started production in 1958 until 1976. There is hardly any production of water. The water is not being produced. Water is not present. This is the only technical water that is being produced from the reservoir. After that, when water injection is started, you can see how this volume of the water has increased. Again, when we ramped up the water injection, this water injection has increased. So this is a perfect example where you can see even in the depletion or solution gas drive reservoir with a weak aquifer influx also, the recovery can go as high as 49%. But definitely it's not only the water injection that has helped us, but the polymer flooding. Polymer flooding has also helped to increase a substantial recovery. Now coming to the second field. So I was telling that there are different methods of secondary recovery, that is gas injection is also. So I have kept this example where water injection and gas injection both were implemented. So as you can see, this is the line basically which represents the gas injection part, and this particular part is represented by the water injection. So in this particular period, water injection and gas injection both were implemented, and you can see there is a arrest in the decline. Why I am saying that, if I draw a trend line from this particular part, it should have followed this line. But after the implementation of water and gas injection, this decline has been arrested. Even though it is declining, but the decline is not that high. After the time we have stopped gas injection and we started only water injection, you can see how the water pressure response has been taken as it. So the reservoir pressure has increased, and it is also linked with the recoveries. So if you can see the circle, this particular circle, and if you can see this the rate curve, you can see the reservoir are producing in a range of 100 kiloliters per day, but it has swept some while and it has reached to a level of around 300 also. Even though there are some contributions of infills also, because if you are doing injection, you need a tapping point. If you are sweeping a while, by virtue of water injection, you should be having some tapping points to tap that oil. So infill is definitely required. So you can see the level of rate, oil rate basically, it has gone up. And the most important factor is the recovery factor. That is also substantial, 35%. So these two fields in oil India Limited has there are several examples, but these two examples have been shown to you for real field experience, where water injection has really worked, and we have gained both in terms of reservoir pressure as well as oil recovery factor. It's a basically similar illustrations of in terms of cumulative oil recovery, just to illustrate. This is the where water injection has been started, and this is the additional recovery till date due to, you can say, due to IUR. Now coming to the last slide basically. So water flooding can result in significant additional incremental oil recovery in many reservoir situations. I think in the last two well examples we have seen, and not all reservoirs are prime water flood candidates. So I have shown two important elements, that macroscopic as well as microscopic. So both these things should be taken care of while selecting a particular reservoir for a water flood. And the macro scale features may control the effectiveness of water flood, whereas if you look on the micro scale, that the mobility ratio is dominates basically. So with this, I have come to the end of the presentation, and if you have any questions to me.
Thank you, Dr. Manish. It was a nice presentation. Any queries from participants?
You can ask any questions from the presentation for water injection or elsewhere also, if you have very good.
I have a small query, Dr. Manish. So
Yeah,
I
yeah.
want to know what is the salinity of the formation water of the upper Assam basin, mainly the oil in
See, in Upper Assam basin, where while India is operating, basically it varies on age basically. So if I see Tirpam reservoirs or Bareil reservoirs, the salinity is below 2000 ppm. But if I go deeper in Eocene reservoirs, the salinity is in the range of 3500 to 4000 ppm.
and what is the range of the salinity of the water that we are injecting?
The water we are injecting, mainly it's in the range of around 200 to 500 ppm salinity water is being injected currently.
It is mainly formation water or the borehole water is injected?
We have got shallow water injection wells are available. So shallow water injection wells are basically being catered, but not all. Some produced water is also being treated and try to maintain a salinity. So I'm just giving you a rough estimate.
There is one query from the participants: why water injection is important?
Okay, so I think in the field examples, let me go back to the previous slides. So I think this slide has answered your question. So I will replay it. There are two important aspects of water injection. The first is maintenance of reservoir pressure, and the second thing is increase in recovery. So you can see if you come to the black curve, you can notice that when the water injection is initiated, there is a arrest in reservoir pressure decline, and after that there is an increase in reservoir pressure also. So the first purpose is solved, and the second thing is increasing the recovery factor. So you can see the recovery factor after water injection is quite close to 35%. So both the purposes are being served this particular reservoir, and this is in general purpose of any water injection reservoir.
Any other query? Well, if there is none, we come to the end of this session. So on behalf of everyone, I want to thank Dr. Manish Kumar for sharing with us your knowledge and expertise on the very important topic of water injection, which is a very crucial part of the upstream petroleum technology. I believe everyone enjoyed your presentation, and it was a pleasure listening to you. So once again from Dibrugarh University, thank you, Dr. Mann. Thank you very much.
Thank you, Dr. Fugan, for accepting my request for accommodating in a very short interval of time. And I thank Dibrugarh University for giving me this opportunity to talk in front of so many persons. And I wish all the attendees all the best. And thank you once again.
Thank you. It was a pleasure. Thank you. So our next session starts from 4:15. From 4:15, we start our next session. So the resource persons are from Anton Park. They will be speaking on nanofluids and also the petroleum rheology. So please join me again at 4:15.
This conference will now be recorded.
Dr. Sumit, are you there? Dr. Sumit Singh, are you there? Dr. Sumit Singh, can you hear me?
Hello.
Dr. Sumit Singh, can you hear me?
Yes, yes, I can hear you.
Yeah. So I'm starting.
Yes,
So
yes,
welcome.
I'm starting.
Yeah, welcome back. Now we will begin the sixth session of the IPP. The resource person for this session will be Dr. Rishi Gupta and Dr. Sumit. Dr. Rishi Gupta has done his doctorate and postdoctorate from the University of Delhi. He has more than 12 years of experience in the field of catalytic reactions and analytical instruments. Dr. Gupta has a rich experience in material characterization and has conducted several training programs on related topics. He has more than 40 publications to his credit and currently working as an application specialist in the characterization division of Amtanpar, India. He will try to give a brief introduction on to the technologies for nanoparticle size analysis pertaining to enhancer recovery and density determination for improved drilling. Dr. Sumit Singh is working as an application specialist, characterization division at Amtanpar, India. He completed his PhD on thermal and rheological behavior of polymers and modified bitumen from IIT Roorkee. He has keen interest in rheology along with its wide range of application and modularity. He has vast experience in providing training and delivering webinars, lab sessions, workshops, lectures on numerous applications of rheology such as asphalt, polymers, smelt, oils, DMTA, gels, glass, powders, composites, etc. He has published and presented many research papers in national and international forums and have received few academic accolades during his research career. He will be talking about the rheology on basic principle with configuration dedication to petroleum products and discuss about the potential significance and real-time application in petroleum industry. So please join me in welcoming Dr. Gupta and Dr. Singh. So first, Dr. Sumit Singh will be speaking on the nanoparticles application in enhancer recovery. So over to you, please.
Thank you, sir, for the introduction about this session. So I just want to ask, sir, I mean, is my slides are visible to everybody?
Your slide is not visible, but your desktop is visible. You can select that.
Just
Slides are not visible.
is it visible now, sir?
Yeah.
Yes, Sumit, it is.
Thank Okay, thank you. So today we at Amtanpar we are organizing this session, a knowledge web sharing session. So myself, Dr. Sumit Singh, along with my colleague Dr. Rishi Gupta. So we will be presenting about the application and wide capability of the Amtanpar instruments for the mostly for the usage of the petroleum and its allied materials. So introducing some feature, I mean, basic of our portfolio of the company. So we are roughly around 3,400 plus, or normally we have approached to 3,600 plus employees worldwide, and we established in 1922, and fortunately this year we are going to complete our 100 years, and we have a headquarters in Graz, and we actually invest 20% of our revenue which we get in the research and development, and we have 33 sales subsidiaries, and we provide 170 measurement solutions, even more than that. So coming to the specifically for the petroleum refineries products, so Anton Power offers multiple solutions to the petroleum industry. So starting from the flashpoint tester, coming to the distillation, coming to oxidation stability, cloud and PowerPoint calculations, water oil separation, gum contact tribology, and viscosity is very crucial factors parameter. We can obtain the penetration properties, softening point measurement, the fast breaking point, ductility. So in this session, we are more specifically focused on the towards the rheology. So we in this session, I will mostly concentrate for all the rheological flow properties for the petroleum materials and allied materials. So I am Dr. Sumit Singh, working as application specialist at rheology. So today I will be covering about the petrochemical rheology, its principle and its wide applications. So before going, I will start with some 2-3 minutes of the basics. Those who were not from the rheological background, so they would have some flavor about what sort of flow properties, what sort of applications we are going to study in the, I'm going to share in the entire this session. So for those, they would have some brush up knowledge so that they get an idea about the how the flow properties, what is rheology, and how what is the main applications, practical applications of the materials. So as the word suggests, what is rheology? So we know that the logy stands for the study of any kind of materials or any kind of study subject, and rheo means the kind of flow behavior. So the rheo stands for the study of the flow behavior. So this flow behavior basically in a general mindset, when people thinks about this rheology, so the first thing a parameter came into mind is the viscosity. So we know that the viscosity is important parameter, but along with the viscosity, there are many multiple parameters where with the rheology you can understand not only the viscosity, also the other structural properties of some materials during different applications. So this is just nothing, just if you apply certain force to the material and even that materials feel some kind of deformation, either that deformation or that force you have created either by applying certain external parameters like temperature, pressure, humidity, any kind of force which you have where the materials property gets changes with the application of that force, and the deformation, or whether it is a permanent deformation or a temporary deformation, that can be measured along with the time over the time is basically called the rheometry. So measurement of these particular rheological data is basically called the rheometry. So physically, if you see when you apply a force to the fluid, what happens when you apply the force to the fluid starts some kind of flows. So for the fluids, liquids, the flows word matters, but for the solids, when we want to understand, then the deformation word is more appropriate. So for the fluids, the flowability is very much important, and for the solid materials, the deformation is basically being come. So when a force you have applied to the materials for the fluid does not regain its original shape because it has some losses which occurs during the force we have applied, and that energy as a flow and the heat it losses. So the response to the deformation for the solids is governed by two things. One is the viscous parameters and other is the elastic parameters. So when a force is removed from the solid returns to original shape. So why it returns to original shape? If the solids have basically a stored energy, and it can recover safe if you apply certain limiting amount of force where the solid structures do not get deformed completely. So most of the materials exhibit both the viscous behavior also as well as the elastic behavior. So the viscous behavior is basically called as the fluid, and the elastic behavior is basically called as the solid characteristic part. Now, when the material has both the segments, viscous as well as the elastic behavior, then basically those materials are called viscoelastics. So consider as basically once we start wake up in the morning, we encountered with many of the materials in our day-to-day life, and those materials somehow play a very big role in our day-to-day applications. So just taking it coming to the left, right, extreme left side of the material, basically called the water. So it is a very low viscosity, and once you keep going on the right side, you can see the viscosity gets increased as where the materials, different materials applications existed. So starting from the water, then oil, then honey, then go to the toothpaste, and then you go to the solid materials. So any kind of materials starting from the very low viscous to the very solid, you can find out the viscoelastic properties. So the viscoelastic property basically works on the two plate model. So you can see here, this is the lower plate. So this plate is basically a stationary, and the upper plate is measuring geometry, where the upper plate shaft is moving down and it's tried to press and try to apply certain shear to the material. So the lower plate is fixed and the upper plate actually rotates, or you can say it applies some sort of shearing force to the material until the material started showing some kind of flowability or the viscoelastic properties are being measured. So this geometry basically works on the two plate model. So the upper you can see, consider this as the lower plate is the one plate that is stationary, and the upper plate is the measuring shaft, is basically called the two plate, because the upper plate that is the movable, once we apply force to the material gets deformed. So just get an idea and a basics that this is basically called a lower plate, and this is called the upper plate, which I have just shown. This upper plate is basically a movable plate and the lower plate is fixed. Once you apply a force to the with the help of upper plate, the material actually deforms. So it deforms from its original position to some displacement. So once you apply force in the form of shearing action, so what happened, the shear stress which is basically calculated is equal to the force divided upon the area. So this area is basically calculated from the geometry, upper plate geometry. So suppose the upper plate of the geometry is 25 diameter, then you can calculate the area and the force which you applied. So once you calculate, you will get the shear stress, and the shear rate is basically the speed at which this plate is moving and with the gap or the height of the material. So that is basically called the shear rate. So once you apply this force divided by the shear rate, you will get the viscosity. So this is basically dynamic viscosity, because most of the samples are mostly non-Newtonian in nature, and once you increase the shear rate, the viscosity keeps on changing. So the ratio between the shear stress and the shear rate is basically the viscosity. So this geometry basically works on the two plate model. So if you consider about the basic idea of geometry, so what happened, either of the two, once you apply stress, the material induces some strain. So that strain is basically called a deformation. Or if you keep deform the material, and the material gets some stress. So if you apply stress, the material gets some strain induced in the material, or if you apply strain, then there is a stress induced in the material. So these both parameters are interrelated to each other. So how can you apply the stress and strain? We have a different number of influencing factors which actually influences the material, so that its material's internal structure or materials feel some kind of stress or strain under certain environment. So that environment or factors has basically, first is the temperature. So if you increase the temperature, the material may expand or contract, or may induce some internal forces where the material's internal structure or the property changes, either with the pressure or the humidity. So we have some smart fluid also where the influence of the magnetic field changes the stress. Now consider this, the skeleton of this compact rheometer, you can see here this is a measuring head. Just as a human being, we have a brain here. So this brain is basically called a measuring head of a rheometer, where everything is being controlled by this measuring head. So this head have a rotor and the shaft, where the shaft actually helps the rotor to rotate or shear the material. So this, we have integrated encoders here, and this integrated encoders or shaft or rotors are basically being suspended in such a way that this disc or the shaft are basically not in contact with each other, and it actually lying in the pressurized air medium. So this pressurized air medium, it seems like that there is no physical contact, so it will reduce the minimum of air bearing frictions. So whatever the sensor will enclose the torque induced when it keeps on shearing on the material. Is my slides are visible? There is some pop-up notification is coming on.
Dr. Smith's slides are visible. Your voice was not coming in between.
Okay. Let me share it.
It is visible perfectly fine. Just need to go
So
ahead.
my voice is audible?
Yes, yes.
Okay. There are actually some error is coming on my screen, and it's saying that you have to move this window away from shared application. It is pausing screen sharing.
You can share this thing again.
Okay, sure.
Your voice and slides are visible here.
There are some errors in the application, sir. I will share it again. I think it will be visible to everybody right now.
Okay.
I think it is visible, sir, right now.
Visible. You can make it, your slides are small, so you can make it large.
Okay.
Hmm? Is it large?
Is slides are visible? Hello.
Visible.
Hello. Is my slides are visible to everybody?
Yes, sir, visible. It's visible,
Okay,
sir.
okay. Thank you. So basically, I have explained about this that rotor and the disc, which are basically suspended in the pressurized air medium, where the air bearing friction is very much minimal. So we have two modes in the rheometer. So first mode is basically rotational, and another mode is oscillation. So this rotational mode has basically been preferred for those kind of studies, for those kind of tests, where the samples are very much in the liquid state, or if at a semi-solid state. So for the shearing action, for getting the dynamic viscosity, these rotational tests are more preferred. And for the oscillatory test, where we want to understand some temperature variation effect, or you want to understand the structural information, then the oscillatory tests are much more preferred. So without going into the detail, we can say that the rheometer which Enterbar supplies, so it have a wide range of capabilities. So these capabilities are basically called the modularity. So this modularity means that you have a number of options where you can vary different number of parameters according with the desired applications. So you can go from -160 to 1000 degrees Celsius also, where you can vary the pressure from up to 1000 bar. You can vary the electric field and magnetic fields. You can vary the humidity if you want to understand how the humidity is playing a wider role in the application of your sample. So you can vary the humidity and you can understand how the humidity can change the viscosity properties of the material. You can find all the structural information. You can do the microscopy where you can understand the how your materials, particles or globules or any kind of structural changes which are happening during shearing or during any kind of temperature variation, and some transforming movement also for some kind of material where from raw material you have manufactured some films, some fibers from composites, where you can want to understand the mechanical strength of the properties, and you can do the DMTA. You can do the wear and tear properties of any sample, just like oils, greases, petrol, diesel. Then you can do the tribology where you can understand how the friction coefficient are being changed for different materials. You can do the powder rheology also, you know, the starch rheology also. So coming to the very basic geometries which are being used for the rheology. So considering that mostly the standards geometries are being used is the concentric cylinders. So these concentric cylinders are being used for those materials which are very much liquid in nature. So when the viscosity is very low, just like taken oil or mineral oils or waters, then we have to use these concentric cylinders. Then for the cone and plate geometries, we can use the particles where the particles are very much small in size, or you can say that when the gap is 0.1 mm, then the maximum particle size which can be accommodated, or you can use this cone and plate geometry is 1/10 of the size. So when you suppose you have a size of 1 mm, then the maximum particle size we can use for cone and plate geometry is 0.1 mm. Coming to the very last, the parallel plates. So this parallel plate geometry are most general plate which being used for the all kinds of general samples, just like fluids, solids, gels, and pastes. So coming to some industrial parameters where how this rheometry is basically being used. So the first information or the flow property or desired is the viscosity. So why this viscosity is very much important, because for the process development, when we manufacture the raw materials, we have to pump it, or we have to store it, we have to transport it from some location to the another location or some another medium. So where the material actually encounters with different number of pressure ranges, different number of temperature ranges, and different number of shear rate, where the material is being uh, transported or shared under the different forces. So the pump sizing, mixer designer, treater designer, dosing system, dye design are preferred. Process simulation means that you want to understand whether after preparation of the sample, how your sedimentation is going to occur, how leveling is going to occur, how sagging or dripping is going to occur, how the coating is going to affect. You want to understand the filling, brushing, and spraying, then you can understand this is the process simulation. Packet design means that you want to understand whether how the pump sizing, how the easy extraction is to be decided. Consumer perception, that you have a perception that this after this particular quality control, you will understand, you will have a much more trust about the quality issues and applications. Quality assurance, quality control, basic material properties. So this is basically called shear rates of the industrial process, where these shear rates are being varied from very low shear rate to the high shear rate. In this implies that how different ranges of shear rates basically refers to different applications of the material. So first thing, if you want to understand whether the sedimentation labeling, once you have prepared the sample, one sample is being lying stationary, then you want to understand how with the stationary position or the rest condition, how your sample viscosity is going to change, whether they have some sedimentation issue, some leveling issue. So you can understand with this particular behavior. Now coming to this higher shear rate range, you can go to the draining, you can go to the mixing, some pipe flow, some spreading, pumping, and so on. So you can see that starting from the very low shear rate to the high shear rate values, you can see that the multiple applications are there. So for every materials, the shear rate variation or calculating or understanding how the viscosity is changing with the shear rate is very much important. So just take an example, there's most of the samples which we saw that non-Newtonian in nature, so they usually show some shear thinning behavior. Why it is called shear thinning? Because you can understand that when the material gets thinner, the viscosity decreases. So here you can see the viscosity is higher at the low shear rate, and once you are keep on shearing, you are rubbing it, you are applying certain force, the material's internal structures gets sort of deformation, and you will find that the material viscosity gets decreases. Now coming to some petroleum industries where there are certain byproducts. So first byproduct we can use, the last bioproducts is basically called the bitumen asphalt, and other bioproducts which we take out from the useful products are the lubricating oils, diesels, kerosene, naphtha, petrol, and some refinery gases. So these all materials which we actually take out from this petroleum refinery systems. So those sort of quality control, those sort of understanding of the applications where you want to understand about these particular all the byproducts which you obtain from the materials. So the first byproduct we obtained is the between the asphalt at the last byproduct, which is basically called a crude oil from the crude oil distillation. So these bioproducts actually vary from source to source and from it's different from the chemical composition. So if you consider that these petrochemicals, starting from the raw materials to the applications, these actually varies from different sectors of from clothing to the health, from agrochemical to the detergent to the foods to the plastics and the bulk chemicals. So there are multiple applications where these petrochemicals are very much useful. So I will go some specific application where you can understand how the rheometer, how the rheological properties of these materials are actually very much helpful in understanding the real-time applications. So first, uh, as a byproduct, the last product which we obtain is asphalt. So we know that these asphalt or the bitumen which we actually got as a byproduct in the petroleum refineries are being used for the payment purposes. So we know that the 85% of these asphalt are being used for the payment purposes. The first and the testing you can do is the quality control. So we know that depending upon the petroleum refinery system, depending upon the quality of the petroleum refinery, depending upon the source from where this petroleum crude oil has been digged out, so these different factors varies and actually affect the qualities of the materials. So if you want to understand whether the durability or consistent according to the OSHA standards, and we have some Indian standards also where it should comply with all the standards for the bitumen asphalt. Coming to the grading of the binders, which is useful, how the rheometers are being useful, that you can grade the binders in terms of different standards which has been dedicated for the asphalt. So you can understand how the original, how the RTFO age binder, how the PAV age binders. So I will not go into detail about the RTFO and PAV age binders. So just for the information, I just want to share that RTFO stands for the short-term aging, where the replication or the binders mixing of the aggregates during where these mixing of the aggregates with the binders or the materials get exposed, and there is some sort of property loss. So that property loss can how those property losses are being considered, or the viscosity or the modulus is changing. So you can understand from this rheology and from this package binders where the long-term effect basically called the service payments properties are being studied for the package binders. So the service life, payment materials properties, payments qualitative and quantitative analysis. So though all these properties are being used with been obtained for this rheometer. So the grading of the rheometers has been important. Another thing is the performance grading. So this performance grading are basically used to understand whether we have manufactured the material and we want to understand how the performance is going to we can predict the performance whether after laying or after using this particular material, how your materials viscoelastic properties, how whether it can be used for the 5 years, or depending upon the traffic load, depending upon the how much temperature, or depending upon the quality of material which you have used for the construction. So these performance grading are having different some standards where they had to meet those minimum requirements of the standard to get passed. Another thing is MSCR. So this MSCR test are basically necessary for those materials which are basically used where the polymers modification has been done. So for the PMBs, there are some standard which have been met to understand how the elastic properties of these polymers are actually helping or giving some kind of benefit and advantage. For the properties, this MSCR test has been included. So we know that for the roads, it can go from very low temperature to the high temperature. So the materials characterization is very much needed, because if we want to understand the rheological properties, because those rheological properties are very much important, because we know that these materials, once it is laid on the pavement, there are lots of traffic with different number of axle loads are being applied or being constantly, just like a creep loading. It goes to the certain area of the pavement section and it passes by, then again some car or truck goes by and then again passes by. So it forms a cyclic load application of the materials due to this particular heavy trucks or the axle load application. So those load application and these temperature in temperature from very low temperature to the high temperature actually affect the pavement. So we know, have to understand whether during these kind of multiple in factors, application of this low temperature to high temperature, application of this loads, traffic conditions, how your material is going to behave. So you can understand the brittleness, britability, fracturability of the materials. You can obtain whether at what temperature your material is going to show rutting. So those kind of rutting behavior can be studied. Another thing is processability. We know that at room temperature, these materials are very much hard in nature and very much stiff. So if you want to process it, if you want to transport it, if you want to work or you want to mix some additives, you want to mix with aggregates, you need to heat it up. So once you need to heat it up, you have to increase the temperature. So once you increase the temperature, the materials actually being focused on some high thermal temperatures. So during that particular temperature, the material gets ages. So during that aging, material losses some volatiles to the once it is mixed. So if you want to transport it, if you want to mix it, you have to increase the temperature. So this binder and the final mixture must be capable of being pumped and poured. So suppose you have prepared the material and you want to transport it to some location. So if you want to transport it, you have to heat it. So that minimum heating temperature should be known. So you want to understand, then this rheometer is very much useful, whether what should be the mixing temperature, what should be the pumpable temperature, what should be the workable temperature, what should be the pavement temperature, laying temperature. So those compact temperature, mixing temperature can be identified with the help of rheometer. So this is basically the MSCR test, where you need to apply the load to the material for 1 second and again you leave for the 9 second. So why this 9 second and 1 second has been found? So they have done numerous studies and they find out that taking scenario of the practical load application where these materials are being used on pavement purposes, you can see here. Then suppose this is the road which has been built with the asphalt materials. So you can see here that these particular cross sections, this axle load up due to the heavy application of the axle load application, this materials implies a very high traffic load to the material for certain sections. Now again, when this particular heavy load vehicle passes, again in the backside, again some vehicle load is coming and it applies certain again the force. So the moment it gets a rest is roughly around 8 to 9 seconds. So they have made standards where they apply the load for 1 second onto the rheometer and they actually understand whether in give a rest for 9 seconds. They want to understand how the viscoelastic property, how the elastic properties are going to get rebuilt if they have a sufficient elastic nature. So those kind of understanding, they have developed this MSCR test to understand whether if you apply the continuous cyclic load to the material, how the material is going to give us the elastic properties. Now another material is the mineral oils and the drilling fluids which are being used for the petroleum industries. So we know that these mineral oils and drilling fluids are used for the drilling and for the digging of the taking of the fluids. So now consider this, that for the mineral oils, we know we have to understand whether this viscosity measurement is at certain, because we know that if you go into the edge go down, there would be a chances that we will face some high pressure scenarios. So under these high pressure applications, when we use this mineral oil or working under this high pressure is very much important for the mineral oils. So for automotive lubricants, these mineral oils are being used. So we have dedicated pressure cell where you can see here, this is the base plate where we have a cup where you can introduce the material, and we have this pressure cell. So this pressure cell has basically been designed in such a way that you can go to up to 1000 bar, and you can understand that how the effect of pressure on the mineral oil flow behavior is going to do. Now you can see here from the graph that once you apply the shear rate from 100 to 1000, now you can see here that when you give a pressure of 1 bar, the viscosity is roughly around 42 millipascal. And once you increase the pressure, you can see the viscosity rises to even 55 millipascal. So you can see that as you increase the pressure, the material's viscosity increases. This increase in the material viscosity is basically due to because it reduces the intermolecular forces between the particles, and it tries to more closely, the materials particles gets more closely packed, and it induce higher frictions. So due to that, the viscosity increases. So at high, when you increase the pressure, the viscosity gets increases. So for the modern motors, these automotive lubricants are very much important because we have to know the pressure range of the application where this material is going to encountered. So for different application, the pressure ranges actually varied. Now consider these drilling fluids. So these drilling fluids are being used for the offshore we are drilling. So where it can encounter very high pressure levels and low temperatures. So it is actually making it difficult to design some suitable drilling fluids. So these drilling fluids are basically mostly used for the offshore applications. So we have this Anton partial where we can go to the 1000 bar even, and with a low temperature option where from minus 30 to the 300 degrees Celsius we can go with the pressure cell, and we can go up to 1000 bar. So you can understand how the flow properties, how the viscosity is going to increase once we increase the pressure, or we have even flexibility that you can go to the even low temperature up to minus 30 degrees Celsius. Now you can increase in this, you can visualize in this graph that due to the pressure, the crystallization behavior changes. You can see here that the material viscosity, once we apply a 1 bar pressure, the material viscosity is roughly around 3 pascals. And now once you increase the pressure, you can see the crystallization is occurring shifted from minus 17 degree to minus 22 degree. So this crystallization behavior you need to understand, you need to know once you are doing using some drilling fluids to the offshore. So this understanding this application is very much useful to understand what kind of drilling fluid, what kind of modification, what kind of parameters you need to optimize for a better drilling. So where some brine fluids are also being designed, so these brine fluids are basically being used as it is very environment friendly and a very good degradation. So this brine fluid crystallization is very much important. Now consider this crude oils wax dispersion. So we know that these crude oils have some pour point and pour point measurements. So these pour point measurements can be calculated from this reometer. So we have this oscillatory mode in the reometer where this wax dispersion or crude oils wax formation is normal in the low temperature when we go to the cool the crude oils. So when the temperature decreases, some wax appearance are being seen. So this wax appearance, they needed some dispersion to reduce this wax crystallization. So you can see here that once we do a measurement in the oscillatory mode in the reometer, we can see here that initially we can see here that the storage modulus that represent the solid characteristic behavior of the sample. So you can see here that the wax formation occurs here, and you're going to go from 40 degree to 30 degree. You can see here that the materials shows that the materials are already in the liquid in nature, liquid characteristic properties, and you can see here that at temperature of 34.8, you can see that the crossover, this crossover says that this is the pour point where the change of phase from liquid to the some wax crystal formation called the solid characteristic behavior. So this particular point is basically called the crossover point, or you can see that there is the pour point where the material changes from its liquid characteristic to solid characteristics. So in the same way, you can find how the pour point is going to. So the pour point for this particular material is going to be 34.8 degree. So here, one thing you need to understand that once you keep on cooling the material, so you have to cool the material very slowly. So we have used this 1 Kelvin per minute for the cooling rate. So the cooling rate should be as low as possible. Now, apart from this microscopic studies, which we have understand whether we have said that we are forming some wax crystal at a temperature when we go beyond 34.8 degree. So you can understand from the microscopic studies also, where we have a dedicated attachment with the microscopy, where we can see that there's a glass plate, and from the glass plate we have a dedicated camera where we have objective and polarizer to understand how the microscopic structure, how the particles or how the wax formation, wax crystals looks like. So you can also study these things from the microscopy. You can visually understand microscopically, rheologically, whether how the wax crystal is going to move. So we have this light where you can find illuminate this light from this light source, and you can focus on this plate, and we have a microscopy where you can adjust with the objective and polarize, and you can get very good images with different magnifications during shear rates which we have applied. So you can see here that once we go from 34.8 degree to the lower temperature, you can see that how the wax crystal formation is occurring. You can see that at 35.17, some spots are being seeing at the wax crystals. Now, the moment we go to the 31.7 or 30.16, you can see here that the wax formation occurs, or formation of the crystal growth is there. The moment now we go to the more lower temperature, you can see that how the moment we go to the 1 degree lower, you can see that the more and more formation of the crystal growth is there, and you can go at 25.160 degree. This crystallization process of the crude oil actually occurs, and you can see it from the microscopically that how the crystal growth has been progressed as we go down the pour point temperature. So there are some crude oil microemulsions also where you can understand that how with how with the application of shear rate, how this crystal behaviors are being taken. So apart from the images which you can take, you can also record whether how with the movement of temperature from high to low, from how the crystals formation are occurring. So you can also record the video, and you can also record whether how with the variation of the temperature, how the crystal formation are occurring. So those sort of understanding, those sort of study you can do, and we know that this quad emulsions display a shear thinning behavior, and it will be useful for the effect of shear rate, or you can understand the microstructure of the fluids. Now, another materials from petrochemicals is basically the raw materials are polymers, where we get some granules for cracking. So from raw materials to the finished products like films, tapes, composites, from granules. So we can also study it and understand these kind of flow properties and rheological. So let's consider this. This is the polymer granules. And we want to understand that what the flow properties of the molecular weight of the polymers, or we want to understand the other properties of polymer, just like zero shear viscosity. So what we do, we take the lower plate and we put the polymer melts, and we can go to the melting temperature of the polymers of 150, 180 or 200, and we can melt it here, and then we can do some sort of viscoelastic measurements. Now coming to the viscoelastic properties, apart from the raw material to the finished product, we can also do some compression, some shearing, and you can also do some tension and torsion mode, where you can understand the viscoelastic or mechanical properties of the polymers. We have these different systems, cantilever, 3-point bending for the very solids or steel or very solid samples. You can do this, use these 3-point bending fixtures. Now there are some sorts of polymers which can vary from very low modulus value to very high modulus value. So depending on the modulus values, depending upon the type of materials, we have dedicated measuring fixtures where you can use this dedicated measuring fixture and you can understand the viscosity properties and the mechanical properties or modulus of the samples under different temperatures. So this is just an example that if you have prepared a film out of the polymer melts, you can find the extensile rheology, and you can also find the degree of crystallization and the branching. And you can also find the solid tensile testing, which we usually for the films. You can also do the peel test where you have a two substrate which are attached there to each other, and you can find how the adhesion or the capability or ability is there. Fracture test where you want to understand how the at what strain, at what how much you need to stretch it, how much to give certain amount of strain to the sample, so the fracture properties occur. So you can also do the fracture test. You can also do the tear test where you want to understand the tear property, just like for the some peppers or some polymers where you want to understand how the tear is going to occur. So you can also find those tear tests. So this is just an example of the adhesive tab, and this is just an example of the tear test, and this is just an example of the compression test fixtures. So this is the adhesive tape fixture where you can see here that, and this one is the tear test where you can see that this is the paper, and once the minimum amount of strain is applied, the material gets teared. And you can see here, now this dynamic mechanical analysis is basically that we can do all kinds of polymers for the polymer melts, sealants, adhesive, elastomers, and solids. So this is basically DMTF fixtures which looks like that, where you can, this is the oven which controls the temperature, and this is a fixture which actually does this axial or this dynamic mechanical applications studies. So at last, I will like to describe all the application in a single slide, where the first material is basically called mineral oils, where there are some methods and measurements which is very much useful for the application. So first thing that you can understand the flow behavior of the mineral oils, and that flow behavior can be characterized by doing shear rate sweep at different temperatures under high pressures. So these mineral oils under different application, we know that these mineral oils are being used for different application where the pressure ranges are very high and the working environment temperature ranges are different. So you can understand and you can find the flow behavior, and the consistency should be maintained if you want, if you are a manufacturer and you can manufacturing these mineral oils. For the drilling fluids, we know that these drilling fluids are being used for the offshore applications where this ultra high pressure or ultra high temperature rheology is preferred. So we have dedicated system where you can go to the 1000 degree also, 1000 bar also, where you can understand the viscosity properties, you can understand these sort of structural properties, whether how these drilling fluids are being used and how these drilling fluids are being needed to understand for the drilling capabilities. Third one is the crude oil. So just I've already explained the crude oil slide, that we want to understand whether the how the wax of crystal formation, how the pour point measurements are being used or obtained. If you want to understand how what is the pour point temperature, you can get an idea about the pour point temperature. You can understand with the Rio microscopy how the wax crystal formation is going to occur with the Rio microscopy. So you can understand with the you can record the video and you can understand by different heating rate or cooling rates. So you can understand how with the cooling rates, how with the temperature range your wax formation is going to occur for different number of samples. Another thing is the polymer rheology. So this polymer rheology, I'll explain that for polymer granules, which we obtain from the cracking of this naphthas or petroleum products. So we have MCR 702 multi-drive, where it actually involves all kinds of tests where you can do the polymers samples from granules to the films to the composites to the from raw materials to the finished products. So you can understand from this steady shear test, oscillatory shear test on the polymer melts, you can find the glass tension temperature, you can find the melting temperature, you can find the any kind of transition, phase transitions which are occurring due to the side chain movement or during any kind of shearing properties. Fourth one is the polymer rheology oscillation, where for the polymers we want to get an idea about the molecular weight distribution. So we have dedicated template and regression models in the system where you can do the frequency sweep, and according to the different models, we have a software where you can calculate and it will relate from the build elastic properties to the molecular weight distribution. So you can find the zero shear viscosity, you can find the relaxation time, whether we applied certain shear stress strain to the material, how much time it is going to take for the relaxation. Last one is the polymer rheology, where linear DMA is the linear DMA means that you can actually do the measurement in the axial direction of the linear fashion, where you can stretch it under the tension. So we have dedicated measuring fixtures. This is basically called SRF. So solid rectangular fixture. This is a solid circular fixture. This is a universal extension fixture, bending fixtures. So different number of product, different types of product. That if you have a product like films, then you can use this UXF. If you have a composites, our solid material, you can use this SRF. Or if you have a very stiff material, just like steels or very much stiff in nature, then you can use this 3-point bending and the cantilever option. This compression is used for the parallel plate where you want to do some compression ability test. So we have this the petroleum products, we have this wide range of applications for different materials which we often from the petroleum refineries. So these are the methods and the measurements which you can use for the understanding of this rheological properties and viscosity properties. So this was my last slide which I have explained. So thank you for very much for your patience for listening, and if you have any questions, please let me know. I will explain your queries and for the best provide the best solution which you feel encountered for your application point of research.
Thank you, Dr. Shamiti, for your nice introduction. Can you hear it from the
Anybody had any questions for the entire session or like which I have explained? Please feel free to ask me. I can reply to your queries, or you can mail to me also. I will mention my mail ID there later on.
you can type in the chat box also. If you have any queries.
You can also drop your question in the chat box where I will explain you if you have any queries. Yes, is there any test for the fire point of liquid in company? So for the asphalt or bitumen, we have seen this flash point tester where you can obtain this flash point for the materials where this fire temperature at which the fire actually takes place. That's kind of instruments we have where you can understand this flash point temperature. Anybody had any questions? You can ask me.
So if there is none, we can invite Dr. Rishi Gupta.
So I will transfer this session to my colleague, Dr. Rishi Gupta. He will explain about the particle size and the surface symmetry application for the petroleum products. So thank you everybody for the patience for listening. So my colleague, I will hand over the session to my colleague, Dr. Rishi Gupta. Thank you.
Thank you, Dr. Thank you.
Thank you, Sumit. Dr. Ranjan, can you make me the presenter first?
Hey, I'm looking. proceed now.
I believe my slides are visible now.
Yeah.
Yes, yes.
Thank you. And I welcome you all over again to this FTP session. And I'm not going into details of the company. I just will give you my introduction. Myself, Dr. Rishi Gupta. I am working as an application specialist in Anton Par India, and I am based in Gurgaon. We'll be discussing about the nanoparticles in upstream processing and their characterization. Most of this information you already know, but just to touch them up, I have briefed few of those, that what are the nanomaterials, they are the tri-dimensional discontinuity in any dispersed system, and the dimension, any one dimension of those particles has to be less than 100 nanometer. They can be of metal, polymer, carbon nanotubes, liposomes, etc. And the benefit with those is their high surface functionality, which subsequently leads to improved physical and chemical properties. They have wide industrial applications, including catalysis, gas and energy storage, in petrochemicals, photovoltaic, electrical devices, biological and medical technologies also. And their size distribution and surface charge characterization is required to obtain reproducible suspension of these nanoparticles with low poly dispersion and desired size. Size distribution affects the functional agent capacity, fluid drag and diffusion, and their cellular uptake also. So these are few properties where surface charge can also play its role. Okay. Now coming to the properties where these nanoparticles can play a role in upstream processing. So we have found several potential applications in the industry due to variety of different favorable physical properties they can impart to the material. There are many in different sections. It can be in environmental remediation, supramagnetics, reservoir traces, nucleic seeding, high surface activities, can go to structural designing, and rather I will tell you why they are going to give you these information in a much better reference, because they have high surface area to volume ratio, high surface activities, high aspect ratios. They have enhanced surface dependent properties such as thermal conductivities and electrical conductivities, and the ability of some nanoparticles, they do have the supramagnetic properties such as iron oxide. And then these nanoparticles have also been used in enhanced ion recovery that has been to, observed to display structural destroying pressure effect also. So the development in nanoscience and nanotechnology has enabled the design, their synthesis also, and the application of these nanoparticles to develop nanosensor and nanorobots, etc., in a very rational way. They could become an integral part of this oil and gas recovery process, and potentially can improve every stage. It can include exploration, can include a drilling, can include the production and enhanced oil recovery as well, transport, as well as the refinery process. So when we talk about the drilling itself, so during drilling operations, the fluids that we use into drilling must have the rheological properties required to carry the cuttings from beneath the drill bit up to the annulus of the well. And then the fluid should also provide the cooling to the drill bit and should reduce the friction there. And it should also maintain the properties while stabilizing the well bore without causing the irreversible damage to those. So these wells, when we drill with fluids, they contain nanoparticles such as nanosilica. If it is there, then they offer the possibility to improve the rate of penetration through difficult water reactive rock formations, which we also call as fells. Now, nano zinc oxides, they are typically been used there, which have been shown to outperform the H2S scavenger. So if the hydrogen sulfide is coming out of it, it can be used as a scavenger footwear that can be used in drilling to eliminate these emissions coming out of there. So there are few examples where they can play the role in well-bore stability, in filtration control, in fluid rheology also. They can be used such as nano zinc and nano copper oxide materials that can be used to cooling the pit also. They can also further be used to control the pollution, and they can also be used to scavenging materials also, as I discussed that in the case of hydrogen sulfide scavengers, then you can go with the nanomaterials made up of zinc oxide. So here I have shown you the example that how the wellbore stabilization can be made with the help of nanoparticles, that they can fill the voids and intergranular space in the rock formation. And the cadmium removal is another example. As I talk about H2S, the cadmium removal can be also been done with the help of the functionalized magnetite nanoparticles. So these functionalized nanoparticles are like the particles made up with iron magnetites, and these are functionalized with the amide group attached to them, and they are actually used for cadmium removal there. The nanoparticles can also be used in the cement, the cement application there, because we need to develop the wellbore there. And in cements, which has been used for well construction, we have also witnessed several advances in nanoparticle implementation there. So nanoscale magnesium oxide, which is been used as an expensive budget there, it can mitigate pervasive volumetric shrinkage issues in Portland cement, and this can develop a threat for long-term stability of the well, and that's for nanotubes and nanosilicas have been used as a reinforced cement material with superior tolerance to the loads, corrosion resistance, and high strength. In addition, some conductive nanofibers have also been shown to increase the piezoresistive response of cement, and they can also be used as a sensor against those. And with this sensor, the structural health of the cement inside the oil well can be monitored remotely in a real-time fashion. So when we talk about cement material issues, if the gas migration issue is there, the solution with nanoparticle can be, you can use nanosilica or the thiol groups attached to nanofoils. For autogenous shrinkage, nanomagnesium oxide can be used for increasing the mechanical strength there. Carbon nanotubes and nanosilicas can be used, and similarly for strength retrogradation, nanosilicas can be used. When we talk about the enhanced oil recovery, there are several methods and several stages where the nanoparticles can play a role. It may be the stabilization of forms, it may be in the stabilization of emulsions, and the nanocatalysis also. But for EOR methods, where we involve nanoparticles, have shown promising effects in providing higher superior emulsion stability and their propensity to displace the hydrocarbons. Multi-metallic nanocatalysts have shown the possibility for catalytic EOR, where heavy oils and bitumens are present. And if these technologies come to fruition, it is anticipated that the environment production and the transportation cost of these can be greatly reduced. So when we talk about the characterization part now, we have already discussed that the nanoparticles are going to play a very huge role in several stages of the upstream processing with gas and oils. Two typical characterization technique that has been used for their characterization. One is the size and second one is the surface area. I'll discuss about the basics of both these techniques related to size and the surface area. First of all, I'll start with the size. Since we are dealing with nanoparticles, and these nanoparticles, if you want to check their size, you need to disperse them into some solvent, and as soon as you disperse the nanomaterials into some solvent, it tends to perform a random motion that we also known as Brownian motion. So the whole approach here for dynamic light scattering basically depends on the Brownian motion of those particles. It tends to perform this random motion there, and this Brownian motion into the solvent is basically dependent on three main properties. One is the size, then temperature, and the viscosity of the medium. And when we talk about size, we already understand that if the particles are bigger, they will move slowly, and the particles are small, they will move faster. And we need to determine this velocity of these particles. And with this velocity, we can correlate their size. And for this Stoke-Einstein equation has been used, which says D is equal to Boltzmann constant into temperature divided by 6 pi eta, where eta is the viscosity, and RH. RH is the hydrodynamic diameter or radius here itself, it is radius. With this, you can correlate the velocity with the hydrodynamic radius. Now in this whole equation, except D and RH, rest everything is constant. Boltzmann constant, temperature is kept constant, viscosity of the medium is also kept constant. So there are only two variables, one is D, another one is RH. Where D is the translation diffusion coefficient, you can also consider it as the velocity of the particle. So you need to know the value of D, you can calculate the value of RH. As the phenomena suggest that the light scattering is going to play roles. So the light scattering basically is that you put something into the straight trajectory of light, and because of that object, if the light is deviating from its path, we call it as scattering. And let's consider if the particles that we put inside the measurement cell, they are not moving. This whole experiment will behave like a double slit experiment where the light will be scattered and the scattered light will make interference with another particle. Now, if this interference is constructive, it will be a brighter spot. And if this interference is destructive, then there will be a darker spot. Now, since there are not only two particles, there are many particles. So instead of forming the bands, it will form the speckle pattern. Again, the same thing is there. The brighter part is because of constructive interference, and the darker part is because of destructive interference. But in our case, the particles are basically moving. They are not static because I told you that they will be performing the Brownian motion in the solvent. And since they are moving, this speckle pattern will not be the static. It will also be the dynamic one, and it will change continuously. Up till now, we have discussed that there will be a laser source which will be incidenting over the measurement cell where the particles will be performing motion, larger particle moving slowly, smaller particle moving faster. The interference will be detected over the detector, and the speckle pattern will be produced. It will be produced in a way that in case of smaller particle, the speckle pattern will change very fast. In case of larger particle, since the particles are moving but at a slower pace, the movement and the change in the speckle pattern will also be there but at a slower speed. Now this DLS measures the rate at which this fluctuation is occurring. So if I need to prepare a graph between this intensity, fluctuation intensity with respect to time, and for a smaller particle, it will be changing very frequently. When in case of larger particles, the change will be there with time, but at a slower pace. So the fluctuation will not be that high. And at the end, we don't want these fluctuation rates. We want the particle size, and for this, we need to understand the correlation spectroscopy, and with that correlation spectroscopy, the intensity-based correlation function G2 comes into place. So this G2 is basically the mean correlation between two measurement signals that has been measured after a time separation. And since these particles are moving, these correlation signal will not be the same. So to make it more clear to you, let's say two signals are there which initially are in a good correlation. When we talk about the value of G2, the maximum value can be 2, the minimum value can be 1. As you can see, if they are in a good correlation initially, the value of G2 will be high. And as the time progresses, they loses the correlation because they are moving and the correlation will not remain the same. It starts declining, and then there comes a time when there is no correlation at all between the signals, and this becomes the minimum value, the one. So when you talk about the correlation function and the particle size itself, you can see there if the particles are smaller and they are moving in this fashion, this type of correlogram will be obtained, which means that the particle will lose the correlation very quickly. This will happen because they are moving faster. And in case of larger particles, the correlation will exist there for some time and then it starts to decline. So if you are experiencing this type of graph where the correlation exists for some time, it gives you an idea that your particle in your samples are of larger dimension. Now from these correlogram, you can calculate that how much time it took from declining from the value, the maximum value to the minimum, which will give you an idea of the decay rate of this correlation function. And by using this decay rate tau and scattering vector, which you can calculate by knowing the wavelength of the light, you can calculate the value of D. Now this D is the same D which was over there in the Stoch-Einstein equation. Now we have the value of D and we can calculate the value of Rs. So this is how we get to know the hydrodynamic radius in any instrument that is measuring the nanoparticle size with the dynamic light scattering approach. As I told you that correlation spectroscopy has come into place here by knowing the intensity trace first. So several algorithm has been also used to determine the parameters here. So for correlation function spectroscopy, we require two algorithms. One is cumulant algorithm, and one is analysis algorithm. For cumulant algorithm, if the sample is monodisperse, then you should go with cumulant algorithm. If the sample is polydisperse, then one should use analysis algorithm. With cumulant algorithm, you will get the information of hydrodynamic diameter and the polydispersity index, and while with the use of analysis algorithm, you will get the details about the particle size distribution. This is the common setup for dynamic light scattering. A laser source will be required. In our case, we are using a solid state laser because when people use gas lasers, they require longer warm up time. So it can go up to 30-35 minutes even. But in case of solid state lasers, the warm up time is very short. Then a polarizer for collimated polarized light, a variable attenuator, or you can also call it as laser power adjuster. So it will adjust the laser power over the sample. If the sample is quite turbid, the laser power will be low. If the sample is dilute, then the laser power should be high to obtain a substantial amount of signal out of it. Different type of detectors are there which help us to determine the size of any sort of particle with any dimension, obviously nanomaterial. Then besides these three detection angles, we also have a transmittance detector. Now, in this instrument, we have a sample chamber which can go from 0 degree to 90 degrees centigrade. And this is to simply simulate the conditions that will going to happen with your material into when it is there into application. So when we talk about a drilling fluid, what would be the temperature there? So if you want to simulate that, what will happen to the particle size in those conditions, that you can simulate those conditions in this sample chamber by raising the temperature. Then we have the movable focusing lens also, which will focus the light over the sample. So if your suspension is quite turbid, we can go with the backscattering detection angle by making the focus at the very edge of the cuvette. And if your sample is quite turbid, dilute one, then you can make the focus at the very mid of the cuvette, and then this lens will be shifted toward the sample. So this is a movable lens which will be used to shorten or lengthen the focal length over the sample. Different detection angle, as I told you, they are for different type of samples. A backscattering detection angle be used when you have a highly scattering sample or your sample is having bigger particles. Then for smaller particles or weak dispersion sample, side scattering should be used. And if you are having a mixed population type of sample, typically if it is having nano size particles, small particles, and some larger particles are also there, then one should go with the forward scattering. This was the solution that you can get from Anton Pass in terms of particle size distribution with the help of light size F500. But this particle size is not the only parameter that you can get out of this instrument. You can also get data potential values. You can also get molecular mass index. You can also get the refractive index and the transmittance value from the same instrument. So this was related to particle size, and now I'll move towards the surface area, how these nanoparticle surface area can be determined. The approach that typically people use to determine the surface area for nanomaterials is called as gas phase option. And in case of gas phase option, basically we want to determine how much is the porosity of your nanoparticles are. So those the particles which have the nanopores there, and this is that I've shown here is the classification what IUPAC has given to those pores. So if the pores are smaller than 100 nanometer, we call them as nanopores, and if they are more than 50 nanometer, we call them as macropore. Mesopore lies between the range to 2 to 50 nanometer, and all the pores which are smaller than 2 nanometer are classified as micropore. Now these micropores are further subdivided into ultra micropore and super micropore. So this gas phase option is a common method to measure the surface area and pore size distribution in microporous and nanoporous material. You may also be interested in knowing the pore size distribution for macroporous material also. But for macroporous material, instead of gas, the probing molecule is different. It is mercury, and for that mercury intrusion porosimetry is the right instrument. But for now, I'm talking about the nanometric characterization. I'll be focusing over the gas phase option only. And this gas phase option will allow you to probe the entire surface, including the through pore, blind pore, and the surface roughness. And we typically count the number of gas molecule that has been used to cover a complete monolayer over the surface. And then by multiplying this number of gas molecule with the cross-sectional area of the adsorbent gas, we can get the surface area of the material. So if you want to do the physics option of for any material, you first need to make the pores empty, because in its native condition, those pores may have some moisture or some vapor inside. So before we fill the gas of our choice into those pores, we first need to make them empty. So we need to degas the sample first by raising the temperature. Then we apply the gas of our choice and record how much volume has been absorbed over different pressure ranges, which give us this type of graph where x-axis is of P by P0 and y-axis is consists of volume absorbed. This whole exercise is being done at a constant temperature, which is the critical temperature of the adsorbed gas. Here in this case, typical people when use the nitrogen, the critical temperature of nitrogen should be 77 Kelvin. And we use ideal gas law to determine how much volume of the gas has been absorbed. By knowing, then by subsequently we get to know the moles of the adsorbed gas. Now by multiplying with the Avogadro number with this mole, we get to know the molecules, how many molecules are there. And then we can multiply the number of molecules with the cross-sectional area of the gas to get the surface area. So typically there are three process steps. One is the degassing, second is the analysis, and third one is the data interpretation. Now for degassing, we understand that some degassers will be required, and typically people have separate degassers than the analysis system. But the system that Anton Para offers has an inbuilt degasser to assess the micropores. The system also has a turbo pump inside. So with the help of turbo pump, we have the maximum efficiency of degassing. Now then, to save our turbo pump from incoming moisture that is coming out of these degassers, we have an inline cold trap. So the cold trap, degassers, and the turbo pump, everything is inside this body only. This is the degassing profile here. Over this instrument, you can have different temperature for different hold time with different ramp rates. You have the option of pressure control heating limit, where pressure this degassing will be done as a function of pressure rise. Then we have the option to keep the sample cell into different states. You can backfill the sample with nitrogen gas, and you can have the option to keep your sample cell into vacuum after degassing. We have this option of testing segment, which will tell us whether the sample has been degassed completely or not, and it will also save your sample from getting unnecessarily thermally aged. And we have this option of evacuation crossover, which will save your sample from being eluted because of sudden high vacuum. Now the second part in this process was analysis, and this is the schematic diagram for that. So if we are having any sort of sample, we need to apply some pressure over this with the adsorbate gas. Now it will start getting absorbed over the surface here and there, and as on we increase on the pressure there, the gas molecules will form a statistical monolayer over the surface, and this is the stage where we can calculate the surface area because the monolayer has been formed. Now from stage 2 to stage 4, the pores will get filled. The smaller pore will fill first, the larger pore will fill later on. So from stage 2 to stage 4, you will get the information of pore size distribution, and after approaching the stage 4 where all the pores are filled, you can get the value of pore volume there. This is the graph that is typically been obtained from here. The basic consideration when we talk about such analysis are three. One is the temperature, second is the pressure, third one is the volume. So I'll talk about the temperature first, because we need to perform this whole exercise over a critical temperature of nitrogen, which is minus 196 degrees centigrade or 77 Kelvin. So you need to have a container which can hold liquid nitrogen there, because to create the ambience of 77 Kelvin, you need to have the liquid nitrogen there. And when you deal with some microporous sample and you want to perform the micropore size distribution there, this whole isotherm may go up to 3 to 4 days. So whatever container to hold the liquid nitrogen you are having, it should have the capacity to withhold the liquid nitrogen up to that extent. So the DeVar that we provide here with this instrument is a 3-liter DeVar, and it can hold the liquid nitrogen for more than 90 hours. Then the P0 measurement, because when I talk about that curve is between the volume adsorbed and the relative pressure, which is P by P0, you would be requiring a concrete information about the P0 cellars. So when we talk about P0, it is the saturation pressure of the adsorbate gas, and which will change with the change in the ambience. So if the temperature is different in the morning and in the evening, then the P0 values will also be different in the morning and in the evening. So to get to know the correct P0 value, you should have a real-time P0 measurement. And for this, a dedicated P0 cell is required. Another thing that is come into consideration here, that the P0 cell should be made up of the same material as of the sample cell. If the sample cells are made up of glass, then the P0 cell should also be made up of glass, because then only they will experience a similar thermal environment. And the last consideration was the volume, the void volume. Void volume is basically the empty space in the sample cell after you have filled the sample there. So how much space is still available once you have already added the sample is called as void volume. Now to determine this void volume, there are different ways to do it. One is the helium measure, where you fill the helium gas into the sample cell and you get to know how much helium can go inside. And this volume is the void volume. Another one is the NOVA mode, which means no void volume analysis, NOVA. So this means that the sample cell is already calibrated. You already know how much is the volume of the sample cell, and then you add the known volume of sample inside. Now by subtracting the volume from the total volume of sample cell, you get to know the void volume. And then the user entered mode, where you need to calculate the volume of the cell itself, and you need to insert the known volume of sample into it. So this is the completely manual mode in case of user entered option. So in anti-fire system, we have a strategical advancement that we do reduce the void volume by reducing the cold zone there. So just to make you more clear, so this type of sample shall be typically used for analysis. And I have given you two cases. In one case, we have immersed the sample cell into liquid nitrogen up to this level, and in another case, we have dipped into this level. So since it is dipped into liquid nitrogen, this whole region is cooler than the above region. We called it as cold zone, and above one is called as warm zone. So what is above the liquid nitrogen is warm zone, and what is inside the liquid nitrogen is cold zone. So the case one is having large cold zone and a small warm zone, and case two is having a small cold zone and large warm zone. And as you understand, if the gas, any gas gets cooler, it starts getting denser. Since we are talking about nitrogen at liquid nitrogen's temperature, it will start getting denser, which means to attain a relative pressure of any relative pressure of X, let's say X, it will be requiring more gas molecule in this range because it is already cooler. So to attain the same pressure, it will be requiring more gas molecule than this case because the cold zone is small. Now this cool zone is small, is giving you a lesser void volume because total number of gas volume inside the sample cell will be less than this case, which means say in this case the total number of gas molecule is 1000 and in this case it is 100 to maintain a same relative pressure of P by P0. So if at a particular P by P0 value, the sample has the capacity to absorb only 10 gas molecule, in this case, the analysis sensitivity will be that the instrument has to measure the change of 10 out of these all 1000 molecules. While in this case, the instrument needs to measure the change of 10 out of the 100 molecule. Now we know it is very clear to us that to measure the change out of 10 out of 100 will be more significant than to measure the change of 10 out of 1000. Because if we talk about gas molecule, these are very theoretical numbers. The numbers of gas molecule will be very huge. And if the sample is absorbing very less gas molecule there, this change, whatever has happened, may behave as a noise for the instrument. So if we could reduce the void volume, this way we can enhance the sensitivity of analysis. And as I told you that we have maintained this small cool zone for minimizing the void volume. This type of thing we are using, we have a level sensor here, and with the help of level sensor, we are controlling the small cold zone throughout. So here you can see that this is the container in which we hold the liquid nitrogen. And you can see it is already uplifted. So it will uplift to the level that this level sensor, the black one, will start touching the liquid nitrogen. So you can see that the level here is above the bulb's shoulder. So whenever the liquid nitrogen touching this black part, this bulb will be into the liquid nitrogen. And since liquid nitrogen is a evaporating coolant liquid, it will evaporate with time. After some time, there will be a gap, so this level sensor will not be touching the liquid nitrogen. But as soon as it happens, the DibrU again uplift to the level that the liquid nitrogen starts touching the level sensor. So this way, we were able to keep a small cool zone and a constant cool zone throughout the analysis process. Besides, to finish this analysis quickly, we have different innovative dosing routines. We have the option of delta Vmax. We have the option of initial fill. We also have the option of maxi dose, which is like every next dose will be higher than the first dose, so that the equilibrium would come quickly. As people tends to use different type of gases for gas option, one may use nitrogen. Nitrogen is the most commonly used gas because it is very easily available, and liquid nitrogen is also readily available. But the problem in case of nitrogen is its quadrupole moment, because nitrogen is a biatomic molecule and each nitrogen atom has a lone pair of electron onto it, which is creating a dipole pair. Again, second problem is that since it is a biatomic molecule, the question of orientation will also be there. And since it is having a quadrupole moment over it, it will be attracted towards the surfaces which are polar or charged. So if you want to do the size distribution over some charged surface, you need to create a very, very low P by P0, so that you could get the information of how much nitrogen has been filled at particular pressure in a microporous stage. So this was the problem with the nitrogen uses, but still people use it because of its readily availability and the cost of liquid nitrogen and the nitrogen gas itself. But IUPAC said that the right choice of gas is argon. You should use argon because it is monoatomic, spherical in shape, no orientation question, it is non-polar, inert, no surface charge, its kinetics is faster than the nitrogen. But the only problem why people cannot use argon, or people typically do not use argon as a routine choice, it's not like the argon is very costly, but the liquid argon is very costly. You can get the argon easily, but to get the liquid argon, it will require a huge amount of money. So this is the concern why people cannot use or do not use the argon on a routine basis. Some people are also interested in knowing the CO2 adsorption over the substrate. They typically want the micropore size distribution with CO2. Now, when we talk about CO2, the saturation pressure of CO2 is very, very high. It is 26,400. Now, since the saturation pressure of CO2 at 273 Kelvin is very high, it can go into even those narrow micropores where the nitrogen and argon cannot enter. So if you want to know the micropore size distribution in more detail, use CO2. But the only problem with CO2 again is like it is having even more quadrupole moment than the nitrogen. So if there is any surface which is charged, or if you want to use some activated carbons or some polar surfaces, you will not get the size distribution with CO2 because CO2 is having the affinity over there. And when you are dealing with some low surface area sample, then people typically use krypton because of its low saturation pressure at 77 Kelvin. So since I talk about CO2, it was having high saturation pressure to 26,400, while in case of krypton it is only 2 torr. When we say less saturation pressure, it means lesser number of gas molecule will be there in the sample set to obtain a particular pressure. So this way, krypton can be used. Krypton can be used to do this. So we have done some technological advancement in the use of gases as well. As I told you that the nitrogen and argon can be used for the same material, but in case of nitrogen, you need to go up to lesser P by P0 value. Say in this example, you need to go up to 10 to the power -7. While in case of argon, the same information can be achieved by going up to 10 to the power -5. So the time that has been saved from 10 to the power -7 up to 10 to the power -5 is quite significant. But as I told you that we cannot use or we do not use argon because liquid argon is very costly. So Enderman has provided you a solution with this accessory. We call it as cryosync. Now with the help of this cryosync, you can develop the ambience of liquid argon with the help of liquid nitrogen only. So the critical temperature of liquid argon is 87 Kelvin, while the temperature of liquid nitrogen is 77 Kelvin. So this instrument, this device, cryosync, will raise the temperature of liquid nitrogen from 77 Kelvin to 87 Kelvin. It will work like an immersion heater, and with this, it can raise the temperature from 77 to 87. Now the ambience of argon is already there, liquid argon is already there. You can use argon as a choice of an allied gas there. The third part of this surface characterization was the data interpretation. You may have to use different type of data reduction enzyme. If you want to analyze surface area, you can do it with BET surface area analysis. You can also use Langmuir, but in case of Langmuir, the sample has to be strictly microporous because Langmuir doesn't assume any multi-layered adsorption there. So it has to be strictly monolayer adsorption. So if your sample is having mesopore or macropore, one cannot use the Langmuir. For mesopore size distribution, BGH method is there, DH method is there, FHH is there. For micropore, HKI method is there, SF method. These all are the data conventional data reduction design which typically people use. But the only problem with this conventional data reduction designs are they underestimate the size when you are having narrow mesopores or micropores there. even up to 30% underestimation can go. So to help into this problem, advanced data reduction regimes are there, which are like density functional theories, which they provide the microscopic treatment of absorption-desorption phenomena over different statistical mechanics. They also take into account the adsorbent-adsorbent interaction and the geometrical shape of the pores there and the temperatures. So with these density functional theories, one would get a more accurate pore size distribution than the conventional data reduction designs. There are different density functional theories. One is non-local density functional theory, another one is quench-sequence density functional theory. Now, non-local density functional theory assumes that the surface is chemically and geometrically inert, while in case of quench-sequence density functional theory, it is assumed that the surface has some activity over it, so it is heterogeneous in nature. Besides this, DFT, Grand Canonical Monte Carlo simulation, can also be used to determine the pore size distribution over the surfaces. This is the instrument that Enterprise promotes for surface area characterization. This instrument is completely modular. You have the option to have one analysis station, two or three analysis station. All the stations can work simultaneously. A coolant level sensor and a DeWar uplift mechanism is there. This is the patented technology with Enterprise. Different type of sample cells are there. A large 3-liter DeWar which can hold the liquid nitrogen for more than 90 hours. This is also the one of the most important feature that the Enterprise only provide you. No other competitor can give you this much holding time there. Then 4 degassing ports. This is another feature that you have inbuilt degassing ports there, and over these degassing ports, different temperatures can be set. Then different degassing abilities are there for temperature ramp, backfilling, pressurized test, evacuation crossover, and pressure control heating limit. For microporous sample, again, modularity comes into the place. You have the options to select a model which is suitable for super micropore or the ultra micropores. The system is completely independent. All the analysis station has their own gas manifolds with dedicated transducers. So if something is happening to one station, it will not hamper the performance of rest of the two. Different ways to determine the void volume, different dosing regimes, advanced data reduction regimes, and cryosync to perform argon isotherm with the help of liquid nitrogen as the coolant liquid. So these are the few characterization technique that one can go with for nanomaterial characterization, but we also offer a few other technique where the gases and the mercury adsorption can play a role. I would just give you a very brief for those. One is the mercury intrusion porosimetry. In case of mercury intrusion porosimetry, as I told you that the probing molecule since is now bigger, we can assess the macro pores in this case. So if as I told you, if the pores are smaller, gas option is there, and if the pores are bigger, mercury needs to be used. Since mercury is a non-wetting liquid, to make it into the pores, you need to pressurize it, and once you pressurize it, the larger pores starts to fill first, and then to fill the smaller pores, you need to create a very high pressure. Now, here we are pressurizing the sample cell, and because of this pressure, this mercury is intruding into the pores. Now, this mercury will itself behave like one plate of the capacitance, and there will be another plate over the sample cell itself. So, the measurement here is of the capacitance change. As the mercury level is going low into the sample cell, there will be a change in the capacitance. So the change in the capacitance has basically been recorded, and this change is actually corresponding to the volume adsorbed there. So as we increase the pressure, more and more gas will get adsorbed. So the basic phenomena that is occurring there is like once you fill the mercury into the sample cell, first of all, it will make the sample compact. So it will be surrounded, the sample will be surrounded from all over the sides with this mercury. So it will be getting compacted there. And as you increase on the pressure, the mercury will first fill into the interparticle space, then the larger pore will be filled, and then the smaller pore will be filled. So we use the Washburn equation to determine the radius with respect to the pressure here. The instrument with which we can perform this and that Entenpar offers is Pour Master. This is the Pour Master system, and it is a benchtop configuration. You can keep this Pour Master even into your fume hood. It is having a very user-friendly Windows software for instrument control. One may have multiple pressure generation routines for it, and you can also perform a low pressure and high pressure analysis over the same system simultaneously. It has been featured or designed with safest handling of mercury. It has self-contained low pressure and high pressure stations. Cabinet is a completely enclosed cabinet here. So this cabinet itself will work as primary containment for vapors, mercury vapors, and if even from the evacuation line any mercury vapor is coming out of this, we have a cold trap line here. So this cold trap will trap any sort of mercury vapor coming out of it. All the transfer from low pressure to high pressure is being done at bench scale level, so you know not to lean it down or lift it up. And then there are micro switches for the precision limiting. This is the Pour Master model. This is a two-station Pour Master, two high-pressure station Pour Master model. So typically, this Pour Master is having four configuration: 33 Pour Master 60, Pour Master 33 GT, and 60 GT. So the basic difference is for 33, you can go up to 33,000 psi pressure. In 60, you can go up to 60,000 psi pressure. As I told you, decrease the pressure, you can go up to smaller pores. So in case of 33 psi, you can go up to 6.4 nanometer. But in case of 60,000 psi, you can go up to 3.6 nanometer. This is a basic difference between 33 and 60. Now coming to the GT. In case of 33 or any of the model, there will be by default two low pressure stations. But in case of without GT models, there will be one high pressure station. While in case of GT models, there will be two high pressure stations. So there are two high pressure stations, two low pressure stations there itself, which means in totality, four samples can be analyzed simultaneously. As I told you that we have uh, enclosed cabinet there, which allows for benchtop operation. It will fit into your fume hood. A spill tray is there for secondary containment. Transfer is at the bench level. Ventilation kit is there, and if there is any accidental spill is occurring, it has been designed for its safest operation. There several alerts and operation limits are there, LED indicators are there, direct readouts are there, and an easily accessible SLAD part. The stop switch is there. So this is emergency stop switch. If anything is happening wrong there and you don't want it to continue, just press it. It will be stopped. A cold trap is there on the evacuation light, which will also provide a superior vacuum performances. The penetrometer cells, the sample cells here in this case of mercury intrusion porosimeters, we call them as penetrometers. So these penetrometers are made up of glass. So if there is any cladding formation is happening, you can see it visibly. So no cladding formation is there. It is very easy to fill the mercury, and different sizes are available for different type of samples that you might be having with you. Easy mercury and oil introduction system. And the good thing is that when you use the penetrometer cells provided by the Entenpar, you need not to perform any blank cell collection into it. Another parameter that one may be looking for is the density of these drilling fluids. We have a gas picnometer which can help you in determining the density of drilling fluid also. Now in this case, there are two sample chambers. One is sample chamber, another one is a reference chamber. But in the sample chamber, you fill the sample up and you pressurize the sample chamber with some gas towards some extent. And then you open the valve in between and the gas is allowed to expand from one end to another. And this gives us an idea that how much sample is how much volume your sample is actually taking there in the sample set. So this is the instrument with which you can determine the drilling fluid density here. You can also use other density meters, but since the density of this drilling fluid is quite high, it is very tough to do it routine density meters. And for that, we Enterprise suggest you to go with the ultra peak model where the density determination of the drilling fluids or any highly viscous solvent can be done very easily. So this ultra peak model is ultra simple also, and it is ultra precise as well. We use the true peak technology, which means that for different type of sample load, you may be having a small sample amount or you may be having a high sample amount also. We do have different type of sample chambers for those. So for larger samples, we have large reference chamber. For small amount of sample, we have small reference chamber here. True lit technology, which will say that whenever you are closing this chamber, you cannot overpress it or you over tighten or keep it loose. So the chamber's volume will always be the constant. We also have the options of bidirectional gas flow. This is typically being used when you have powder type of sample to protect your powder sample from flowing along with the gas flow. The whole system is having a peltier temperature control. Now, since when we talk about density, the temperature needs to be constant there. As the temperature can vary the density of the material, so we need to set it at a fixed temperature, and the system is having a peltier temperature control here, which can vary the temperature from 15 degree to 50 degrees centigrade. The machine is having an intuitive user interface. It has vibrant 7-inch touch screen there with which you can do any operation that is required to be done. You can see a graphical overview of the measurement process. You can see actually what is happening inside. Say the time you can see that the third run out of 5 has been going on and it is pressurizing it. This chamber is getting pressurized. These valves are right now closed. If they have been open, they would be in the same line of this. What is the sample weight? What is the temperature? How much pressure is there? What is the density? What is the volume? Everything you can get out of this. So you can also have the reports out of this. You can save your reports into pen drive. You can also have the options to visualize these results over the PC as well. That's it from my side. Thank you very much. If you have any concern or query regarding any of those instruments that I have discussed, related to light size of 500 or Atosob IQ or mercury user porosimetry or solid density measurement, please to ask.
Thank you, Dr. Gupta, for your answer. Any queries from the audience? You can drop your queries in the chat box also. If there is none, with my remarks. So on behalf of everyone and Dibrugarh University, I would like to thank Dr. Rishi Gupta and Dr. Sumit Singh for sharing with us their knowledge and expertise on nano fluids, nanoparticles, and also the biology. I hope everyone enjoyed the presentation. Thank you very much.
Thank you, sir. Thank you very much.
So with this, we come to the end of day 2 of this FDP. On behalf of the Department of Petroleum Technology, Dibrugarh University, I thank all the participants for joining and attending all the 4 sessions of day 2 of the FDP. My sincere thanks goes to the resource persons for sharing their knowledge and expertise with their talks. So the next session will be tomorrow at 10 a.m. Please join me again tomorrow at 10 a.m. Thank you once again. Have a nice day.